conference provided a platform for discourse on the prediction skill and future prospect of extreme precipitation events and tropical cyclones. Bring you the third edition focusing on predicting the monsoon weather extremes. We have an interesting lineup of talks and posters coming up. With this, we start the first session for today, Extreme Weather Events and Prediction. I invite Dr. Dev Nyogi to chair the session and Dr. Satyavan Ratna to co-chair the session. The rapporteur is Dr. Medha Deshpande. Thank you. Over to you, sir.
Good morning, everyone. Welcome to this day 4 of this STIPMEX workshop. The first session is actually the extreme weather events and prediction. In this session, we have 4 talks. And I would like to invite Dr. Vijay Talapragada from NOAA to deliver his talk.
Right, good morning. Can you hear me okay? Can you hear me okay now? Yep. Good morning. Thank you again to the organizers for inviting me and take part in this conference. It has been a wonderful meeting so far with a lot of interesting talks, and I really enjoyed meeting my old friends as well as new colleagues. Today, I'll be talking about a new system that NOAA is developing for seasonal forecasting. And many of you know probably we have been using the Climate Forecast System version 2, the CFS version 2, as our primary seasonal forecast system in NOAA for more than a decade now. The last implementation was in 2011. And IITM, incidentally, has taken that model and transformed it into a system model that significantly advanced the forecast skill and really made huge significant improvements in the predictive capabilities, both on the seasonal timescales and even longer timescales. But unfortunately, we were not able to take advantage of those developments, but we're back into the track of developing our next generation systems for both research and operations. And I will be talking about how we embarked on designing and developing this new system for operational predictions and research in NOAA. I wanted to acknowledge all those people who are back home at Environmental Modeling Center within NOAA, and also our collaborators across the world who have contributed to the community-based models that we are developing for both research and operations. And we also have a 5-year implementation plan that allows people to understand where NOAA is leading the next generation modeling systems into. The current production suite in NOAA has so many models. My focus will be on those 3 boxes that are on the top here: the climate forecast system, the GFS, and the global Ensemble forecast system. All these 3 are in the unified forecast system framework, which I'll be talking a little bit now. But the goal is to combine these 3 infrastructure-wise and use a fully coupled system for medium range to subseasonal to seasonal predictions. And to accomplish that, we started this project called the Unified Forecast System, which is a collection of several component models that are tied together using more modern software infrastructure. And it is all community-based, open source, open access. We even put our developmental versions on GitHub for people to interact and work on collaboratively or independently. And what we chose in the beginning are these components. The infrastructure is defined by the ESMF, the NOAA, and the CMAPS. CMAPS is the community mediator for Earth prediction systems that was developed jointly with NCAR. ESMF is the Earth System Modeling Framework. A lot of NWP and climate models use that framework. And NUAPC is kind of standards that unify the nomenclature and standards across different modeling systems. For the atmospheric model, we are using the finite volume cube sphere dynamical core, which is developed at NOAA GFDL. And that is replacing almost all atmospheric components of our NCEP production suite. CCPP is the Common Community Physics Package. You will hear more about that from my colleague Fanglin Yang in his talk. And the ocean model also comes from GFDL, the MOM6 modular ocean model. The CI's model is from the consortium of CIs, size 6. Wave model developed at EMC, WaveWatch 3. Aerosol model from NASA, GoCart. Land model is NOAA MP. That's what we currently are planning on. And a significant effort is going on to develop the next generation data assimilation capabilities within our UFS infrastructure using JEDI, which is a Joint Center for Satellite Data Assimilation driven software infrastructure that allows us to seamlessly assimilate data sets from all observational sources, also for reanalysis and reforecast and the coupled data assimilation. Each component has its own authoritative repository. We don't disturb those communities. They can still interact and work together to develop the next generation applications. And the applications here we are focusing on are the GFS, Global Ensemble System, and the Seasonal Forecast System. Conceptually, UFS is a toolbox, a lot of tools here. You can choose what you want. They all coexist. This is the mediator that connects almost every component of the system. It has the data assimilation component, the workflow, verification, products, all stay within this ecosystem. The blue boxes outside are the configurable applications. And they serve different needs. They have the space weather, hurricane, short range, coastal hydrology, air quality, and the medium range and subseasonal to seasonal applications. That's the focus of this talk here. So what are the goals here? We have to establish the priorities spanning from medium range, 0 to 2 weeks, to S2S. Weather is defined as something that happens between now and 2 years, according to Weather Act of US Congress. So we can predict weather up to 2 years. We don't need to confuse. Scientific goals that ensure that the medium range and S2S applications will meet our demands from the forecasters and their priorities. In order to do that, we design and conduct and evaluate the S2S applications so that we can demonstrate the performance improvement. And in that process, we work with our collaborators and stakeholders simultaneously. So currently, we have GFS version 16.3, last implemented in November 2022. It's also in the same framework, the UFS framework, but it has no coupling to ocean or ice. The target is to put GFS version 17 using the coupled model. Similarly, the GEFS v12, which is the Ensemble forecast system, also implemented in 2020, has no coupling to ocean or ice or aerosols. We plan to integrate all of those into the GEFS v13. And the CFS version 2, since March 2011, has been using the spectral model with the ocean coming from MOM4 and SIS1 CIs, which is pretty old and legacy. And the plan is to replace the CFS with our new seasonal forecast system. Conceptually, when you put all these 6 components together, this is how the model simulation looks like. This is a 5-day simulation running at 3-kilometer resolution with all these components activated. It's not possible to do operations with this kind of setup because it only takes 10 hours to produce a day of forecast, which is way beyond our 8-minute per day requirement. So, but it allows us to conduct research that allows us to identify the biases as well as identify sources where we can make huge improvements in our forecast systems for operations. So what do we do? How do we develop the system. This is a hierarchical system development, if you know what I mean. We add each component carefully to the system and test and evaluate until we are satisfied with the intended performance metrics. And in order to achieve that, we do prototypes, various prototypes with a predetermined testing cadence. In this case here, for instance, the prototypes of the UFS coupled model, it's a single member, 35-day forecast. We use twice a month initial conditions and for a 7-year period. That gives us enough samples that can be used to statistically determine whether any component is adding value or not. And if not, we make changes and retest. So this allows us to do rapid testing and development and evaluation to get what the desired incremental improvements that are. And like once we satisfied with the coupled model performance, then we start the 3-stream approach here. One is the HR1 to HR4, which are high resolution prototypes, which are meant for the GFS style application, the medium range, where we can use either 13-kilometer or even 9-kilometer to test the performance of the coupled system at that resolution. And then the ensemble prototypes, the EP1 to EP5, which are completed actually. These are 11 ensemble members going up to subseasonal timescales, and we have chosen a 2-year or a 4-year period to test the ensemble performance. We are still in the process of finalizing the testing cadence for our seasonal forecast application, but we have some results that I will definitely share. One important point to note, all these prototype datasets are available freely to anybody to look into and analyze and do research or offer us any help, even identifying what's wrong with that. The coupled model prototypes are from P1 to P8. As I mentioned, we made several changes for each of these components as we move from P1 to P8. And by P8, we already included the aerosols in our system so that we could analyze the impact of aerosols on subseasonal seasonal forecasts, which is first of its kind. I'll just give you one example of evaluation results from these prototypes. There are different prototypes, as I mentioned, and CFS version 2 is in the gray, and the rest of them are 3 different prototypes just for evaluation. And you can see different variables here: SST, precipitation rate, 2-meter temperature, geopotential height, CONUS precipitation, which is important for our North American region, and also MJO skill here. In almost all variables, the UFS P8, which is the final one in blue, either meets or exceeds the performance of our current operational systems. And that's the goal here. These are still not fully vetted in terms of initialization. For instance, they still use CFS initial conditions or GFS initial conditions. There is no data assimilation or cycling of those ensembles or anything that we intend to do in operations. This is just to check whether the coupled model is doing better or not. And the intended benefits are already shown here in terms of the MJO skill. Relative to CFS version 2, we added about 5 days of predictability into this coupled model. And that's definitely a huge improvement relative to the old generation models. And then this development shifted into ensemble prototypes. We have 6 different prototypes, EP0 all the way to EP5. It is going on in parallel to the prototypes that I described in the previous slide. So you take one stable configuration and run it in ensemble mode. For instance, the P8 is used here for EP3. And these are different variables that are going into the initial conditions and perturbations for the ensembles. And likewise, EP4 started taking advantage of the high resolution physics that Franklin and his team were developing for GFS. And likewise, HR3, this is the final configuration, which also includes the aerosol component along with ocean, ice, land, and waves. All these are completed in terms of the runs. And just to show a few results here, again, MJO skill The ensembles now are compared against the GEFS V12, the current operational system. And you can see both EP3 and EP4 using the latest physics packages have higher MJO skill than uncoupled GEFS. Both are using the same atmospheric model. The EP3 and 4 are coupled, and the GEFS V12 is uncoupled. That's the only difference. Of course, there are some differences in the physics, like Thomson microphysics is used, NOAA MP, and then ocean stochastic physics also is added. And the plan is to increase the forecast length from 35 days to 48 days to allow our customers to do monthly outlook forecasts. All right, that leads to the main goal of developing seasonal forecast system to replace CFS. I mean, there is a reason why we don't want to use the word climate anymore. As I mentioned, the weather is defined as 0 to 2 years. And incidentally, our CFS also goes out only up to 1 year, which is kind of a seasonal scale rather than climate scale, which is generally considered longer than 2 years. And the goals are to identify the common errors in the CFS V2 and then try to alleviate them. And that's where our focus is. For instance, representation of uncertainty, systematic drift reduction, reduction of biases, better infrastructure for scalability and supportability. We can enable this model to run in the cloud so that you can provide on-demand forecasts or surge forecasts, incorporated to UFS repositories so that we have the same community who can support this development. And typically focus on the common errors in our current operational seasonal forecast systems, both CFS and the NMME, which is the National Multi-Model Ensemble. And as I mentioned, it uses the same community components that I showed earlier. All these become part of the SFS V1. And just to give you an example of what this new model is doing when you run it in a free climate mode, just using the same P8, but run it for much longer time and test whether we have characteristics of a climate signal or seasonal mean depiction of the Earth atmosphere. And if you just look at the precipitation, these are kind of CMIP5 results. The typical problem with many of these CMIP models is the double ITCZ. If you look at the UFS P8, the mean precipitation did not show that signature of double ITCZ, although the precipitation itself has high bias. So it is probably a good signal. We still need to know why, but the first results are really pretty encouraging. Then we started looking into different prototypes in an ensemble mode. We used a lower resolution, C192L64, and use a P5 version, a slightly older version, and then used the MOM6 and Size6. We did not use waves in this experiment, but we ran 41-member ensembles out to 9 months to really look into the skill when we include more stochastics and the perturbations for both atmosphere and ocean. The NINO 3.4 forecast skill from these experiments, the UFS is in orange here. The GFDL sphere is in blue. The CFS version 2 is at the bottom here. And obviously, CFS is way behind in its skill, particularly for the NINO 3.4. And the black on the top is the multimodal ensemble when you also include the UFS. And the other black line with a circle here is the multimodal ensemble without the UFS. So not only the UFS is performing among the best performing members, it also adding value to the multimodal ensemble. And remember that there is no bias correction yet in the UFS. So there may be even more added skill once we start understanding the bias corrections. If you look at how the individual members perform, this is like best, one of the cases like El Nino. We have the 41-member ensembles here showing the prediction of an El Nino case here, the variation among all these ensemble members is as high as 5 degrees, but it did essentially capture the signature of the El Nino relative to the CFS version 2 bias-corrected members. The spread is pretty large, but there is a signal that matches the performance of the CFS. So if you apply bias corrections, definitely the results will be much better. Similarly, for La Nina case, the spread is even larger, but the general trend of La Nina is captured by UFS as shown here. The trend, but return to normal SST, probably it could be delayed, and there may be a warm bias in the winter time that we need to understand and probably address it in our next iterations. Even for the neutral case, the spread is pretty large. It has a good prediction for the neutral case. And so in general, the large-scale modes of variability are well captured by CFS, by the seasonal forecast system prototypes. That gives us confidence that this model is getting ready for replacing our operational CFS. There is also a simultaneous development going on in improving the scalability and performance optimization. And one of the aspects that recently Ke Zhao and Fanglin Yang sitting here have focused on is to use a hydrostatic option within our Fe3 core. All our previous results that were shown were using non-hydrostatic option. And the goal is to see whether hydrostatic option gives you similar performance. And in addition, it has a significant computational cost saving, like as much as 47%. And we found immediately, like, if you use a larger time step, the model becomes unstable, whereas the hydrostatic option decreases the forecast time rather significantly. And if you look at the results, I just used one of them, the QBO, the general mean at the equator, this is a 2-year run, and this is the analysis. And these are the two seasonal forecast runs. One is the non-hydrostatic, another is the hydrostatic. And hydrostatic appears to be much closer to the GDAS. Non-hydrostatic has a faster evaluation of QBO relative to the hydrostatic option. So that gives an encouragement that we can go ahead with using hydrostatic option for our seasonal forecast system. Another important aspect of operational seasonal forecasting is the data assimilation. And data assimilation is not only needed for initial conditions, but also for reanalysis, which is an important part of the seasonal forecast system, because you need the data for calibration and validation and also bias corrections. We use the tree analysis to initialize the reforecasts, and then the goal is to develop multi-decadal reanalysis reforecasts to support applications of the seasonal forecast in operations. For GEPS V13, which will be also a coupled model, we could not get into the coupled initialization as much as we would like to. So instead, we went with a 30-year replay. A replay is like, you use the ERA 5 and ORAS 5 reanalysis and replay it to FE3-based initial conditions and MOM6-based initial conditions. We used that replay, and we generated 30 years of analysis. The dataset is available here in this link. And along with that, we also have a 50-plus year publicly available observational database that goes into the coupled data assimilation. We are in the process of developing a weekly coupled reanalysis using Ensemble 4D VAR or 4D ENVAR. That's a work in progress. We also have Ninja. This is the new project, the NASA NOAA Joint Archive for Observations for Reanalysis. And all these data sets are available for anybody to use across anywhere. So that leads into this Joint Center for Satellite Data Assimilation's new venture of JEDI, which is the infrastructure for unified data assimilation and reanalysis. We are using part of it already for marine components like ocean, ice, land, and aerosols. We are already using JEDI. atmosphere. We're still making progress, but that will be available in the next few months to a year or two. We are using GSI in operations since 2007. This is the grid point statistical interpolation. Many of you are also using in India or elsewhere, even with the WRF. But portions of the code are older than many of the young generation scientists sitting here. So we need to move on and identify how to take advantage of the emerging industry's software standards for improving the efficiency of the data assimilation systems. So the JEDI is a model agnostic, generic and portable, does not impose any methodology on anybody, and it allows to share efforts. Like if you have any new observations, you can easily plug into this JEDI. And it also allows one shared code base for all data assimilation from global to regional to coupled Earth system components. A few examples here. This is the schematic of how we would like to do the weakly coupled data assimilation. The FE3, the GSI is right now still supporting the atmospheric component, but the waves and the MOM6, the ocean and the aerosols and ice model and NOAA MP, they're all using this JEDI SOCA, the sea ice, ocean, and coupled assimilation. It has the hybrid ENVAR. It's using 80 members. The LETKF algorithm provides the Ensemble, and it can handle different observation types much more easily. And one of the examples that I'm showing here is when we did the weakly coupled data assimilation with GSI and the JEDI SOCA for the marine components, just 3D VAR, you can see there is a huge reduction in the analysis errors that have easily demonstrated the value of the coupled data assimilation for initializing our Earth system models. This is just using AVHRR NOAA 18 data sets in our assimilation system. Likewise, a huge improvement in the Arctic, Antarctic sea ice when we assimilated in this coupled system the data from the sea ice coming from the database that CPC manages. So I'm almost completing my talk here to show where people can engage in this huge community-based enterprise. We have started something called EPIC, Earth Prediction Innovation Center, that allows people to interact. There are user supports available. You can get the codes. There is a meeting happening next month. It's called the Unifying Innovations in Forecasting Capabilities. Again, a huge event where a lot of community engagement happens. We have code releases. The UFS capabilities are released. The regional rapid refresh forecast system or land DA or many of the use cases are available online. And all these 10 different focus areas that are in the seasonal forecast system are supported, and we are seeking community inputs and collaborations. So anybody who is interested in working with us, these are ways to engage. The user engagement through EPIC NOAA, developer access through GitHub, as I mentioned, open access, open source, and all the data is also available openly and freely. And we'll be glad to take any questions. Thank you.
We have a time for maybe one question.
So,
yeah.
So this SFS headcasts you are doing only with the now ERA5 and ORSFI. JD's contribution is to only to remap. Is it correct?
yes.
So this weakly coupled and strongly coupled, when are they expected to be?
So the weakly coupled is currently in action. We still are using GSI though for atmosphere. It is currently working. It is being demonstrated. It will be part of our GFS version 17, and also will support our coupled reanalysis development, which is the scout runs are happening right now. So there is a huge progress in that field. Still a lot of obstacles to overcome, but significant progress has been made.
Any other last question? Yep.
I would be interested, coming from Germany, if you had made any comparison with the icon model, which is now very much used and encouraged to be used in the German community. How does it compare with your cube dynamic core?
Yeah, right. That's a great question. I think we have some preliminary evaluations going on with international, the WCRP, WGNI. We are providing these data sets for inter-model comparison. In terms of systematic evaluation, no, we have not done that. Maybe that's something we can look into. Thank you.
Any other burning question? I guess not. Thank you very much, Vijay. Appreciate it. Thanks. Thank you, Dr. Vijay, for this interesting talk. Our next talk is by Professor Kerry Emanuel, MIT USA, who will be delivering his talk online.
Okay, I don't know if you can hear me.
Over to you, Professor Emanuel.
Okay, can you hear me now?
Yes, we can hear you.
Okay, I'm going to share my screen. I need to have somebody enable me to share my screen. There. Okay. Looks like I can do that now. Okay, can you see my screen? Is that all right?
Yes, we can see you.
Okay, good. Well, good day to all of you. I'm speaking to you from France, and I want to talk to you today about a very interesting new subject for me, which is the physics underlying severe convective storms. And in particular, I want to address the question of how we build up energy in the atmosphere for such storms. Here's a picture of one of the phenomena associated with severe storms, which are hail, which does a great deal of damage. So why should we care about these storms? From a practical standpoint, there are significant cause of damage and especially loss of crops worldwide. Comparatively little is known about how climate change affects this particular weather hazard. And I'm going to focus on the concept of convective available potential energy, whose acronym is CAPE. It's an important ingredient in severe convective storms. It's not the only ingredient, but it is an essential one. And I'm going to focus about how we get large values of this quantity. And I'm going to talk about how we might understand the climatology of CAPE in today's climate as a step toward quantifying current and future severe convective storm risk. So each year in the US, 1,200 tornadoes occur and on average kill about 60 people. They injure about 1,500 people and cause roughly $400 million in damages. On average in India, several tens of people a year are killed by tornadoes. Hail causes several $100 million in damage each year on average, mostly to crops and property in India. So this is a serious problem in many parts of the world, including the US and India. Here is a map of the climatology of hail in India. This is the average number of hailstorm days per year in each of these districts shown on the map. So what is convective available potential energy, or CAPE? It is essentially the energy stored in the atmosphere when you have conditional instability. Here is an atmospheric sounding. This is an actual sounding. So on the vertical axis, we have pressure on a log scale decreasing upward. And on a skewed axis, we have absolute temperature. The thick black line you see on this is the actual profile of temperature versus altitude or pressure measured by a weather balloon. The dashed lines are various adiabats. The dashed line you see down here in the lower left is a dry adiabat. The other dashed line is called a pseudo-moist adiabat. Air lifted from the boundary layer initially will be stable. That's a dry adiabat, that's a moist adiabat. But if lifted high enough, it will be positively buoyant relative to the environment and accelerate upward. One can show that CAPE is proportional to the area enclosed by the sounding and the moist adiabat in a situation like this. The reason that we can build up a lot of convective available potential energy, and this is very important, is that you have a barrier layer, which is called convective inhibition. So that's the only other acronym you need to know here is CIN, C-I-N, is proportional to what we call the negative area in the sounding. It's this area down here. The existence of this potential barrier to ascent of air from the boundary layer is essential to allowing CAPE to build up. Now, over most of the world, most of the time, including India, but particularly over the oceans, we don't have a situation like this. We have a situation which is much more like Rayleigh-Baynard convection or boiling water in a pan. We call it quasi-equilibrium convection. The atmosphere is essentially always convecting, and the convection is using up energy at the rate at which it's being generated by large-scale processes. And if we look at a typical sounding, weather balloon sounding in the tropics, this is one from the island of Majuro in August of 2016, but they all kind of look like this. What you see here is the sounding itself is in red, okay? That's, again, temperature, there's pressure on a log axis, temperature on a skewed axis here. And if you just pay attention for the moment to the dark blue dots, that is a sample of air lifted from the boundary layer, and you're showing its temperature basically, and you notice it falls right along the actual sounding. What we see universally in this sort of situation is convective neutrality. That is, it's a very, very efficient process. So we have a self-organized critical system, and that is right at the lip of stability. So we see precisely zero CAPE most of the time. Now, over land in the tropics, the diurnal cycle is a little bit too fast for quasi-equilibrium. So we see a little bit of CAPE buildup in the afternoon, which is why you can have thunderstorms that are stronger than maritime convection, but we don't ever see very large values of this quantity in the tropics, and mostly over continents in the spring and summer. But there are interesting exceptions which dictate the climatology of this. Now, when you look at convective storms that happen under high CAPE, they look different. They're very dramatic. This is a picture of a thunderstorm over the central United States. This is the kind of storm that breeds tornadoes and hail. You don't have to be a meteorologist to know you're looking at something a bit qualitatively different from tropical convection. And here on the same kind of diagram is a sounding characteristic of what you would see before, not necessarily during such a convective storm. Once again, the red is the temperature profile measured by a balloon as a function of height. And these dark blue dots are different. There are different adiabats we sometimes use. The dark blue dots are the temperature of a sample lifted from very close to the surface. And you can see that it is much warmer than the environment through a large distance. If you look, focus your attention on the bottom, if you squint, you can see that there's a little kink in the sounding down here, which allows there to be a barrier layer so that there's convective inhibition. That is precisely what allows this convective available potential energy to build up without immediately being released. Okay, now if we converted all the energy in the sounding to the kinetic energy of an updraft with 100% efficiency, it would have a speed of 110 meters per second, which is really, really large. You don't want to be in an airplane that flies through that, compared to the 1 or 2 meters per second, which is characteristic of tropical or ordinary convection. So this is really a very different situation. And the question is, how do you get soundings like this? Why does that happen? How does it happen? And that's what I'm going to talk to you about. The key questions are what determines, for example, the geographical distribution of high Cape storms? Why do things like tornadoes and hailstorms peak characteristically in the late afternoon to early evening? And why do they occur mostly in the spring? Why are peak Cape values around 3,000 to 6,000 joules per kilogram, which you can convert to kinetic energy, if you like, for the updraft speed? That's what we observe. Can we predict that by a scaling argument that they should be something like that? And finally, how might these values change with climate? So the conventional view, and this comes right from my old textbook, and this is a situation in the United States, is that the way you get these soundings is to start with an air mass which has been strongly modified by its presence over very dry land, like deserts. And if you look off to the left of the diagram, those little upward pointing arrows are meant to be the Rocky Mountains. And over here we have the deserts of the southwestern US and northern Mexico. They get very hot in the spring. The soils are very dry, so all the sun goes into heating and not to evaporating water. They're very hot at their base, but they get cold rapidly as you go up in the atmosphere. You take that air mass and you physically move it over moist but cool air coming from the Gulf of Mexico. And that creates, between these two layers, this capping inversion that allows Cape to build up. That is what I always thought. That's what most people think. It's the conventional view. It turns out to be largely wrong in an interesting way, which is really what I want to talk to you about today. So we having looked at this for a while, have now an alternative hypothesis, which is that large Cape is produced when a deep dry adiabatic layer, that part of the old idea, is maintained. A deep dry adiabatic layer, dry adiabatic means the temperature is falling quickly at height, formed over dry land, is advected not over moist air, but over moist soil, which is then subjected to solar heating. So the key ingredients are a dry soil, preferably elevated, somewhere upwind, climatologically upwind of moist soil. So we're maintaining that strong soil moisture gradients such that dry ground is upwind of moist ground is the essential thing here. So let me just show you a series of cartoons for this. So we're going to start with a dry surface indicated at the bottom here that's been heated by successive diurnal cycles from the surface. Remember, all the sunlight is going to heating the soil. The soil essentially has no heat retention. The amount of heat that you can store in soil on these timescales is very small. So it basically goes right into the air. The air gets hot, but it has a steep lapse rate and then giving way to a shallower lapse rate of temperature aloft. So we're going to take that air, okay, this is a temperature versus height sketch, and we're simply going to move it bodily over wet soil. And what happens when you do that? Well, the wet soil is much cooler because you're using a lot of the sunlight to evaporate water rather than to heat the soil. So the desert air in contact with the soil gets cool, but it also gets moist. This dashed line here shows the dew point temperature, if you will. It's fairly high down here, but of course you get into the desert air up here. So this boundary is the boundary between desert air. It was all starting as desert air, but it's been modified by contact with this moist soil, right? Here's the moist adiabat. So it's still stable. If you lift air, you don't get any buoyancy, all right? But you have this very, very strong barrier layer here. Now, the final step is you let the sun come up and shine on this system, all right? So what happens is the boundary layer heats up and moistens up. As it does both, the entropy of the air in the boundary layer increases, and the barrier layer gets weaker and weaker over the day. And so if you take air and lift it up now from the boundary layer, you find that it's negatively buoyant in this barrier region and then becomes positively buoyant. So this is how we think you can get large values of CAPE. I want to emphasize to you once again, this is rare. This is not something that commonly happens, even in places where geographically it happens, but it only happens in certain conditions at certain times of the year. Textbooks will make you think that high CAPE is frequent in the world. It is not. It's a rare phenomenon. So we're going to try to encode this in a very, very simple model. It's a one-dimensional planetary boundary layer, or PBL model. And the key features is we assume the air in contact with the surface, the boundary layer itself, is well mixed in conserved variables, which is approximately the case in reality. We begin with this dry adiabatic elevated mixed layer. So we assume that's already been formed. To make things simple, we have no moisture in that air. And that higher up in the atmosphere, the lapse rate becomes shallower, so the air is more stable, which is typically what we observe. We put that in contact with the surface, which we're going to radiate with sunlight, and we assume that there's surface energy balance in the first place. That is, all the sunlight hitting the soil is balanced by a turbulent flux of enthalpy, both a latent and a sensible flux from the soil. Later, though, we're going to replace that assumption with an actual soil model. That is, we're going to couple the atmosphere to a model of the upper soil layers and vegetation. We're going to begin in the simpler case with specifying the surface soil moisture content. That is how much of the how far the soil is saturated. But we'll replace that again by this soil model as we go on. We're going to use something called the aerodynamic surface fluxes for surface and latent fluxes. The parameterization in which those fluxes are held proportional to the large-scale wind speed, which in a one-dimensional model has to be specified as an external variable. We use Doug Lilly's formulation of the entrainment of dry air into the boundary layer as it grows. And everything else is based on conservation of mass and moist and dry static energy. So energy and mass conservation. We will assume that the mixed layer that forms when the desert air is put in contact with the moist soil is just saturated at its top at sunrise. Okay, and as the boundary layer grows, again, it entrains the drier, hotter air from above, the well-known process, and not controversial at all. The key parameters in such a model are the mixed layer potential temperature that you start with, the initial boundary layer temperature and humidity, the initial depth of the boundary layer, but we tie these two together by the assumption that the initial boundary layer is just saturated at its top. So we only have to specify one of these. We specify the large-scale surface wind speed, and initially the fraction of saturation of the surface soil moisture, the exchange coefficients and the turbulent transfer, magnitude and time evolution of the insulation, and if we do couple, when we do couple to a soil model, we are unfortunately going to have to add a lot of parameters to this, which is too bad, but we haven't been able to figure out which ones we can throw away. They all seem to be important, which makes me a bit nervous. Here is just showing you a diagram of local time going from 0 to 24 hours of the specified net radiative flux into the soil. It's negative at night because the soil is radiating in the IR, and it's positive in the day because that's overbalanced by absorbed sunlight. It's just a specified function. It integrates to 0 over 24 hours. So that's how we're forcing the system. So let's first look at the case where we specify the soil moisture. And what we're seeing here is the development of CAPE in the single model over the course of 18 hours. So we start at sunrise, local time 6 hours. At the left-hand side of this diagram, we go to 18 hours, sunset, okay? And these curves are for different initial temperatures of the desert air. And you can see it matters a lot that those initial temperatures vary from 294 Kelvin in the lowest case, to 310 Kelvin. And what happens to the CAPE is it grows, it reaches a peak value and then declines. We stop the integration when the convective inhibition, which is not shown on this particular diagram, vanishes. So as we make the desert air progressively warmer, CAPE goes up very quickly with temperature. If it's too cold in the desert, you don't really build up any CAPE to speak of. If it's very hot, then it turns out the convective inhibition does not go to zero before the sun sets. You still have the barrier layer. It hasn't gone away. We call this a situation of stranded CAPE. So the sun sets, you no longer can erode the barrier layer just by solar insolation, but you have all this CAPE. In practice, that can be released later or survive until the next diurnal cycle. There are lots of interesting things that can happen, which I won't have time to talk about. This is the same exact integration, but showing you the convective inhibition, which starts out quite high, and the hotter the desert is, the higher that inhibition, the stronger the temperature inversion. That declines during the day, and as I said, in the two hottest cases, doesn't vanish. When it does vanish, we stop the integration, presumably deep convection breaks out, and you're off to the races with severe convection. So now we're going to couple this to a soil model, the simplest one I could find. It's a forced restore representation of soil. It has basically just variables at the surface and in the root zone of the soil, and those variables include temperature and volumetric moisture contents. The key variables controlling the soil are its porosity, thermal conductivity, heat capacity, its ability to transmit water, the vegetative cover, and variables controlling transpiration of plants. So you really made the model somewhat more complex in terms of the number of variables by coupling to the soil. This turns out, however, to be terribly important. So now we're going to do the same thing. We're going to look at the CAPE as time evolves in a situation where we're coupling now to the soil. So we don't assume surface energy balance anymore. There is energy storage in the soil. And these curves, again, CAPE versus local time, between 6 and 18 hours local time. These different curves are for different kinds of soil, with everything else being the same. And this is a little frightening because it means that whether or not you build up energy for severe convection depends very much on the type of soil you have. This ranges from clay, which is virtually impervious to water, to sand at the top. So the kind of soil makes a big difference. Now, this is a bare soil case. Let's see, is that true? Yes, I think it's true, without any vegetation. But it does depend on vegetation, and this is, I can only show you dependencies on a few of the variables that turn out to matter. This is just showing the CAPE dependence on the fractional coverage of vegetation, ranging from 0 at the bottom up to 100%. Vegetation, the presence of vegetation, all other things being equal, actually does tend to give you larger values of convective available potential energy. It depends on things like how much water is in the root zone. And this is for 100% vegetative cover. And you can see that if you make the soils too dry, you don't see that in this diagram. Nothing happens at all. And as you finally get up to 20%, you get some CAPE during the day. But it depends very much on how much water there is. Otherwise, what happens is that the vegetation dries out in the course of the day, and you don't have enough moisture to support high values of CAPE. Now, let me finally say that we have also, with my student PJ Tuckman, looked at what actually happens in nature, and I'm going to show you some of those results. This is for the US, but we have recently extended this to the whole globe. So I don't know if you can see where you are here in central United States. And what we do is we find from very high resolution reanalyses episodes of high CAPE and independent on whether that resulted in severe convection. So we're really looking at the time leading up to the severe convection. We're not trying to tackle the severe convection itself. There's a lot of literature on what happens dynamically when this stuff is released. We're not addressing that. We're addressing how high CAPE builds up. So here at the upper right, the CAPE, and you might be able to squint and see a little rectangular box. We take that box, we fill it with points, and we follow the trajectories backwards in time, both in the boundary layer, and that's these red streaks. You see the box here, going back in time, and the air that constitutes this barrier layer. It's usually a few kilometers above the surface, but of course, the air informing it usually descends into that layer. You have the blue and green trajectories over here are air that forms that barrier layer. And you can see that in this particular case, by the way, there's an ensemble of trajectories. That's why you see many lines. The air is coming from the south. It probably originated in this case over the Gulf of Mexico, but the trajectories that form the inversion uniformly come from desert regions, and we see that all the time. This, by the way, is the a proxy for the convective inhibition down here, and that's the control box. So that's this particular case. And now what we're looking at, there's a lot of quantities here, and I don't want to run out of time, but at the top, over about, let's see, 1, 2, 2.5 diurnal cycles, you see the CAPE. This is the red line. Don't worry about the red dashed line, the red solid line. And the convective inhibition, which has been multiplied by a factor of 5, so you can see it on this diagram in blue, all right? The convective inhibition, of course, builds up at night. It decays during the day and so forth. So you see all these diurnal cycles. Finally, you notice the CAPE building up over successive diurnal cycles. You have a lot of stranded CAPE every day. And then it finally gets released at time 0, or at least not necessarily released, but the convective inhibition goes to 0. And I won't bother with these quantities down here for now. Here's a different case where the control box is way over here in the east. It's a region of high CAPE at time t equals 0. If you see the upper right here. And you notice in this case, the trajectories happen to go around in a circle. They were never over water. And we see many cases where the trajectories, basically, you have to go back many, many, many days, and they might be over the Pacific Ocean, a cold ocean or something. These trajectories stayed over land, but the air that formed the capping inversion, the blue streaks, are always coming from dry land, okay? They're always coming from dry land. That's an essential ingredient in this. And same kind of thing here, the diurnal cycles. This is showing many diurnal cycles in this case of both CAPE in red and convective inhibition in blue, okay? And don't forget, we've multiplied the convective inhibition, I think, by a factor of 5 so that you can see it here. And again, there's stranded CAPE on most of these things. And finally, after many diurnal cycles, the barrier goes away and the CAPE is presumably released. Now, so let me just wrap things up because I'd like there to be time for questions. But what this implies for the climatology is that you expect to see large CAPE in places where there is moist soil climatologically downwind of dry soil. So if we look at this map, which we've only been able to produce in recent years, it's a satellite-derived climatology over just 7 years of soil moisture. It's a measure of soil moisture. Where you see yellow, it's dry. This, by the way, is for the whole year, which isn't entirely relevant. You want to look at it during the seasons of severe weather, but this is the best I could do. And the blue is moist soil. So where would we find dry soils upwind of moist soils? Well, if you pay attention to the red circle, the classical place here is the plains of the United States. You have the elevated deserts to the west, moist soils to the east, very sharp gradients, and the prevailing wind is from the west. So that's one obvious place. The Pampas of South America is another place where we expect to see this. And this indeed is a well-known place of severe hailstorms. It's a very big problem in places like Argentina. Another place is southeastern Australia. Lots of deserts to the west, but a moist coastal plain far enough away from the equator that you have, again, generally westerly winds from the dry to the moist regions. Northern India and Bangladesh, at certain times of the year, particularly, you have the desert, dry soils in Pakistan and places to the west. And at certain times of the year, anyway, you have westerly winds here that blow it over the moist coastal plains, river delta regions, and so forth. Eastern China is another candidate place. Now, if we go to the equatorial regions of Africa, the prevailing wind is from the east now. And this region in the eastern Congo is around Lake Victoria is interesting. You have very dry, elevated soils in Kenya and Somalia, and that air mass is advected over the very moist regions of Congo. And they have the highest lightning rates in the world here, very, very tall thunderstorms with a lot of cape. There's very little wind shear, so you don't have the other ingredient you need for severe convection, generally speaking. Europe is an interesting place. If you look at outbreaks of hail, which is very serious, by the way, in Europe in the summertime, invariably it happens when air from the Sahara is blown across the Mediterranean and over the moist soils of Europe. And there's a place in southeastern Africa. So let me wrap things up. Large cape occurs when deep, dry adiabatic layers are advected over moist soils. This is our hypothesis. We think there's something to it. I didn't mention this, but the length of the diurnal circle limits the amount of cape you can generate. Of course, diurnal peak values of cape increase monotonically with the potential temperature of the desert modified air. The hotter the climate, the more cape you can generate. It also, I didn't show you this, but it also increases with the surface wind speed and with the soil moisture when it's specified. Coupling to the soil and vegetation physics is important, and the dependence of on soil moisture may offer a degree of seasonal predictability of cape, which is something we need to explore. Agricultural and other land use practices on regional scales probably have already strongly altered the severe storm climatology. Global models are likely sensitive to how you formulate soil and vegetation, and global warming increases cape unless the previously moist soils dry out too much or lose too much vegetation. Thank you very much.
Thank you, Kerry. A lot of interesting ideas there, and I'll take up a couple of questions maybe, and I do have a couple of on my own. Shabin, I'm sure you'll have one, yes?
Shubin, thank you for the fascinating presentation. My question is the contrast of surface soil moisture the primary factor for those big cape, or that's just one of the factors? In other words, over regions, you have more homogeneous soil moisture. Are you saying there are no high cape cases?
Yes, more or less I am saying that somewhere upwind, it might be some distance upwind, you're going to have a way of generating these very hot air masses with steep lapse rates. Another conceivable way you can do that is if you have a hot, elevated plateau, whether or not the soil is moist or dry, you could perhaps do it that way as well. But if it's over a large, like the Amazon basin, it's just moist everywhere. And indeed, we see diurnal convection and we have ordinary type thunderstorms over the Amazon, but we don't see big hailstorms there.
Thank you.
Any other question? This one back.
I wanted to ask you, you made this point about the impact of CAPE on hailstorms, but then you said earlier in your talk that high CAPE is rare. So could you explain how to get these two things together? Is it about the most extreme events that you were speaking about? Another convection is perhaps different from what you explained, or did I get this wrong?
No, you have it right. I mean, severe convection itself is rare. I mean, the kind of really strong storms that produce damaging winds, tornadoes, which are rare in a global sense, and hailstorms. So, of course, it depends very much on the exact definition of rare, but I guess I'm saying the frequency of these severe convective events is partially rate limited by the fact that high CAPE episodes are relatively rare. There are places like central US where maybe April and May, during those 2 months, it's not so uncommon, but in a global sense, it's rare.
Interesting. My question is, when you show about the Indo-Gangetic region, where the most of the irrigations also happening. So when you have a irrigation parameterization in the model, did you improve the lightning predictions? Because most of the fatality in India is happened to the lightning. So that's my question.
Well, that's a very interesting question. I don't know the answer, but I think that if you wanted to predict that, if you wanted to predict, whether lightning climatology will change, that irrigation should be a pretty strong factor. By the way, you can get lightning in ordinary convective storms that aren't in one of these special environments just because of the diurnal cycle. But of course, these severe convective storms produce a really large amount of lightning.
No.
Thank you, Gary. This is Peter Hitchcock from Cornell University. I was a bit surprised by your conclusion around the prospects for changing the climatology of CAPE under climate change. It seemed like lots of different scenarios could be imagined depending on the pattern of soil moisture changes. But I think you only gave one sort of possible configuration. Can you say a little bit more about that?
I'm glad you asked that question. It's basically, if you hold everything constant, increase the temperature, you expect increased CAPE. What I didn't say and should have said is you also increase convective inhibition a lot. So these two things go hand in hand. But how soil moisture and its gradients change is absolutely critical. And it's not possible, I think, to make a sweeping statement about how those might change. It's going to be very dependent on how the climate changes and probably dependent on your models of soil moisture and so forth.
Yeah. Thank you for your insightful talks. I have just some basic curiosity. I'm asking that. So it's how this soil moisture, or it's when it comes to urbanization, when it is how this extremes and CAPE is being interrelated. So there also the this soil moisture and all those things plays an important role for the urbanization.
Yeah, it should. And let me emphasize that it's not just the soil moisture. There's a lot of talk about soil moisture. It's really important, but it isn't the only thing. The vegetation, and when we say soil moisture, now we can measure it at the surface with satellites, but we can't measure the subsurface soil moisture yet, probably never with satellites. The porosity of the soil, the type of vegetation, the leaf area index, these all matter. So one of the things I would say is that we've got to pay attention to all of these and not just the soil moisture, but the soil moisture is important.
Thank you, Kerry. I think we will stop the questions, but I have one, if you're still there.
I'm still there. I'm going to turn off my video because I'm having trouble with the connection, if that's okay, but I'm still there. Yeah.
So this is Dave Neogi, University of Texas, Boston. mean, when we look at it in terms of the variations with land atmosphere interactions, we have seen it with irrigation, we have seen it with urbanization, we have seen it sort of affected into the mesoscale mode. So the question is, are you suggesting that they don't need to be co-located in terms of the wet and dry boundaries, and that they could actually be over a much different regions, and simply the manner in which the air masses are coming together over a location can create the potential for convection? Or you're actually saying that we do need them to be co-located, and then the question would be, what is the scale of that heterogeneity that needs to be prescribed here? Thank you.
Well, it's an excellent question. My guess at an answer to that is it depends upon things like radiative timescale. So if you form a air mass with a steep lapse rate over dry land, how far can you move that, right, before those characteristics begin to go away because of modification by mixing on the synoptic scale, modifications by radiative transfer, subsidence, and so forth. My guess is you're talking about synoptic scales, 1,000 kilometers. So we have the example of air from the Sahara coming up over Europe, having to cross the Mediterranean, and that does happen. I don't know if I've actually answered your question. I had to try to interpret it, but yeah.
But I said it was the last one, but it looks like Krishnan has one, and I'll take that quickly. It says it's excellent talk, and extremely dry conditions prevail over many areas in Pakistan during May and June. What mechanisms can trigger very high CAPE over such dry areas? Wondering if the original theory of high CAPE generation by transport of moisture from neighboring ocean areas into dry regions would be applicable in such cases. I guess that's what you're saying too.
Yeah, that's an interesting point. The problem is if you transport moist air from an ocean over a dry region like Pakistan, it can be very moist. But nevertheless, if the soil is dry, when the sun comes up, all of the sunlight goes into sensible heating. So you get very rapid boundary layer growth. There's very strong entrainment of the dry desert air into the boundary layer. The convective inhibition goes away typically before noon. You might have some convection, but it isn't going to be very strong. So that's the problem you have with that. But thanks for the question.
Thank you, Professor Carey, for this interesting talk that followed a very interesting interaction as well. Now we'd like to move to the next talk by Dr. Estivalis Gaskan from Germany.
Hello, good morning, everyone. So first of all, thank you very much for the invitation to come here and to be able to show all the work that we are doing in terms of extreme weather forecast in ECMWF. I speak here on behalf of many of the colleagues that are working hard on this area. So let's start. What are the strategies in severe weather forecast in ECMWF? Well, first of all, the main one is creating new severe weather products and model improvements. So in that sense, every model cycle, we try to introduce improvements in the severe weather prediction. But also we create new products, post-process products. Some of you know quite well the EFI and some precipitation type forecast, easy point, and so on. But also we are now having and working hard in two different aspects. One is the Destination Earth initiative, which will try to create a very high resolution or kilometer scale forecast, global forecast from the IFS. So currently we have 4.4 kilometer resolution, and we are also understanding the uncertainty quantification from the 4.4 kilometers. So we are using machine learning to create this uncertainty. And finally, I will talk a bit about the machine learning models, in this case about the AIFS, which is our current artificial intelligence forecast system. And I will explain a bit more how it can help us to predict better the extremes. Okay, regarding the new products and model cycles, here is just a summary of what we have been doing in the last years. So the last model cycle that we implemented, it was in summer 2023. It was the 48R1. And in that, we did a big improvement in the increment of the resolution of the ensembles. As you know, we have 51 ensemble members in our ensemble system, and we increased the resolution from 18 kilometers to 9 kilometers. So now the high-res and deterministic forecast in the ensemble have the same resolution. We also increased the number of ensemble members in our subseasonal forecast from 51 to 100 ensemble members. And also we are computing it from the day one of the forecast now. So we have two databases that you can compare from the day one to the day 15, the ensemble forecast and the extended range forecast. In total, 151 ensemble that you can play with. And finally, we apply other upgrades in the multi-layer snow scheme and so on. But if you focus now in the 49R1 cycle, model cycle that we will implement in October, or well, after summer, we apply a couple of new important aspects. So the first one is the new ocean sea ice component that we are going to upgrade. But also we are going to implement new landfills or upgraded landfills and the SPPT. So the SPPT, the SPP, before we use SPPT to do the perturbations, so the stochastic parametrization tendencies. Now we will go to SPP and how we change this, what is in the concept of practical way. Well, in general, we notice that we increase the spread of the forecast of the ensemble, and this helps to detect sometimes better the extremes. So we notice that we can reach a bit better the extremes forecast with the SPP. And finally, we will also increase to 100 ensemble members our seasonal 6 forecast. And just to say, ERA 6 is ongoing, so we are preparing ERA 6 after ERA 5, and ERA 6 will have around 13 kilometers compared with ERA 5 that now we have 31. And as many of you are working with that, I think that it's important that you are informed about this new updates. Okay, so we're working quite a lot on predicting better organized convection, which obviously in global models and hydrostatic models are not very well handled. In this case, in the 47R3 last year, the cycle that we applied last year, we managed to improve the forecast of the microphysics. And for example, here is an example of the organized convection, square lines in Africa. And on the top is the observations, and on the bottom is the forecast. We managed to improve quite a lot the organized convection in that area, when before we struggled to do it. But testing this without the convective deep convection scheme, in 9 kilometers and also some tests with 4 kilometers, we cannot remove this scheme. We cannot switch off because we see that this organization just is disappear. Another important aspect that some people saw in some discussions is that we have the problem of the diurnal cycle is slightly shifted. In conclusion, I mean, I think that in total, on average, this is a test in Europe, but we reached the peak of the convection much earlier in the model. And the problem is that the convection dies too quickly in the model compared to reality because the Cape is consumed too quickly in the model. So this is something that has to be fixed in the future, but it's important that you are aware of it. Another important aspect is that all the parameters that we produce related to convection and severe weather are usually related to Cape. So we revise also the Cape and scene computations to agree with the, well, we work a lot with the European Severe Storm Laboratory to agree in a common pattern or common equations for this. So the main change what we apply is that we use virtual potential temperature instead of equivalent potential temperature to calculate this. And we notice that it improved quite a lot globally. So this is one of the improvements we did recently. This is the forecast indeed for today. is the deterministic and probabilistic lightning prediction that we produce in the CMWF. Many people work here, I think, with lightning prediction. So I wanted to put you the forecast because today is an exciting day, I think, if you like storms. As you can see on the left-hand side, the lightning plus density is quite high in our area, well, in general in the north of, in central India. But on the right-hand side, you have the probability of lightning plus density greater than 1. And we can see that in the last 6 hours, if we focus on the 12 UTC today, we are in the hot spot. So be aware that maybe we have some severe storms. I hope, if not, it means that the forecast is not so good. So. Okay, another important product we recently published, but it's not in the open charts, freely available, but probably will be soon, is the clear air turbulence. What I put this here, because it's quite important for the flights, for aeronautical purposes, let's say. No. This is now a trending topic because, as you remember, there was a problem with a Singapore airline going, I think, traveling not far from here, I think, and they struggle, they have very strong turbulences. So this product may help because you can establish in different levels and you can check different pressure levels and may help to predict these turbulences. The only problem is like there is a lack of verification because how you can verify this clear air turbulence with observation. So this is some open question that in the future we can maybe we collaborate with other institutions to see how to do. An important aspect is that we will produce this variable in ERA 6. So this means that even if you don't have this verified, we can calculate anomalies in the climatology with ERA 6. So this is also some good improvement. EFI, I think that most of you know the Extreme Forecast Index. This is a very a product that we produce for many years. But just I wanted to remind you how it works, and we use it to denote how extreme a given ensemble forecast, so our ensemble forecast, is relative to the model climate, so the climatology of the model. So if you plot here the black line of the model climate, and here you plot the ensemble, we calculate the area. So the value that we provide is like this area, and it means how the ensemble shift ahead or in the back from the model climate. And it gives you the feeling of how extreme your forecast can be in your place. This is important because we are still working on producing new products for severe weather with EFI. And the last one that was recently, a couple of years ago, 3 years ago, produced is the EFI for Cape Shear. So there are some parameters that the global model IFS cannot predict because obviously it's not capable to resolve well the processes, but it can give you an idea of something that can happen. Something severe can happen based on other parameters related to this severe event. So for example, this is an example of a derecho case that we had in Europe, in the Mediterranean in 2022. We don't usually have a derecho. Derecho is a very strong wind gust with a squall line that rapidly propagates, and it creates really, well, in this case, we have 12 fatalities in Corsica, but this is not happening frequently in Europe. It's more from the US. So in this case, the forecast was not good, obviously, to predict the exact wind gust that happened in that area. But if we see the forecast of the EFI Cape Shear at day 5 of the forecast, we can see this intense area that EFI is highlighting in red, which it can give you an idea of some severe event happening in that area. So this is just to say that even if we don't resolve properly some of the aspects, so some specific variables for extreme events, you still can have guidance from the Ensemble forecast system. Okay, this is the Ensemble vertical profiles. This is freely available. This is just to mention that with them, you can also have the forecast of 3-hourly forecast of your location. And it can give you also the feeling of the uncertainty of the forecast because you can see that it's plotted all these shade colors, plots the viewpoint temperature and the temperature for all the Ensemble members. You can see here that you have low uncertainty, here high uncertainty. And also, it's important to see that we produce the Cape. So it's like the distribution of the Cape in that area compared with the scene. So you can see also if you have some probabilities of having some convection activity. Okay, this is an important product that we are going to release publicly soon. So it's related to tropical cyclones, but we are going to create a graphical product, the CPS. So it's the cyclone phase space trajectories for specific tropical cyclones. So this was requested specifically from the Portuguese Met Service, and we have been working on that. But the important point is that you will be able to see from all the ensembles in the high resolution forecast in which side of this cyclone phase space you have your tropical cyclone. You can monitor the tropical cyclone from that side. So it can give you an idea about if you have already in the extratropical transition, if it's intensified, and so on. So it's complementary to what we have now. Okay, many people here in these days, we discuss about machine learning forecast, machine learning tools, what we can do with it. So as you know, we recently produced the AIFS, so it's our artificial intelligent forecast system. And what I am going to present is obviously this has lower resolution, so it's not so good as we have the deterministic forecast, but in some aspects can give you a better forecast. And I'm going to focus mainly in the tropical cyclones forecasting because it's what we have really studied until now. Okay, so first of all, a general overview. This is the stable, equitable error in probability space for total precipitation in the tropics. In this plot, you can see the IFS in red, and you can see the AIFS, the last version, in green. What happened here is, so if you have higher values, you have better forecast, so the verification gives better forecast, and here's the forecast day. So as you can see, we have from 1 to 10, and we see that for as we go to further lead times, we increase the lead time. The AIFS is performing better in the tropics than the IFS. So we can see already an advantage in precipitation forecast in the tropics in that sense. We are still producing more plots for the tropics, but unfortunately, we didn't have time. So most of the plots that we're producing for verification are related to the North Hemisphere extratropics, but we are on it. Okay, just like an introduction, how is the AIFS? So the first implementation was with 1 degree resolution in 2023, but we recently in January updated with 0.25 degrees, which is a really good improvement. So just to give an overview of how it was produced, it was based on the graph neural networks. And one attractive aspect of this GNN system is that we can learn from data on arbitrary grids. And this allows to the AIFS to work directly with the native IFS reduced Gaussian grid. So we can learn from different resolutions of forecast, okay? So what we did is to use a subset of the data fiber analysis to train the system, but also we have tuned a bit more with 2 years of the IFS. I don't have all the details, but the good point is that 2 days ago, the paper that describes this forecasting system was publicly available. So you have the link here. It has been submitted to a journal, to BAMS, but you can already access to the paper if you are curious about how it was produced. Okay, I put this in the training, but I think on Sunday, but I think that this is interesting to see how costly these AI models are. So you can see a perspective like this elephant is the ERA 5 computation. So you can see that it's huge, the capabilities that we need to produce ERA 5. But it's once, it happens once, you produce once and that's all. Then you have the ECMWF high res, which is this mouse, and obviously it's much less, but we have to produce daily. So you need still a lot of computation resources. And finally, you see this small ant that is the AI model. So I have to say that comparing the high res is very cheap. So it's why all the AI models are being producing more and more, because it's cheap. Obviously, they are not perfect, but they are cheaper. This is a very interesting question that we saw in a paper in BAMS in 2018, that the question is, have we reached the limits of the predictability for tropical cyclone track forecasting? So this paper mentioned that there are evidence that we have hinted the approaching limit of predictability for tropical cyclone track prediction, and it's nearly here, or it has been reached already. But what happened at this moment, we didn't know about machine learning models. They didn't exist. So what we did is to compare all or most of the machine learning models. And this is the tropical cyclone track verification for different forecast steps up to day 5. And what you can see, the high-res is in blue, the area 5 is in gray, and we can see that all the forecasting and machine learning models are reducing these errors in the cyclone track. So with machine learning models, we really can pass this limit that we thought that we had with the physical models in predictability of some aspects of the predictability. Here, this is the forecast skill for tropical cyclones 2022. This is for the IFS compared with the high resolution forecast in blue, dark blue is high res, AIFS is in light blue, and the dots corresponds to the new version that we have. As you can see, the position error is reduced in both. It doesn't improve too much in the second version, but it's reduced compared with the IFS. However, we still are a bit far away of reducing the error to be as good as is the IFS in terms of central pressure detection. So we can see that in some aspects, we still cannot go there up to the good forecast as the IFS, but in others, yes. And this is important because we don't have the resolution, the same resolution that we have in the IFS. And this is more expensive. So we can produce up to one limit, and the resolution of the machine learning models will increase, but there still is some challenge that we have to pass. This is another example of how the resolution helps in terms of predicting severe weather, in this case, tropical cyclones. This was a tropical cyclone, Belal, that happened near Madagascar. And it was a small tropical cyclone that at the same time that we were shifting from AIFS version 1 to version 2, so we could test. And as you can see on the bottom, version 2 could detect the formation of the tropical cyclone 2 days earlier than in the version 1. And we can say that it's a quarter of degree compared with 1 degree. So you can see that the resolution matters here, it's important. And it's just something that we have to address in the future with machine learning models. Okay, and why these models, these machine learning models, are much better in predicting the TC tracks? Well, in conclusion, I'm not going in detail to this plot. The critical point is the steering flow. So for the data-driven models, the machine learning models, we are reducing the steering flow errors. We found that we are reducing quite a lot, which will translate this in reduced tropical cyclone motion biases. So this is important because we can improve that aspect. And as the trajectory and the tropical cyclone tracks are much better, or are at least better than in the physical models, we are going to try to produce some open product freely available as well that will plot the machine learning tropical cyclone tracks. So all the machine learning models that are currently in the market, we will try to produce the tropical cyclone tracks as soon as we detect a tropical cyclone activity. So yeah, just pay attention because at some point it will be available in our open charts. Okay, now finally, just to finalize, we go to the Destinationers Initiative. If you remember, Tim Palmer mentioned about the importance of having machine learning models to learn and diagnose aspects that we can improve in the model, but also having a high resolution forecast model. And this is the high resolution forecast model with 4 kilometers we are producing. In this Destinationers Initiative, we want to create digital twins of the Earth. And this is a collaboration between ECMWF, ESI, and UMETSAT. So ECMWF is producing the Extremes Digital Twin, which is the IFS with 4.4 kilometers up to 5 days ahead. But we are also producing the Climate Change Adaptation Digital Twin, which is a climate model with between 5 and 10 kilometers. But I'm going to just show a couple of examples of the first one. Here is the tropical cyclone intensity that we tested with different resolutions. So we are testing or verifying how good is the IFS at different resolutions compared to the observations. And we can see that we are improving it as we increase the resolution. So here is 4 kilometers, 1.4 kilometers, and we see that we still have scope for improvement. We can go there. Here is also the super typhoon Bolaven in the Pacific, and we can see also that the destination air 4.4 kilometer managed to detect better. You can see how deep reach. It's not good enough as the track, as the official observations, but we are going to that direction of improving the intensity. But it doesn't happen always that we improve that. And in this case, it's like the tropical cyclone Otis that it was in Central America. And we see in the gray colors that is the high-res and destination air forecast. We didn't really detect the deepening of the tropical cyclone. What we did here is some research experiments, adding, for example, extra observations, reduced parameterized convection, higher resolution for the bar. And we see that as soon as we add improvements in the model, we could see that the detection it was much better. So it means we can go to higher resolution forecast, but we need to go at the same time with improvement of the model physics. If not, it doesn't work in all the cases. And finally, I will move, this is Medicaine Llanos. Medicaine is just a Mediterranean-like tropical cyclone that we have in the Mediterranean. And here is just an example of how moving to 4 kilometers, we also detect better the wind gust and the structure of these medicanes that are very small, so they are very difficult to detect. And if we focus on the waves performance, we can see also, compared to altimeters, that we are performing much better as soon as we increase the resolution forecast, okay? This is another example in Madeira, and this is just to show that also the precipitation in very high mountainous areas are better predicted as we move to high resolution. And 2.8 kilometers is the next step if we can reach, but for now we are staying in 4 kilometers because operationally it's very challenging. And yes, this is the last slide. Sorry for the long presentation, but this is another aspect that we know that we have deficiencies in the convection. We explained some of them before, but one important one is the propagation of convection from the coastal areas up to farther inland. And this is an example in Israel because we have many cases of this. So they provided us quite a lot of observations to check. So what we are doing now is some research experiments with modifications in the model physics, in this case, in the deep convection parameterization, to improve this. What happened is that sometimes it helps for many cases, but not for others. So in this case, this reduced cloud-based mass flux that we are applying, and we see that it improves, is degrading the verification scores in the tropics. So this is just to explain, anything is perfect. We have to work together resolution with model physics, but we need to be sure that it works all around the world. And thank you very much. And well, thank you for attending.
Thank you. Yeah, this is excellent talk. And let me compliment ECMWA also for providing all these products for our personal use. My specific question is, I'm from India Met Department. So as you were mentioning about the AI model also, so there is yes, there is improvement, it seems, in the track forecasting of tropical cyclone. But when we come to the intensity, even recent cyclone also, it was not giving a correct indication. Whether the real ECMWA forecast was the right, but the over prediction was there in the AI model. Second part is that with respect to the extreme forecast index of heavy rainfall, so that what you showed, that is giving a good guidance about the intense expected high rainfall. But point is that when we are talking about the individual ensemble members, some of the members are showing very high member, 1 or 2, whether that can be outlier or that is also a maximum probable precipitation. So whether it is possible for ECMWA using the ensemble system and AI, whether to give a product like maximum probable precipitation in 24 hours, whether that is possible. Because when we are I will show in my presentation, we are not able to catch the peak rainfall, what is expected during many of the mesoscale event, even the large scale event also. So that ensemble members, if you say one, whether it is outlier, or is there any possibility that you combine all the ensemble members to derive a maximum probable precipitation in 24 hours?
Okay, yeah, that is an interesting point because, well, the problem with the precipitation is that always the resolution, we are calculating the mean of the precipitation in the grid box, which is 9 kilometers. So the mean, it doesn't detect always what is happening inside of the grid box, all the details. So some, with the perturbations of the ensemble members, some of them randomly sometimes detect this maximum value, sometimes not. We can produce a product with the maximum value detected. You can also go directly with, I think that you have the percentiles of the ensembles, and you can go to directly and plot the 95 percentile or 99 percentile and detect that. And also just to say that in the AIFS, we are producing also an ensemble system. So with the artificial intelligence, they are calculating the uncertainty quantification, and they will produce that. So maybe a combination of both can help also to detect better that. I don't know if I answered your question, but.
I'll just have one quick question. I mean,
yeah, we can discuss during the coffee break if you want as well.
yeah. So did you, in the combination where you're using the AI-based systems, has there been anything that has helped improve the dynamical physics-based models, or has there been anything from the physics-based model which is then getting imported into the improvement of the database model?
Yeah. So now what we are doing is to try to use the AIFS forecast to use like a diagnostic tool for our forecast, because we didn't see that it predicts much better in terms of the parameter prediction, but we saw that the predictability increased in some of the aspects. So we are trying to understand this predictability, where it comes from, and especially to diagnose in which areas it's happening, to really go and improve that in our IFS. So this is I think that we just started this month to apply this type of diagnostic. So, but we will do much more.
Thank you. I think Krishnan has a comment that they will be watching for the lightning forecast.
Yes.
There's one comment there, question there. And one, okay. Let's start from there. And okay, you already have it. Please go ahead.
Yeah, thank you for the very nice talk. So I just have the fascinating about the digital twins, the Destiny E project from the ECMWF. So I'm just wondering how this is going to, suppose like a 4.5 kilometer, when you bring down to the 1 kilometer resolution to the complete globe. So still, whatever the models are existing, it is not adequate to have the complete, means the model physics to every part of the region. And so how it's going to mitigate this, this Destiny E? So its backbone is really only on the machine learning and deep learning programs, or else how it's going to mitigate this physics with this resolutions, bring downscale?
Yeah, well, for now, in terms of improving or increasing the resolution in Destination Earth, we are going in parallel with the IFS. So all the IFS configuration will be the configuration of Destination Earth. So for example, the 49R1 cycle will be implemented, that it will be implemented as well in 4.4 kilometers. But we are aware of these deficiencies when you move to higher resolution. So in the future, we don't discard that we have to adapt and modify the model physics in the 4.4 kilometers, independently from the IFS. But this is an open question. As you say, it depends how degrades, how the degradation of the forecast happened with the resolution.
Hello. Take one last one.
Yeah, sorry.
Thank you for a nice talk and to have the machine learning things. How many algorithms did you use for the machine learning to train your data? Did you compared with all the algorithms, and which one is giving a good accuracy?
I honestly, I'm not sure how they designed it. They designed it just in the last 8 months. So they developed this forecast really fast. I know that they tested different aspects, but this, yeah, I don't know exactly how it was developed. I know that in this paper, they discuss some of the aspects, so you can access and have a look. But yeah, I think that they first tested how to use with RFI, then they tested how to introduce the IFS. But in terms of the algorithms, I know that they wanted as much flexibility as possible in terms of the grid, how to assimilate different grid resolution.
Did you know the dependency, which one they have put, how many members to train this machine?
We have only one member, it's deterministic for now. but we're creating some kind of ensemble artificially as well, and giving some uncertainty quantification. So there will be soon an open.
I think you should have the numbers of members more to train the machine, and you will get a good accuracy with that.
I think that there will be 51 ensemble members, but it will be something useful to compare with the other.
Let's continue the conversation
Yeah.
over coffee. Thank you very much.
Thank
Thank
you.
you again. Appreciate it.
Thank you, Dr. Edelweiss, for this interesting talk. Now it's time to move to the last talk of this session, Dr. Pankaj Kumar from ISAR Bhopal.
So it's working. Thank you. So good morning, and thank you, organizers, for giving me this opportunity to speak here. So what I will be speaking here is talking about a little bit on hybrid modeling. So what we are trying right now, and obviously this data-driven techniques are okay. Let's press this. So these data-driven techniques are becoming more and more interesting, and a lot of people are putting effort on this. There's a previous talk also talked about this. Tim Palmer also said something about these things that probably we are going in a direction where we will be using hybrid tools, not only the physical models, but also the hybrid tools, which will be a little bit more useful. And let me acknowledge my group, because this is work largely done by a couple of my PhD students, and what we are trying is to not only look into the climate models, but also to downscale the information a little bit more realistically. This is what I will cover. And why we are doing is basically I work on the climate scale. And what we know that this is what we are trying to have this by the end of this century. But what reality is that already in this period of time, we already have 1.59 degrees centigrade. GHG are the main drivers. They are able to speak about the science of climate change. But they do show limitations when we are really looking forward to it, because we really are talking about the urban extremes and all the extremes which are really bothering us, and we are trying to address those things. And there's another Copernicus data where you can really look around those things, and this always is changing. 2-3 years before it was 2040, we will cross this number. Now, last year it was 34. Now it is July 33. That's what the speed, if the speed we are walking through, we will get in those areas. And this warming is obviously unprecedented has been already discussed. These plots already I'm just putting in to bring it into my talk context. And the observation and this warming is really significant in these things. And when we see this, obviously is integrated with the anthropogenic forcings, and then these anthropogenic forcings lead to this warming trend, and leading to extremes. The return period frequency under different warming conditions, they are really increasing. So we, especially in our part also, like cyclones, where we were not having cyclones in the Bay of Bengal, Arabian Sea, we are now getting those things. Urban flooding, especially it was flash flood and all, where this scenarios for the mountainous region and all, but all our cities are very frequently we are getting the flash floods and all those things. So this and obviously extreme heat waves, which we have in the last week as well, when there was election. First time I heard in my life that the people who are doing the election duty, they died within doing this thing during the daytime itself, 5 to 7 people. So it's really becoming very, very challenging. And to address this at that scale is again a challenge for all the system models which we have around. One more example which we can take is that this coastal areas is already predicted to have very high level sea level rise. By the end of this century, if we talk about there's a huge population, a lot of economic activities, and the areas where this extremes are supposed to be there, and then it's difficult to talk about those extremes with respect to the models which we have around. And obviously the emissions and all very common figure, but the point which I wanted to bring here is that the vulnerable people lives in this part of world where the extremes are becoming very, very high. And when these extremes becomes integrated with all these non-climatic factors, unequal access to resources, poverty, and all those things, the impact really becomes very, very strong. So before I go to the slide, which largely what we do, we use some models which we are using at our place. So we are not doing Earth system modeling, but we are doing regional Earth system modeling. And there we have a model which is coupled to our Codex area. And this is the atmospheric model REMO, which we coupled here. And then we have a full hydrological discharge model, which we run at the global scale. And then we have the full MPIOM global model, ocean model, which we are running at a very varied resolution up to 5 kilometers over the coastal areas and 20, 25 kilometers over the oceans, and the full BGC and all those things. We're doing a lot of simulations at very high resolution. Even with this, the high resolution things, and also I'm selling this product by saying that even while doing this with the ERA interim force simulations, the coupled simulations with this 0.22 and 0.11, they even showed better results than the forcing thing. So having said this, also the point is that when I look into the biases, not the biases, biases in the extreme precipitation. So the lower panels are the model I was just talking about. These are other regional models which are available from the Codex community, and then RCA, REXIM, and all those things. Everywhere we can see that the precipitation, the biases in the precipitation extremes, higher precipitation extremes, are quite visible. However, it has reduced visibly in these settings where the rainfall obviously is very less in these areas, but also you see that it's visible. The biases are noticeable. Biases are there. Now with the availability of the data-driven, this climate data has come into the big data science now, because I will not say science, big data category. We are able now because of the CMF5, CMF6, satellites, all those products, we can use this information from this data and try to mimic something there. And then with these information, we try to data from knowledge, we should try to use this for, especially for our extreme things or other things, which I will be talking in a minute. So with this AI, ML, and these things have proven their potential in other disciplines long back, and very significantly. And sooner or later, we will also have or we will be. So obviously there are the algorithms which are very well developed and are showing that they are able to capture such scale features. And this is what we say that, and even the pattern recognition things, if we try to implement this in our field, we have a lot of spatial and temporal data sets. So these data sets can learn instead of looking into the PC and UF only. If we can implement these methods and try to identify the more signals which really the statistical method cannot, can be very useful for prediction and also for the projections. Image resolution obviously is one thing, and then which is where we can use it for downscaling kind of products with coarse resolution to high resolution image and all those things. They are very well existing algorithms, can be implemented in our part of world also, to coarse resolution to high resolution. And then there's a walking things also, which we can track those things. So these forecasting things, speech things, the speech algorithms and all, where the language and all, onset and all can be thought of doing with these kind of technologies. There's a handful set of algorithms around which people are right now working to address this to integrate these algorithms in our sector. Obviously, artificial intelligence is the big box under which of machine learning, and then the more neurons, more deep learning, and more deep processes where we trained it. Obviously, it is also very computational resource and incentive if we go in this area. Usually, when we talk about machine learning, where we have something input and we try to provide some base thing, which feature extraction, and then this neurals, ANN networks, they work here and we get the output. Whereas in the adversarial or deep learning things, everything is done by the neurons, where the control is very limited. Here we have a bit more control. So largely in the deep neural networks, the most useful thing is the CNN part, convolutional neural network parts, where the image data and the video processing things can be more useful. This kind of data we have around to look at it. And there was recently one paper by Sun et al. in 2022, where they have already shown that where these machine learning algorithms can be used for deep learning or in hydrology or atmosphere or geosphere. Means technically it can be implemented almost all the sectors which we are talking about, all the system areas. So if we talk about the different hybridization or hybrid tool, which we can maybe looking around, or maybe the team was also saying, and the ECMWF is also working, and a lot of groups across the globe are working on this area. So in different phases of our model simulations, this AI/ML can be utilized to improve our prediction or projections. So especially our standard practice of any model process steps chain for modeling is initializations or data assimilation, then model physics and dynamics, and then the post-processing. These are the standard process of doing all those things. So even if when we are talking about initializations or assimilation part, here itself, we can also integrate the better machine learning retrieval algorithms, fast-forward models, ML-based observation operators for data assimilation, and also here itself we can improve our forcing, I would say. In the dynamics and physics, this is the main part where most of the things or a lot of work can be done, and I'm sure within the next 3 to 5 years, things will be visible in this part as well, because AI obviously is a data-driven technology, and it's very difficult to tell what is going inside the box. We really don't know. But now people have started working on PIML kind of things. So physics and informed machine learning, can we decode those boxes and talk a little bit on those lines? So so if in these models, if we can talk about a little bit about can we use some machine learning algorithm and train it using maybe some 1 kilometer scale model and try to mimic the radiation scheme, which is more or less universal. Obviously, the one problem with these technologies that if it works for one case and then another case it does not. So if we can generate some mimic the radiation scheme with ML, and then these and generate one emulators, and put these emulators into our physics part, then this will significantly reduce the computational time which we are talking about as an elephant and the ant. So this will really will make a lot of changes. Similarly, microphysics, there are n number of parameterizations which can be handled. Obviously, physics can be faster, and in model itself we have so many constants. If we just even control those constants also and put them back into in a much more correct way, or correct is a very within quotes, this definitely will improve the simulations as well the speed. And again, obviously, the cloud physics and all, or even the convective parameterization, they all consumes a lot of computational time which goes there. Obviously, it's a very optimistic thing, but I'm quite sure a lot of people are working around, and very soon we will be seeing these kind of tools coming into the market. Post-processing, obviously, we do a lot of, because all our results are deep learning downscaling processes, or another thing is that RCMs, regional modeling, that people were saying that this will take over RCMs, regional modeling community, because obviously if if you're able to downscale those information almost to a kilometer scale or even 500-meter scale, then and with some logical reasoning, a lot of things will be then compromised in for that community. Bias correction, usually when a lot of people do bias correction, we don't encourage to do bias corrections, because you do bias correction with the existing observational data sets, it's not credibility for the future and all. But when you're doing using these kind of algorithms, those comments also will be handled to some extent. So model output statistics, which is also a very important thing which we do. Nonlinear machine learning algorithms can handle these things, for especially when we are talking about the ensembling the averages and all those plots which we make for assessment and all. I will just show one case study which we are doing right now. We are trying to downscale IMD 1 degree data, low resolution, to IMD high resolution 0.5 degree using this data-driven techniques. So the point which is why it is important, because we are, as I said, it is extremes is very difficult to capture. Most of the models, when we do, they either don't look into these outliers, or just they smoothen those things, and it's largely not captured by these things because of the distribution which we have around. So what we are using, we're using right now, the one I'm just presenting is the GAN. So we have supervised training and adversarial training. This is much more controlled system. It is a little bit uncontrolled system. So here 2 algorithms are running here. One is running, and then we are showing the high resolution image. It generates high resolution image, and then we show the target image and then look into the errors, and then it generates the weights and biases. Here it's little bit more complicated, more computational time is needed here. So we show the discriminator, the targeted image, and then they try to see that whether this both the images are, how much error is coming, the minimum when the errors is almost negligible, then we are almost done. So I skip this. So this is the data which we have used it. And for monsoon season, I will show some results here. We did some experiments. So with these experiments, I will just talk about the results here. So when we did the experiments, so this is the standards bias correction spatial disaggregation methods, which a lot of people do, and we get a lot of good correlation with the data. So, and here it is more into the deep learning models, it is more machine learning models, and we see good statistics here, but less when we are going into more complicated systems. So, just to highlight this, these things, I am just showing you the extremes. These are the extremes conditions defined by the IMD, and these are the VHR and LHR. We are going here, it is more higher extreme values we are talking about. So if we see, we have seen that the BCSD was showing better correlation, and RMSE and statistic-wise it was better. But when you come to the extremes, this is the blue color. If you see around, it goes there, and then when it comes to it totally fails to capture those things. Largely, the one simulation which we did was better able to capture the biases relatively less. So just to second last slide, is this. This is the IMD high resolution image, and this is the simulation where the correlation is really almost same as this one. But here we see more homogeneous, more picture, where here the pixels are much better resolved in these kind of approaches, and obviously the subgrid scale, the processes are better represented in these processes, even though the correlations are poor, but these are relatively better signals, and obviously we need more time to train those things. There are some more events, I will not go there, and then in the last, I would say that the high efficient image super resolution techniques is adopted and applied for downscaling graded rainfall data over India. And it is basically trained over VGG19 architecture, which is already available. That also need to be trained if we really want to improve there also. That was also one of the reasons for a little bit lower correlations. And also one point, to GAN training strategy is more powerful than the supervised learning strategy in the preserving minute details. Also, we also need to see that whether we go more deep or not, because you may get a better results at first hand also, not to going too much. A lot of work is going on in this direction. So people are doing these things very frequently. The more, I think the maximum work is going in this direction, where the physics inform machine learning models we are trying to develop, where not only the like Navier-Stokes equations or orography or static fields, orography, land sea mass, temperature, humidity, all those things we can integrate and try to talk about those things. And obviously, if we can do those things, so ESM and RESM's feature projections can also be downscaled and looked around those things. Thank you very much. I'm sorry if I exceeded the time.
Thank you. I think we might have time for a question or two. Yeah, there's one there.
Thank you for the talk. It's Yashraj from IIT Hyderabad. I'm also interested in ML applications. I was wondering, you had 3 boxes. The middle one was about the model. I was interested in knowing, are there any explainability tools or interpretability tools for explaining how or why the model behaves the way it behaves? Thank you.
So you're talking about the data-driven model or the physical models, which I was talking about?
Yeah, the physical models.
Physical model, obviously, we have, they are based on the physics and the parameterization which we develop around. So they all have the proper reasoning to implement those subroutines or parameterization into the systems. I was talking about that, can we mimic those things into and replace those things? Because they take a lot of computational time. So if you're running cloud physics, it takes, I don't know how much percentage I should say, but it takes a lot of time. If you're running convection scheme, they take a lot of time. So can we mimic these things? It's all is theory, right? I tell you practically. So coming these things in future, in practical, maybe we are working very fast, maybe 3-5 years, we are seeing these things, but definitely something will come out.
Indeed, something should be evolving. Do we have any other question? And from my co-chair, do you have any question? Okay. Well, with that, I think we can end this session. Thank you very much for fascinating talks, and we'll hope to have a break.
Thank you, Dr. Niyogi and Dr. Ratna, for chairing the session. I request Dr. Niyogi to present the mementos to the speakers. Please come up on the stage. I request Dr. Vijay to please come on the stage. Dr. Estebalis Gascon. Dr. Pankaj Kumar. I request Dr. Mukhopadhyay to come on the stage to present the memento to the chair. So please stay back. That's all.
Yeah. You can give me half a minute.
Yes. Thanks, Chair.
I request Dr. Satyaban Ratna, co-chair of the session, to please come on the stage. Thank you, sir. We just have a few short announcements. Posters and short audio-video presentations are available on the STIPMEX webpage, and photos of the sessions are also available in the photo gallery. Please do visit the website. Today evening at 7 p.m., we have a cultural program showcasing Indian art forms. Do stay back and enjoy the program. Also, please note that tomorrow we are starting the session at 9 a.m., requesting everyone to be present before that. We'll now break for tea. We'll take a quick break and we'll resume at 11:50.
Welcome everyone. Now we start our next session on extreme weather prediction. I invite Dr. A.K. Shahai to chair the session and Dr. Jay Kumar to co-chair the session, and the deputy is Dr. Radhika Kanase.
Radhika is here. Radhika. Okay. So we are already, we have spilled over the time, and it is very tight schedule, cultural program, and all those things are fixed. So I will request 3 speakers who are before lunch to, if they wish, they can finish within 20 minutes so that we can get lunch on time, and then after that we will start. So thank you, Jayakumar.
So now I invite Dr. Yang from Ensemble. The topic about the development and evaluation of NOAA UFS system atmospheric model physics component for the Ensemble operation forecast applications. So, Dr. Yang.
Okay, I get started. Hope you all enjoyed the tea break. I try to be as fast as I can. So give you time for still some time for lunch. Otherwise, you have to skip the lunch. So I give a brief review of the physics development aimed for improve the unified forecast system, extreme weather forecast. At the first, like to thank all my staff and also collaborators for their contribution to my talk. Well, in this morning, our first speaker, Dr. Vijay Talpakanda, already gave a very nice review of the UFS, and that's the foundation for my talk. So probably I can save some time here. So this is a community effort. It's not just by one group or one person. You can see there's a long list of collaborators from our NAA's, NOAA labs, also the wider community. On this slide, which showed the current status of our operational model, we are trying to use the unified system as an infrastructure to replace many of the, if not all of the current operational systems to speed up the transition to operation and also reduce the cost of maintenance. So this is the schematic showing the components of the coupled or unified forecast system. No need to repeat there. So the UFS, which I said earlier in the morning, can be tailored for different applications. Right now, for the regional, we have this rapid refresh forecast system, a regional model, and the inline air quality forecast system and hurricane forecast system. On the global side, we have the Ensemble forecast system and the global forecast system, the medium range deterministic, and we are working towards build the seasonal forecast system. The system actually has also been used for deep atmosphere applications. We got whole atmosphere models for space weather forecast one. So my focus today will be on the physics development for UFS application. The guiding principle for physics development is to reduce model systematic biases, improve forecast of extreme weather and climate events, and maximize model prediction scales. Another effort we are trying to make is to unify the physics schemes or parameterizations for all applications across different spatial and temporal scales to speed up the R2 transition of physics innovation and also reduce the cost of operational system maintenance. This slide shows the current status of the physics parameterizations used for different applications. Starting from our global model GFS version 17 and GIFS version 13. The basic GFS and GIFS use all the same configuration, except the GIFS has the perturbation and also ensemble members running at a lower resolution. You can see on this slide, everything in black color are unified among the applications, and those are in pink colors are still somewhat different among the applications. One of the major reasons for the RFS is regional model and have so many different applications. We started the RFS development from the HER model. So it has the first implementation of RFS in trying to maintain the continuity of the HER system. But we have the plan to replace many of the physics packages shown here for the RFS and with other physics transitions to unify across all the applications. One example will be the land-surface model. Currently, the RFS is using the rock land-surface model. We are working towards using the NOAA MP in the future as well. So how the physics development has been evolved in the past few years since we started the UFS development, which I mentioned earlier. So we started from different prototypes. You can say this will be the picture, and almost all the physics components parameterization have been either replaced with new parameterization or updated for better performance. Notably, there are a few, and we have changed for the land-surface model, replaced the NOAA land-surface model with NOAA MP and the microphysics, switched from GFDR single moment microphysics to double moment Thompson microphysics. And also for ground drag transition, we made many changes. So we started from the low resolution, so-called prototypes. This P at the 13 kilometer resolution. Now we are working towards on the so-called high resolution. The test evaluation at the 13 kilometer. Our target for GFS version 17 is 9 kilometer global model. So here is an example on what the physics we have been changed, prepared for the GFS version 17, GFS version 13 implementation. Many of the in blue color also have been already in operation, being used for the first UFS-based hurricane forecast model called HAFS. It's already in operation. I mentioned earlier, we replaced the GFDR single moment microphysics with the Thompson double moment microphysics. I have more details next slide. We replaced the NOAA land-surface model with NOAA MP, and with introduced a new small-scale quantitative wave drag transition, and also the TOFD called turbulent orographic form drag. We updated the convection with probabilistic convection franking area instead of prescribed convection area. Introduced new stochastic physics in the ocean, land surface, and the atmosphere. Implement the new positive definite tracer activation scheme in both the convection and PPL scheme to prevent the model from producing negative tracers. And the new capability of coupling between air source and the physics, so allow us to develop the air source cloud radiation interaction. Also update the new land, ocean, lake masks, and the new ice climatology and the surface composite franking grid. A little more detail about the Thompson microphysics. It has been known Thompson microphysics very popular in the regional model, has been used in OFF. But after we first put in the global model, first thing we found is computational instability because the global model has much longer time step. So we introduced the so-called semi-Lagrangian limitation scheme to make the model stable, applied to global and run. And also we improved the simulation of ice cloud in the tropics. So as I'll explain why we have to improve the ice cloud in the tropics in next slide. But first I want to mention one effort we made to simulate the mixed phase cloud. As we know, the super cooled cloud water is very important for aviation application. That's also one severe weather product we provide to our customers. The operational GFs, current operational GFs cannot simulate the super cooled cloud water, and we are using a single moment GFDR microphysics scheme. After we implement the Thompson, switch to the Thompson microphysics scheme, we are able to simulate the supercooled cloud water, so make a better aviation products. The difference is observed the supercooled cloud water. Also IFS is also one of the nice in the picture. So it also has the capability to simulate the supercooled cloud water. But after we first put into the Thompson microphysics, we found in the global application, there's problem in the tropics, the energy balance. We can see there's some numbers of the total number of hydrometers. So compared to also the IFAS and GFS version 17 new model, and also version 16 GFS microphysics, noticeably the Thompson microphysics has much less ice and not more slow. So we had to discuss the original developers and come up with some solutions by tuning of this relative humidity for an ice formation, supersaturation criteria. We were able to balance the energy in the tropics. This is very important for seasonal, sub-seasonal forecast. So this for the quantitative wave parameterization, and now it's not actually this is 5 parameterizations. It's not only one. It's not one parameterization for quantitative wave, and now we included the large scale work-with quantitative drag and the low-level flow blocking, and non-stationary quantitative drag and small scale quantitative drag and the turbulent work form drag. This field difference listed there. They each have their own physical mechanisms behind these parameterizations. So after this implementation of this GW package, and we are now able to simulate the QPO quite well. So what showed here is the GFS version 15. We did not have the non-stationary quantitative drag parameterization. It does not capture the QPO at all. And in version 16, after we extended the model top from 64 layer to 127 layer, also included a preliminary version of the non-stationary quantitative drag parameterization. We were able to simulate somewhat like a QPO, but the period is 1 year, and also intensity is not high enough. So we keep improve this with our latest implementation. We are very satisfied with the performance of the model, and we tested in different resolutions. Like earlier, we just showed for 96, 192, or the shoot here is the 384, that 25 kilometer resolution, and the QPO magnitude and phase matched and the observation quite well. Another feature started we observed on our GFS version 17 is the water vapor in the stratosphere. What plotted here is the monthly mean water vapor. This is the latitude. Here is the vertical layers. You can see the model captured the variation of the water vapor, seasonal variation of the water vapor very well. And before this version, GFS version 16, we couldn't capture the variation of the water vapor. One major change we made in the version 16 was included a parameterized methane mechanism, photo dissociation of the methane to produce water vapor. We have now started to check carefully how the water vapor have been changed in version 17, and that's what well, hopefully that will be still keep this nice feature. So the second speaker, Professor Emmanuel, talked extensively about the CAPE. I don't need to emphasize the importance of the CAPE anymore, but we do have some problems with the CAPE in the GFS version 16 implementation, and we had to sign a memo with the NOAA's Storm Prediction Center saying we will improve the CAPE in next version, GFS version 17, otherwise our implementation will be in danger. So you can see this CAPE, this GFS version 17, the latest prototype. We improved many of the physics, but unfortunately the CAPE actually become even a little bit worse than compared to version 16. And both are worse than the ramp, so-called ramp analysis. We have made many efforts to try to understand the cause and also improve it. One of the improvement found is by enhance the PPR or reduce the PPR mixing. You can say here the schematics. This reason if we have used the TKEDM PPR is full local non-mixing, and this dark green line is the with no local mixing. So by tuning of this PPR entrainment, we get a profile in between. By reducing the mixing, we are able to improve the cape. And also for the parameterization, we made this mixing entrainment function, both the vegetation fraction area and also surface roughness length. So this is a picture showing the improvement in the cape forecast. This over the central US and east region, you can say the improvement is about 300 to 400 units. Some areas reach up to 500 units, and also we improved the water vapor near the surface. So the target was near surface, but you look at the vertical profile and also the temperature, and this green line is the latest. The black line is GIF version 16, the red is the control, and you can see we were able to reduce the deficit of near surface water vapor and also improve the cape. But the cape is a complicated problem, like the Professor Emmanuel mentioned. Sometimes you can pump a lot of water, increase the latent heat flux. It will sometimes improve the cape, but you take the other parameters. Also, by increase the latent heat, you reduce the surface 2-meter temperature. That's also another problem. Recently, we have been looking on also other causes. One of the causes we think is because actually the emissivity in the tunnel's waste part is too low in the nighttime. The cooling is not enough, so the contrast between the east and the west is not enough, and then the Gulf Stream, the jet is too weak, and you do not have enough moisture transport from the Gulf to the central US, and the Cape is weaker. So that's in the model, it's very difficult to improve the Cape, and with also so many feedback mechanisms. Well, now everybody is talking about machine learning. So why do we, maybe we can skip all the physics different to go directly to the machine learning. So we made this attempt. You can see with GIF version 17, after many of the updates we made, still compared to the ramp, it's weaker, the cape. This is validation data, and we attempted to use the machine learning using GFS version 17 data and applied to GFS version 17. You can see the cape matched the ramp analysis very well. I think this is one part of the area we can use to improve the cape prediction in the operational system. This is a geographical distribution you can see here. And this is ramp analysis. These are control run, the certain given model with the machine learning. We could definitely improve the cape, but still weaker than observed. One of the problems we found when we couple the going from the uncoupled to fully coupled air system model is the hurricane intensity. You can see GFS version 16. And if we run the version 17, still uncoupled with prescribed ST, the hurricane intensity is almost the same as version 16, but the fully coupled has much weaker hurricane intensity. What happened is in the coupling, you have a much less latent sensitive heat fluxes. So we have been trying to work on improve this hurricane intensity, made some changes. One is by introduce the wind shear effect in the convection and the PBR scheme. Seems this single change of the physics very effective, and the results shown here for 2020. The Eastern Pacific, Atlantic, and the Western Pacific, you can see the flank line is GFS version 16, and the red line is the control coupled model. And by introducing this wind shear effect, we are able to improve the hurricane intensity by a certain degree, but still not enough. There's still an area of active research and development for us to improve the coupled model. Okay, I talked a little bit about the improve the MJO and the monsoon forecast in our fully coupled GFS version 17. Which already showed earlier in the low resolution model the 25 and the gives this is what I showed here is a certain kilometer deterministic forecast system. You can say the MJO be improved in both the winter and summer. The improvement in the summer is more advanced than in the winter time. There are many physics changes. We did some sensitivity tests, and one of the major reasons for this improvement of the MJO is because of the introduction of the fractional convective area in our convection scheme. Look into the more details, the MJO improvement, the bias, and the amplitude and the phase. You can see GFS version 16 has overestimates the amplitude, and also the phase error is very large. The two lines, colored and red and green, there are two versions of the version 17 fully coupled. You can see definitely reduced the bias in both amplitude and also in the phase, although they are not perfect. Look into detail why the MGS improved. So if you look at each component or some of the input parameters used for the keep the MGO calculation, you can say definitely the 200 millibar and wind and 550 millibar wind and error all have been improved. The RMS has been reduced in this hydro model for both winter and summer. I skipped this, the monsoon index. We have improvement for the East Asia monsoon, but it is not improved much in the North American monsoon region. Okay, the Q1. I still want to talk a little bit about our work on the regional RFS rapid research forecast system. It has been known it overpredict the heavy precipitation and also radar reflectivity in the earlier version without the parameterized convection. So one of the efforts we made is to include the convection scheme in a 3 kilometer region model. This observation radar reflectivity, this control result, and then by including two versions of different convection scheme, they have some same origin, but it deals in different paths. You can see that both can reduce the intensity of the overestimation of this convection. And now this both of the scheme now be including different ensemble members of the RFS to improve the precipitation forecast and also reflectivity. This slide shows the overall time evolution with the forecast are how at different the DBZ the radar reflectivity bias has been reduced. You can see the sense has reduced even more than the GF scheme for light precipitation, but for heavy precipitation, they are equally good. And the blue line was the original without the parameterized convection. I skip this for the hurricane part. We're still improving the hurricane. For 5 or 30 seconds about the unification of the physics, and we have made a lot of effort to try to unify the physics across different applications. We made some. It has been successful in some aspects, but we still have a lot of challenges. One of the major reasons of many of the physics was development for the particular application. Now we want to apply for different temporal and spatial scale. We have to make it the scale well. Not all scheme scale well up to date, and there's not more work to be done. With that, I end there.
Thank you, Yang. We can have 1 or 2 questions. No, okay.
A nice presentation, first of all. So I just want to, you have shown one convective scheme with respect to radar reflectivity, right? Can you go to that slide? Yeah, this one. So in this, the first one and the second one, the second one is somewhat, the left one is the observation, right?
Yes, this one's observation, this one's the control run without parameterized convection.
Okay, so it is in both the cases we are not finding it is matching exactly, means more or less similar pattern with observation. Only for the control run it is somewhat is there, but yeah, it is not matching except for the higher reflectivity cases. We do not find so much matching.
So you have that point. After including the parameter convection, the model tends to sometimes miss the convection. That's now has actually been a problem. But overall, the effort is really, if you compare to this, the model usually has a trouble to really match the observation. But if you just compare these three slides, you can see the overestimation of the convection has been really reduced. That was a concern for the forecasters.
Okay, thank you, Dr. Ang. Now we will go for the second talk because we have less time.
So for next talk, Dr. Takaya from JMA. Title of talk is Forecasting Severe Local Storms with the Advanced DA and Ensemble Beyond Weather Forecast. Please, sir.
Last one.
Okay, so I'm Takuya Kawabata from MRI JMA. So I come here to celebrate the long history of Indian Met Service of 100 years, so long history. So I will talk about the forecasting severe local storms with advanced data simulation ensembles beyond weather forecast. So to celebrate the long history, I will start my talk with achievement of current NWP for historical disaster in Japan in 1959. And then I will talk about the perspective of the severe local storm, how to predict and how to get useful information from that. So I will introduce the Typhoon Vera attacked in 1959, 65 years ago. This typhoon was actually a super typhoon, and this typhoon induced the big storm surge of 389 centimeters tide level, and we lost more than 5,000 people's life. So this is the picture of the Typhoon Vera. So you can see the storm surge attacked to the Nagoya city. This is actually the JMA's local observatory in Nagoya. So this map shows the water coverage or duration. So this is longer than 1 month, this area. And this is more than 80 days. I'm sorry. So due to such huge storm surge, we lost more than 5,000 people's life. So how to deal with the operational forecast of JMA in 1959. This is the electrical copy of the JMA's forecast. We have two lines from the empirical method, 1, 2, and the forecaster draw this line for the direction of typhoon. And we have 3 numerical models here. So this map shows actually the multi-model ensemble in 1959. So they issued the, oh, I forgot to mention about that. JMA is actually the third entropy center in the world, followed by USA and Sweden. This is a big computer for that. And they only issued the forecast on the typhoon direction for 24 hours. This is all of forecast in 65 years ago. So nowadays we have a numerical weather prediction system. We started with the JMA's global reanalysis, JLGOGO. The horizontal resolution is 60 kilometers. And then we conducted the downscaling with the non-hydrostatic model at the horizontal resolution of 20 kilometers. But we got the very weak typhoon in simulated. So we decided to the next step to use the full nonlinear numerical weather prediction system for regional. So this is the operational 4D at that time. So we assimilated drone sonde observation by US Air Force in the eye of typhoon, and in addition to the conventional data. So we get the strong typhoon here. This is Typhoon Bella in 1959. So we succeeded to predict the Typhoon Bella weather forecast like this. Left side is the pseudo satellite images, IR image. Right hand side is the radar images, pseudo one. Actually, the first JMA stationary satellite was launched in 1979. And the first testament radar is on top of the Mount Fuji, started operation in 1964, 5 years later. So we have the high ability to predict track and intensity of typhoons and weather by using advanced entropy systems and high performance computing. So from this weather forecasting, we would like to predict local storms. So this is the orographic updraft, and this is the convergence by fronts. These are the large scale forcing. This is the main source of weather. But my target is like this, with very strong small scale forcing. This is local storms. So local storm has small scale in space and large variation in time. I have to say it's really hard to predict. And also, it's really hard to observe the local storms. We need water vapor in the lower troposphere and wind convergence for the initiation of the local storms. And the initiation, from the initiation, the cumulus drops into the cumulonimbus just in 10 minutes. And its horizontal resolution is small, 10 kilometers. So we can observe such things by weather radar, and we can get the wind surrounding the cumulonimbus by reflecting the insect. And also we have the water vapor information from GNSS satellite, and Doppler and wind water vapor radars here, and satellites. So for successful prediction of severe local storms, we need to observe environmental fields, water vapor, wind, temperature, surrounding the storms. And also we need water substances observation inside the storm. So to utilize this remote sensing data, we need data assimilation, advanced data assimilation techniques. So I will introduce two approaches for predicting severe local storms. The first one is deterministic one. This is a traditional one. So we want to predict a quantitative prediction, detecting when and where and how much rain occurs. But it is limited within from 3 to 5 hours due to chaotic behavior of the atmosphere. And the second one is probabilistic prediction using ensemble techniques. We need precise probability with less sampling errors. This is applicable for longer than 24 hours. So to make a precise deterministic forecast, we need advanced data assimilation system. I will introduce my system, NHM4D. The forward model is JMNHM for non-full physics with the double moment microphysics. The adjoint model is dynamic core and cloud microphysical processes. The horizontal resolution is 2 and 0.5 kilometers. And then we can assimilate the radial velocity by Doppler radar, radar reflectivity, and polarimetric parameters like KDP and ZDR, and GNSS information. This is the SWAN total delay, and Doppler wind radar data, in addition to the traditional conventional data. So this is the example of the predicting the linear MCS. Left-hand side is the radar data, right-hand side is the assimilating result of reflectivity and radial velocity and precipitable water vapor derived by GNSS satellites. So you can see the very good agreement between them. And the second example is predicting the cumulonimbus, assimilating the Doppler radial velocity and precipitable water vapor. You can see the initiation of convection in the focus result, but no significant echoes in the observation here. And these weak echoes are reflected by insects. So I got the wind field from the insect. So this initiation developed into the cumulonimbus like here. So this is actually the first study to predict an isolated cumulonimbus from the initiation to the end. This is the verification using the rain gauge, surface rain gauge, 10 minutes rainfall amount. So you can see the good agreement from the initiation to the end. So this is I will move on to the probabilistic forecast using ensemble technique. So I conducted large ensemble for less sampling errors. So this is the 25 ensembles multiplied by 40 ensemble. This is actually the 1,000 ensemble predictions for linear MCSs initialized by ensemble Kalman filter techniques. The horizontal resolution is 2 kilometers. You may think all of linear MCSs in the model are the same. So I will enlarge some of them like this. So you can see the differences in this. But it is impossible to see each of them in detail. So we put all the information into one field to see the probability over 20 millimeters per hour. So this is result. This is a weather observation for 6 hours. This is a deterministic prediction started with ensemble mean field. And the last one is probability with 1,000 ensemble members. You can see the long-lasting localized rain with more than 80% reliability. This is the power of ensemble, one large ensemble. So we want to predict more localized, more smaller prediction, like cumulonimbus itself. We need a particle filter with full nonlinear process and full non-Gaussian PDF. So this is NHM RPF. So the model is also the JM-NHM. And the observation operator is the same with the NHM4D. So we implemented the adaptive R estimator into the NHM RPF. So this is the ensemble mean of the assimilating nature run observations. So you can see the cumulonimbus initiation in the particle filter result, but no initiation in the no DA experiment. So this convection developed into the cumulonimbus after 90 minutes. From the probability perspective, you can see the mostly Gaussian distribution in these variables like potential temperature, water vapor, relative humidity, and updraft at the initial condition. But the variables related to water substances, this is cloud water, and this is rainwater. These variables are concentrated into 0. So because this is before the initiation of the cumulonimbus. So this is full non-Gaussian PDF. So but the convention develops into the cumulonimbus. So you can see the full non-Gaussian PDF in these variables. This is why we need particle filters for severe local cumulonimbus predictions. So I will move on to the last topic of my talk, impact-based forecast. As I shown, we can predict weather and local severe storms. Beyond this, we need to predict hazard itself. This is the impact on people's life. Under collaboration of meteorology, hydrology, oceanography, and so on. We already have good numerical prediction, weather prediction model like this. And we combined hydrological for flooding like this. This is meteorological parts, rain falling, and the water from the rain makes river and groundwater. And we predict such behavior using hydrological model like tank model. And then we can predict the land side flood and inundation like that. And we need oceanographic model for predicting storm surge. So I will show the example of prediction of storm surge for Typhoon Bella 65 years ago. You can see the red color here. This is Nagoya City by passing Typhoon Bella here, red. So this is actually the 3-meter tidal level. So for verification, I will show the comparison between the observation and forecast. You can see the very good agreement of the observation and forecast in time and tidal level. So another thing is the coupling with hydrological model with 1000 ensemble prediction. So I will show the random index. This is the output of our hydrological model. So you can see green, orange line. This is actually the historical maximum of the random index. JMA actually is a calculator for more than 30 years. We define the historical maximum like this. And black line shows the observation of random index. Observation of random index means tank model forced by radar observation. So the dashed line is a deterministic forecast. So this is the grid point of the model, this point. This is a fully flooded building. So this flooding occurred at 6 in the morning. So you can see the deterministic and observation exceeds the record at the exact time. And to see the probability of this record breaking is 40%. So at the end, the probability increased to the 60%. So we can say that we predict the probability of hazard occurrence at the exact time before a half day, 6 hours before. So this is the river basin, and this is hazard area, actual hazard area. Upper panels are probability, and the lower panels are random index of observation. So yellow shaded area indicates the actual flooded area. So you can see the dangerous area come from the south, north to the south. And then we got flooding at 6 in the morning. Black means 40% of dangerous probability. And fully dangerous area here indicated. So the last movie of my talk is this. This is the deterministic linear convective system, and the color shade means the probability of that. And you can see the 80% of the heavy rainfall occurrence. And then I will show the random index like this. So this is the probability of heavy rainfall index. The linear MCS move from the south, north to the south, and the river gets danger in time. And black means more than 40%, as I shown. So let me, I'm sorry. Let me conclude my talk. Towards successful focus on severe local storm beyond weather forecast, we need data simulation and probabilistic prediction and impact-based forecast. So thank you for your attention. This is just advertisement. Thank you.
Thank you, Dr. Yakuya. It's very nice presentation, and I think there will be many questions, but we will take questions and we can discuss during lunch with him. So I will
So now I invite Dr. Paul Davies from UK office. So please, Davies, exploring the mechanism and interactions of extreme weather and large-scale atmospheric process using modern observation with a particular focus on the interactions between tropic and mid-latitude.
Thank you. Good morning, everybody. Chair, I promise my talk won't be as long as the title of my presentation. I will be relatively brief if I can. But my presentation is largely about the application of science. I'm seeing it through the lens of an operational meteorologist, which I'm the chief meteorologist at the Met Office, but also in the context of customers, civil protection, the people we want to serve, and how the fantastic science that we're doing, how that translates into action. So the first thing I want to sort of draw attention to is the kind of period of record-shattering rainfall extremes. This is a period in early September 2023. It was only 10 days, but we had huge impact across the globe, Northern Hemisphere. And just an illustration of this, Storm Daniel, over 1,000 millimeters in 24 hours. Libya floods, which we've already talked about. And each of these storm systems were all connected. And they're all connected in such a way that it's associated with a blocking pattern. And I wrote a paper with Haley Fowler, who's a professor, and I'm a professor at Newcastle University, explaining why we had these extremes. It's in Nature, and it got accepted a month ago, and it's out there. But largely it's around a block pattern. And that block pattern, you can see here, which was during the events of 2021, is often associated with this quasi-resonance amplification block pattern, the Din and Wan CGT pattern, which is well known in the 2005 paper, where we had this period in time, especially in the summer, where the atmosphere just gets locked and gets blocked. This particular example here is the consequences of what happened in 2021 from a fairly active monsoon. I take this graphic from their paper and I superimpose what actually happened during that summer. And you can see here that you have periods of fairly intense windstorms, intense rainfall, intense wildfires, intense heat, all happening at the same time. And it's been a real concern for insurance companies, for the Red Cross, Red Crescent, for civil protection, for United Nations, because managing one event is hard enough, but managing multiple compound events, extreme events, is so much harder. And this is one of the key points I want to get across. I'm trying to work out, are we in a period where the compound extremes and the impact is much greater than the individual hazard impact itself through global warming? My conclusions at the moment is tending towards yes, it is. And that is a growing concern, I think, for society. Another aspect I want to talk about is largely what is causing these extremes, especially I'm focusing on rainfall. So we had a very particularly bad event in the UK during the winter of 2019-2020. That period is very interesting because a lot of evidence that multiple extremes occurred in that period. And for February 2020, we had huge amounts of rain in the UK. And when I ran the global models, the climate models, and compared with observations, you can see here that the actual amount of rain, precipitation anomaly, was way above the Ensemble spread from the climate models. And so my question with the Hadley Centre, and I work very closely with them, is that anomaly well predicted within the climate models? Is there something wrong with our climate models? Is there something we can describe and understand the mechanisms why there was such an extreme based on the climate? And so working with universities in Manchester University and in particular Newcastle University with Haley, we'd be looking at observations. And just from a scaling factor based on the Clapeyron-Clapeyron equation, 1 degree rise leads to 6 to 7% increased bit available moisture, we're able to then verify that based on observations that largely speaking for a daily rainfall, it's following that pattern. However, it breaks down. It breaks down when you start to get into hourly rates. You start to find that classic Clapeyron scaling is no longer applicable. You're starting to see much higher scaling rates of the order of 2 to 3 times. So there's something else going on. It's not just the thermodynamics, but there was a dynamics contribution in the circulation pattern. And what's happening in the convective cells, that's releasing so much more intensity in sub-hourly front-loaded rainfall that we still yet to understand. And then building on that, I wanted to know whether there was something in the large-scale circulation patterns that resulted in that extreme event in the UK. And again, this is another paper. This is largely thanks to Steve Hardiman. I was a co-author to this research. And all these papers are all published. And I wanted to know whether the predictability of that extreme event we saw in the UK could be attributed to what happened in the Indian Ocean. And through that mechanisms and understanding that, we see this is for February 2020. This is cloud liquid water. But look at these atmospheric rivers. This one stretched almost way back into the Eastern Pacific, went right up into the UK. And we saw that last year too, right? You saw the atmospheric rivers coming into Southwest United States, into South America. It happened in the UK again and Northwest Europe. So these atmospheric rivers pumping in huge amount of moisture and heat into the circulation patterns was partly the result of what happened in that particular time. And the Indian Ocean dipole at that time too, which I labeled A, was very anomalous and high. So what we did was we relaxed the sea surface temperature anomaly from the very positive IOD just to run as a sensitivity experiment to see whether it induced a Rossby wave or an explanation of why we saw those extremes. And we did. So you can see this Rossby wave arcing up from Indian Ocean across the Northern Pacific. And then it branched in two patterns here, one going across the Northern Hemisphere, across the UK, and one down towards Africa. And the result of it was a very anomalous low pressure system across Northwest Europe. And you see there's an anomalous high pressure system west of British Columbia. So this was a blocker for any perturbation to the polar vortex, which meant we had a reduction activities for southern stratospheric warming event, along with this low, which resulted in a very strong potential vorticity and polar vortex. So we could explain from this paper that what happened in my country in 2019, 2020 was a result of what happened here in India. And that's significant because it means that we have to look at extremes, not only in the context of local, but in the context of global circulation patterns. And then I've got two more features here, windows of opportunities. I talk about windows of opportunities because there are some occasions when our predictability, especially in the seasonal, is much higher than other parts of activities of time. And there is I think, a misguided guidance really to my meteorologists to say that in the summer there is no predictability in the seasonal prediction. That's not true. There are windows of opportunities when the predictability is higher than sometimes in the winter period. And again, I wrote this, contributed to this paper by Nick Dunstan. I was a co-author. And we're looking at windows of opportunity and using the Pakistan floods of 2022 just to illustrate the fact that there are windows of opportunity. And for Pakistan, some of the models, seasonal models, did have it. And their message and the questions I wanted to ask, was there any physical dynamic understanding of why we had those extreme events in Pakistan? And as a consequence of that, did it have a big impact to the Northern Hemisphere circulation patterns? And the answer is yes. So this is what available to my forecasters. This is a probability. This is a terser probability, precentile terser probabilities of rainfall being anomalous. And from a meteorologist, it's not really shouting at you that it's extreme. It's basically saying that we've got about a 2 in 3 chance of being in the upper third of the rainfall for that summer for the Pakistan region. But perhaps we need to start to look more into the extreme tail of the distribution and start rather than looking at tercels, but looking at upper quintile and upper decile events. So in other words, you're starting to get into the guts of the ensemble system to see whether there's any extreme signals within that ensemble system. I'm echoing and supporting Tim Palmer's view that the mean can hide a lot of the extremes. We need to be a bit more bold and look at the extreme signals in the tail of the distribution. And this is the problem. My forecasters and my community, my users and my customers are saying we have too much data. We are drowning in data. We're thirsty for information. Hicks' law and cognitive biases. So if you have too much information, the decisions are harder and often the decisions you made are wrong. So how do we communicate that so that we get real actionable mitigation responses based on our expertise and our fantastic research? And so in this example, we asked our community, we asked our users, what do you want? And they say, just can you give us a map and just color country by country based on your analysis of the event and your prediction so that we can then inform and get better decisions. And the underpinning science is hidden. So you can look at the dynamics of the event and you can look at how it compared in terms of decile and quintiles compared to the previous events going back using ERA 5 and also using glossy. My last piece here, so I said my presentation will be fairly short, but I think this is probably one of the most important bits of my presentation, is social behavioral sciences. I think as we enter machine learning and artificial intelligence, the role of social sciences and cognitive biases understanding is going to be ever more prevalent. Because as someone who's developing machine learning, you can choose what data you train against. There is a danger we may slip into confirmation biases. We start looking for the training data to support our argument. So that is going to be, I think, a paradigm shift in future, in 5 years, that we start to see that we need to support not only the complementary and hybrid approach of machine learning and physical models, which inevitably would deliver profound impact, but also the role of social sciences about how we create that. And more importantly, how we support and contribute to allowing people to stay safe and thrive. And it's just an illustration of this. This is a big event that happened in my country. This is a COVRAC event. And when this occurred, our meteorologists and hydrologists were unaware of this event happening because the scale of the event was so small, but so impactful. And I brought this picture up again under my training. These are cars. The forecast and the warnings, well, especially the warnings, weren't fantastic. There was no warning. So those people who were up in the hills knew nothing but what was happening down where their cars were parked. If they had their perfect warning, they may rush back to their cars. And rather than being no fatalities, unfortunately, we may find there will be dead bodies in here. There was a question that came in afterwards. I said, what about people going to the site? What do you do about that? Well, you close the road. So the warnings that we issue based on your fantastic research has to be tailored to the actions you want people to take. And that is a critical role of social behavioral sciences. A blanket warning doesn't work. You have to target people and support people so that they know what to do based on what you provide. And just my last slide here is the New York event. It's just one of many examples of the role of social behavioral sciences and the role we want to do to actually contribute to saving life. And this bit here, this quote here, basically said and appreciated that short lead time extremes is very hard to predict. So maybe we need to find a different way of communicating that so that people know what to do. This bit down here is essentially we need to focus on those people who are more vulnerable than others. In my country, those who can escape. It's often wealthy people, people who've got cars. But what about the vulnerable, disabled? What about people who don't understand what we say? What about the elderly? So and young as well in schools. So we need to target and support those communities because those are the very communities we want to make sure they stay safe. Most people who are educated know where to go. Maybe we should focus on the vulnerable and the poor and how we support that and how we communicate that is really key. So in summary, my presentation is this. I think compound extremes are changing more quickly than individual extremes. So the compound cascades of extremes of weather hazards into impact, I think it's going to be a growing issue for us. We need to look at the dynamical changes, the importance of atmosphere and how it relates to persistence. I think the extreme forecast signals, how we support our operational meteorologists and forecasters, and we need to prioritize our science for society problems. I think that's absolutely key, and how we do it is through transdisciplinary collaboration. So thank you very much for your time, and thank you for having me.
Thank you, Professor Paul, for very crisp and very important presentation and giving us sufficient time for lunch. But we can take 1 or 2 questions if someone is interested, or we can talk with him during lunch. That is also possible.
Thank you. It was a wonderful talk. I really enjoyed. I'm really not in the field of extreme weather. I'm more dealing with what's going on in the stratosphere. So I just wanted to have your opinion about, do you think there could be more physical processes involved in the stratosphere that could be responsible for compound extreme events?
Yes. Yeah, I do. Because I think the role of the stratosphere has a key role in the blocking patterns, because it sometimes preconditions, right? I know there's papers that suggest that right now, the polar vortex in the Northern Hemisphere, it's been fairly strong. It had a rebound. And that probably has an impact on the double jet structure across the Northern Hemisphere, or the potential for, which then results in these blocking patterns. So yeah, absolutely. Keep working hard on it because we need your research to help us to save lives. Thank you.
Thank you. So Any other question? Okay, and yeah.
Hello, thank you for this talk. I'm coming also from the stratosphere. And my question is, you have extreme weathers like thunderstorms, typhoons, and do you are also interested into the interaction with like in the monsoon systems? So we are here in Asia, and then we have an impact back to rainfall, whatever. Is it also something what you are dealing with?
Yes, we are. And hopefully my presentation showed that with the Pakistan floods. We're interested in what's happening in the Indian Ocean and what happens in India. Because if we're in a situation where a circumglobal teleconnection pattern could materialize, that's a consequence of the Indian summer monsoon. And that has a massive impact for mid-latitude weather, whether we get blocking patterns in the United States, heat domes, heat waves, flooding. Also for, Europe, there could be more prevalence of heat domes, especially across eastern parts of the Mediterranean, Western Russia, and obviously the impact it has across Southeast Asia. The whole planet is interconnected. It's a living organism. And so all to focus on one bit, you get misguided. You have to look at the whole living system to better understand and predict extremes at the local, but that has to come from the global too, and back again. Thank you.
Thank you.
Thank you. Thanks, Professor Paul, for your excellent talk. There are extreme atmospheric blocking in the northern hemisphere, particularly the west of Russia and the Siberian high. What is the effect of these things on the compound flooding events that occurred in England and other places?
Yeah, thank you. So with the Pakistan floods we saw in 2010, yes, we had the heat dome right over Western Russia and the massive heat wave. The big impact from a meteorological perspective is that was part of a blocking pattern and we sat in the wrong side of the block. It was wet for us. In fact, that was our infamous barbecue summer, where we said we're going to predict the fantastic summer. Everybody gets the barbecue out. It's one of the wettest summers we had. We learned a lot of lessons from that, how you communicate. But also that has a big impact from food security, right? Because the CGT pattern, if it does materialize, unfortunately, the heat domes sit in the wrong place. Central United States, the Great Plains, Western Russia, Southeast Asia. This is the growing food production, right? The breadbasket of the planet. So there's a real concern, not only just about the meteorology, but the consequences on the economy and the consequences on food security too. And I think that's something which we maybe in time need to branch out and engage with. Thank you. It was a great question.
Yeah. Thank you, Professor Paul.
Thank you.
One short question. I like your points of combining forecasting with social and behavioral sciences. But there is a premise that is assuming your forecasting is right. And we are typically used to giving good examples when we do a good job. In reality, we are guaranteed to mess up sometimes. When you become too serious telling people, particularly disadvantaged groups, what to do in the end, nothing happened. There is a price there. I don't know, how do you handle that part?
That's a very, very good question. When I engage in my country, the civil protection and communities, they came back to me and said, don't worry, Paul, we screw up as well. And so, for example, that in Sri Lanka, we had the huge floods in Sri Lanka this weekend just gone. What they didn't realize is that they were relying on electricity to monitor the river gauges, but they had to switch the power off. They had to switch the power off because it was dangerous. They suddenly had no means of monitoring the rivers. They were blind. And then we're relying on solar power for those observations who relied on it, but it was cloudy. And so when people stuff up, everybody stuffs up. And I think it's an appreciation on being empathetic and honest with your customers and people to say, yeah, we do screw up, but can we work together? Can we work together and understand how we can present a narrative that we understand what to do with your best science, but more importantly, from your side, what is it you want to know? What do you need to know so that you can protect your family and your property? Because between that, you may find the answers and the resolution, the research may be very different. So that's the key, transdisciplinary. Transdisciplinary is everybody involved. It's not for communities, it's with communities. That's the key. Great question. Thank you.
Thank you, Professor Paul. So now we will break for lunch. If there is any announcement from our organizers.
We will break, sorry. We will break for lunch and resume this session by 2 o'clock. And those who are funded by A Park, please remain seated for instruction to fill the form. Thank you.
So welcome back. We are going to start and continue the last session. And
So next talk is from Dr. Indrani Roy, University College of London, UK. She is giving a talk about East African October to December rainy season, major drivers, mechanism, and improved predictability.
Shall I start?
Yes, sir, please.
Hello, everybody. I am Indrani Roy. The title of my talk today is East African October to December rainy season, major drivers, mechanism, and improved predictability. The outline of my talk: first, I will compare station data with observation and reanalysis. Then I will discuss about East African monsoon, October, November, December rainfall and drivers. Then I will do some analysis based on station data that will cover cumulative rain and onset date. And then I will summarize my work. What is the motivation of my work? The motivation of this work is that compared to other African countries, East African countries are more prone to floods and droughts. Now, the initial work started, comparison of various precipitation data set against local observation. Now, various data are consistent in identifying bimodal pattern shown in top left for Kibaha station shown here, and unimodal pattern bottom left for Metora station. Rainfall pattern are presented here. Station data are marked by thick black line. And we chose these two stations because both have station data to compare with. Right-hand side is a correlation table that indicated that high resolution CHIEPS data has stronger correspondence with station data, and the correlation coefficient is 0.74. And because of that, most of the work afterward, we focused on CHIEPS data. Now we did precipitation of OND, October, November, December season with separately for ENSO as well as IOD. And there is a very strong correlation in the region of East African sector as marked here. Left-hand is plot is for precipitation OND versus NINO 3.4 OND precipitation correlation. And the right-hand side is precipitation OND with NINO 3.4 in July, August, September. What we find, there is a strong, significant positive correlation when we consider simultaneous season shown here in left. And again, if we consider JAS for NINO 3.4 with correlated with PPT, October, November, December, in this region, again, we find a very strong, significant signal. And similar signature is noticed if we consider Indian Ocean dipole instead of ENSO. Next, we verified compositing technique. Why we applied compositing technique? Because it can eliminate effects of confounding factors of ENSO and Indian Ocean dipole when both are in the opposite phase. To strengthen the work of correlation, we further did correlation analysis separating 2 decades. Right-hand side is for later 2 decades. Left-hand side is for earlier 2 decades. Here is the precipitation OND correlated with Indian Ocean dipole, July, August, September. What we observed, again in the same region, there is a very significant signal, positive signal in this East African sector. If we use ENSO instead of IOD, the signal is similar. Also, we have shown here the data detrended here if climate change signal is having any effect. Even detrending or without detrending the data, the results are similar. Here, data is shown here after detrending. This work was continued with various other data sources. GPCP is shown here, but other data sources are also giving similar results. We tried regression analysis, but the results are same. Now, knowing that the connection is so strong, we further did the compositing technique, and why we did, we explained earlier. Here is the result for compositing. Left-hand plot is for CHIEPS data, right-hand side is for GPCP data. Now, whole period, we have segregated those in 6 cases based on ENSO and IOD drivers. Case 1 considers when ENSO and IOD both are negative, starting from July, August, September, that continued till October, November, December. Case 2, consider when ENSO and IOD both drivers are negative only in July, August, September. Case 3 and case 4 are similar like case 1 and case 2, but here respectively, but here both the drivers are positive. Case 5, when ENSO and IOD are opposite in July, August, September, whereas case 6 considers all years together. What we observe, if we focus on top left plot in using the CHIPS data, in the region for case 1 situation, we find a very strong signal here. It is a deficit of rain is identified. It is very significant, shown here marked by red. Whereas if we focus on case 3 situation, there is an excess of rain in the same region, marked here by blue. However, if we focus on case 5 situation, no signal is detected in the East African sector. Instead of case 1, if we consider case 2, the signal is similar. And instead of case 3, if we consider case 4, the signal is similar. To strengthen the result, here we are presenting the result using GPCP data. Again, for case 3, case 1 situation, there is a strong significant deficit here shown in East African sector, whereas excess of rain shown here in case 3 situation. Significant region, 95% significant are marked by hatching. Now, one interesting thing is that in 2022, we were in case 1 situation, and it was the second consecutive year. And we indeed noticed deficit of rain in those countries of South African sector. Those countries cover Tanzania, Malawi, etc. What we did, we issued a news bulletin and we informed relevant authorities like WMO, Tanzanian Meteorological Authority. A blog was written in September 2022, and those were validated at beginning of 2023, and that outlook indeed matched. Next, we also did some analysis based on interdecadal, decadal, and multi-decadal signal. And to understand that, we have used centered moving average method. The same region where we detected significant signal, we marked here was by A. We have taken an average value of rainfall of that region. And we find that there is no significant trend if we consider year-wise variability. For interdecadal signature and decadal signature, we could identify the trough and peaks. When we focused on multi-decadal signature, there was a rising trend and it switched around 1957-8 and it became decreasing trend. 1957-8 has been detected by a climate shift period by many other research, and it was observed in other climate variables as well. Now, what could be the mechanism? We identified that based on the Indian Ocean dipole and so there are different signature. If the phase matches with each other, there is a different signal. What could be the mechanism? To understand that, we have plotted zonal wind anomaly at 200 millibar level. Here, I'm showing ERA 5 data. Right-hand side for case 3 situations, left hand for case 1 situation. What we observed in the region of East African sector, again, the signal is reversed in case 1 to that from case 3. To strengthen the mechanism part, we further did longitude height plot. Here is the zonal wind anomaly for using ERA 5 data. Right-hand side is for case 3 situation, whereas left-hand side is for case 1 situations. Again, we see in the East African sector, the zonal wind is reversed in case 1 to that from case 3 in that place. And all these mechanism part indicate that Waka circulation is indeed playing a very important role in such kind of analysis, and for this getting that different result. Now, further classification of drivers based on threshold value also tested. Here we have taken threshold value 0.4. It is tested for case 4 because recent year 2023 was case 4 situation, and JAS fell in that category. And if we extended data since 1940 for ERA 5, we have longer period data available. And again, a very significant signal, excess rain is noted in the same region of East African sector. And 2023 also, we noted that there is a very excess rain in this last year. Next, we are focusing on onset of rainy season. Onset plays a very important role for purpose of mainly agricultural purpose. Now, criteria for rainy season onset in Tanzania using official standard technique. Here I am termed here as ST or standard technique. It is given by Tanzanian Meteorological Authority. There are various thresholds involved, as you can see here. There are various conditional statement and arbitrary threshold, and those are also varying different countries to countries. And as there is a limitation, it indicates that there is indeed an importance of a new algorithm that is free from any conditional statement as well as any arbitrary threshold. Now, here is a plot using the standard technique, official standard technique. We have plotted the onset date using different data source. Here, I have presented 6 different data. What we note here, that there is no consistency among various data sources. In some year, say here, we have marked there 2016. In this year, there is even 60 days difference between onset days if we consider different data sources. Now, a different new technique we have tried. It is a alternate technique, and we are giving a term here AT, which is based on cumulative precipitation anomaly, and it is not based on any arbitrary threshold or condition. That technique is, this paper is published. I am one of the co-author of this paper. And that technique, here I am presenting result for 2017. It calculated onset date, duration, as well as cessation date. And it was a normal rainy season year, and onset date defined by standard technique and alternate technique AT both matched. How this technique worked? The black zigzag curve shows daily rainfall starting from July, and blue curve shows cumulative anomaly. And when the cumulative anomaly changes from increasing to decreasing to increasing that particular day, we are noting it at onset date and marking here as green. Whereas when the trend is reversing from increasing to decreasing, that particular point marked here by red, we are noting it as cessation date. And here AT and ST, both the techniques matched for the onset date. Now we are focusing on cumulative rains based on drivers. 6 different scenarios, case 1 to case 6 are presented here. Left-hand side is for averaging method. And the station I am showing here, Kibaha. Why I am choosing that station? Because it has a station data, easy to compare with. Right-hand side, the same case 1 to case 6 situations I am presenting here for cumulative OND rain. But here I am using box plot. Top one is for Kibaha station, bottom one is for Metara station. What we see, there is a rainfall deficit in case 1 and 2, shown here by pink, whereas there is a excess rain for case 3 and 4, shown here by blue. And uncertainty is smallest in case 1 and 2 for all the cases. And also, box plot is giving better result because we can also remove the outliers from the box plot. And rainy season onset based on the drivers in July, August, September is also compared for 2 different techniques. Right-hand side is for standard technique, left-hand side is for AT technique. What we find in both the techniques, that there is a late onset in case 1 and 2 shown by pink, whereas early onset in case 3 and 4 shown by blue. Sometimes 1 month different of onset date using these 2 techniques. And next, to summarize my result, we have identified 2 important drivers of monsoon OND rain in East Africa, and affected regions are identified. Compositing indicated there is a significant rain deficit in OND season if both drivers are negative in July, August, September, whereas there is excess rain if both drivers are positive. We showed water circulation is playing a very important role. An alternative technique, AT for onset, is tested, which is based on cumulative precipitation anomaly and offers fair result and comparable to official standard technique. We also identified late windy rainy season onset if both drivers are negative in July, August, September, whereas if both drivers are positive, there is an early onset. Using both the techniques, we define that result. Future outlook of cumulative rain and onset date is possible even a season ahead using box plots for any station or average over a region of East Africa. And here are the few papers that are published based on this research. One important thing is that Indian Ocean dipole data is keep on changing, and the data I use for my analysis, I have published the data. And if you want, anyone who was interested in using IOD data, you have to be careful when the data has changed. You have to mention in the paper also. And thank you very much for your patience and listening to the talk. Thank you.
Thank you, Indrani. Are there any questions?
Thank you, madam, for your excellent presentation. What is the role of the West Atlantic, East Atlantic ocean, Atlantic influence on the west coast of east coast of Africa?
Yeah, thank you.
That moisture is it
Yes,
is there.
yeah. Because for windy season, we found the strongest role is playing by Indian Ocean Dipole and ENSO. Also, SAM is playing some role, but we didn't include that SAM part in the analysis. But long rainy season, March, April, May, there is a more influence on Atlantic region. Atlantic Ocean and North Atlantic Ocean, that oscillation is playing a role in March, April, May, but October, November, December, we couldn't identify that signal there.
Okay. Any other question? Okay, I have a question.
Yes.
You told that even in one season advance, you can give onset this thing based on cumulative rainfall. But whatever you have shown the figure which is down and going up, so there were so many times when the graph is going up and down. So when you will say that it is onset in advance, means real time, how you can say based on cumulative rainfall. Can you go to your slide?
Yeah, I can.
Where you are comparing.
Here is the onset. This is the onset and this is the cumulative rain.
Just go back. Yeah, this.
Yeah.
Yeah.
This technique.
So here you say that whenever it will be rising, then you say that onset is there.
Yeah.
But you say there are many points when it is rising, even 25-day, 50-day, and so. How can you say that only there it is rising?
Yes, it is longer time. When it is rising up.
Longer time means you will only say after few days.
No, here say it is happening and then it turned and it never came back.
So never came back will be determined after few days only.
Yeah, of course.
How it can be real time?
Real time means standard technique is always giving the actual onset.
Okay, just.
We are comparing, but it is sometimes not matching also in the onset with the standard technique.
Thank you. Thank you.
Yes, thanks. Thanks everybody.
So the next talk is from Mr. Vaibhav Tagi, IIT Indore. He is taking an interplay of background dynamics and Earth-space circulations in the Kerala Extreme Event 2015. Please, Vaibhav. Online or please check. So then next talk is from Srividya Ravi from QSAT. It's an online. Is the dynamical aspect of heavy rainfall when if somebody can inform to she's there, Srividya. Okay, Srividya, you are ready? Okay, please. Unmute your mic. Srividya, please unmute your mic. We are not able to hear you. We are not able to hear you, Srividya. Can you again log out and log in or? Hello, Srividya. We are still not able to get you. Is your microphone working properly or not? That's doubting.
हेलो आप लॉग ऑफ होके वापस लॉग इन कीजिए मैडम।
I think already she did once.
नहीं नहीं अनम्यूट है अनम्यूट है।
Hello, Srividya. Things we are not able to get you. Maybe you should have microphone. Yeah. Maybe microphone. No, no speaker. Yes, yes, you can log in from your phone if your network is proper. Yeah. Yes. Yeah, your presentations are up. You, you, you can dock from your phone and we can shift the slides from here. You can. No, we can. Can you test again from your phone? Yes, it's already been. You can use your phone and you can try. Some of her friends will be here from Gizat. Can help her.
Hello, am I audible, sir?
Yes. Now we can able to. Excellent. Please start.
Sorry for this. Hello, sir.
Hello, Srividya.
Hello, sir.
Echo is there.
Am I audible?
Hello. Yeah, yes, yes. Now it's clear. Yeah, please continue.
Sorry for the inconvenience. And also thanks for giving me this opportunity to present through online mode. And my topic is dynamical aspects of heavy rainfall events over southern peninsular India during northeast monsoon season and its association with the Indian Ocean warming and MJO. We all know that northeast monsoon is an important season for peninsular India, especially for Tamil Nadu region, because about 60% of annual rainfall is from northeast monsoon season. So heavy rainfall events and associated flood studies about northeast monsoon season is important for this region. In 2050, Southern Peninsula experienced a heavy rainfall event and associated flood. And 2015 was a El Nino year. Several studies have emphasized the importance of influence of El Nino on occurrence of heavy rainfall even during that time. And in 2021, which was a La Nina year, that time also Southern Peninsular India experienced a heavy rainfall event. This motivated us to re-examine the relationship between El Nino and heavy rainfall event, and also association with the MJO, because MJO was in fourth phase for 15 days in November 2015 and 70 days in November 2021. We have used daily gridded rainfall data from IMD and SST from hard SST data, and all other data, wind data, moisture divergence data, net long wave radiation data, etc. from ERA5 analysis. And MJO indices is from RM11 and MM2 index is used. Percentile technique is used to identify the heavy rainfall events. If the daily rainfall event exceeds 95th percentile, is considered as a heavy rainfall event. This is the comparative study between rainfall event during 2015 and 2021. And this plot shows the daily rainfall averaged over the southern peninsular Indian region. And the black line shows 2015 year and orange one shows 2021 year. In 2015, there were 4 heavy rainfall events. And in 2021, there were 3 peaks is observed. And association of easterly wave with this activity is also analyzed. In 2015, first event is occurred from November 8 to November 12. In easterly wave analysis, there is a easterly wave propagation from 6th of November to 11th of November is observed. Like that, all other events in 2050 and all 3 events in the 2021 are also associated with the easterly waves. So easterly wave activity is important for occurrence of heavy rainfall over the region. Then synoptic condition during both events are studied. The above figures show SST and wind anomalies during 2001 and 2050. As 2021 is a El Nino year. La Nina year. 2021 was a La Nina year. Since negative SST anomalies are observed over the My screen is clear, sir. Hello, am I visible? Hello, sir.
Yeah, it's visible. Please continue.
In 2021, which was La Nina year, and negative SST anomalies are observed in the Eastern Pacific Ocean and positive anomalies over the West Pacific Ocean. So wind is easterly in the equatorial and Eastern Indian Ocean region, and wind is westerly in equatorial and Eastern Indian Ocean region and westerly in the West Pacific region. And easterly anomalies of wind is also observed in the hello, is it clear? Is it visible? Hello?
Yes, yes, yes. Please go ahead.
In 2050, which was a La Nina year, positive SST anomalies are observed in the East Pacific and Indian Ocean region. Negative SST anomalies are observed in the West Pacific Ocean. Hence, easterly, strong easterly. My cursor is visible to you, sir. Hello.
No, cursor is not visible. Yes. No.
It's okay.
It's okay. Please go ahead.
Easterly wind anomalies are observed in the eastern and eastern equatorial Indian Ocean and Bay of Bengal region. Convection is associated with the positive convection anomalies are observed over the southern peninsular India in both time period. So both El Nino and La Nina years are giving heavy rainfall even for the study region. We have analyzed the relation of northeast monsoon rainfall with the Nino 3.4 SST, and we have done a 21-year moving correlation between northeast monsoon rainfall and Nino 3 SST, and we have get a decadal variability and in recent time from 1999 onwards, the relation between El Nino and northeast monsoon rainfall is weakening. Some other studies are also reported weakening of relation between El Nino and northeast monsoon rainfall in recent time. Then we have analyzed a trend of heavy rainfall even in recent time, which is increasing in the southern tip and southeast coast of India. So then we have analyzed the atmospheric and oceanic variable associated with these heavy rainfall events in two epochs. The first epoch is considered from 1981 to 2000, and second epoch is considered from 2001 to 2021, both showing different pattern. And in the MSLP and wind pattern, early epoch is associated with a anticyclonic circulation with the positive MSLP anomalies. In a previous study, it is found that this type of anticyclonic activity is associated with the El Nino events. And but in the recent time, it is associated with the negative MSLP anomaly and anticyclonic vorticity. And anticyclonic circulation is from southern peninsular India Ocean to southern peninsular India to Arabian Sea is observed, and positive MSLP anomaly over the West Pacific is observed. In early epoch, rainfall is associated with the El Nino type SST. Positive SST anomalies are observed in the Eastern Pacific Ocean, and other regions are relatively cool. But in recent time, it is changed to an SST gradient. Positive SST anomalies over the equatorial Indian Ocean and the maritime continent region, and negative SST anomalies over the West Pacific region. This SST gradient is contributing more rainfall in the recent time. And convection over the southern peninsular Indian region, equatorial Indian Ocean and eastern equatorial Indian Ocean is observed in the early epoch. But in recent time, it is confined only to southern peninsular Indian region and the Arabian Sea region. And some convection over the maritime continent is also observed. And in the Pacific Ocean, it is shifted slightly eastward. And in moisture transport also, in the early epoch, moisture is transported from equatorial Indian Ocean to the southern peninsular India. But in recent time, it is transported from West Indian Ocean to southern peninsular India. Water circulation are also different in both epochs. In the early epoch, ascending branch of wind is observed in the Indian longitude region, but descending is observed from maritime continent region to West Pacific Ocean region. But in recent time, two ascending limbs are observed, one over the maritime continent and other is over the Indian region. And Indian region ascending limb is intensified as compared to the early epoch. And in Hadley circulation are also varied. In the early epoch, ascending branch of wind is observed from equatorial to near to 10° north region. But in recent time, wind ascending from near 10° north to 20° north region, and it is strengthened. And in a downward branch is also observed from equatorial to 10° south region. Hence, most of the characters in the early epoch is associated with the El Nino, and in the recent time, they are changed. So then we have analyzed the relation of HRE with the MJO. For that, trend of heavy rainfall events during each phase of MJO is calculated. And MJO in heavy rainfall events are increasing in third, fourth, and sixth phase of MJO, and it is significant in fourth phase of the MJO. And MJO duration of fourth phase is also increasing in the recent time as compared to the early time. And the relation between HRE events and MJO duration are also analyzed, which is showing an out of phase relation up to 2006. Then after that, in the recent time, it is showing almost in phase relationship. And in an 11 years moving correlation also done, which is also showing increasing correlation in the recent time. So MJO fourth phase is influencing heavy rainfall events in the southern peninsular Indian region during northeast monsoon season. So we have analyzed the oceanic and atmospheric variable associated with the MJO4 in recent and early epoch. In early epoch, MJO4 is associated with the negative anomalies of MSLP over the Indian Ocean and maritime continent region. But now it is associated with the positive anomalies of MSLP over the West Pacific Ocean region. Heavy rainfall events in the southern peninsular India is also associated with this MSLP from our previous figure. Similarly, in recent time, MJO4 is associated with the SST gradient between Indian Ocean and West Pacific Ocean. Similar type of relation between HRE and this SST gradient is observed in the above pictures. And convection is over the southern peninsular Indian region and Arabian Sea is favorable for MJO4 in recent time. It is also associated with the heavy rainfall events in the recent time. So MJO4 is associated with the, from this we can infer that MJO4 may be related with the occurrence of heavy rainfall over the region. So we have analyzed moisture divergence with the MJO4 and heavy rainfall events in two epochs. In the early epoch, the picture is entirely different. But in the recent time, the pattern is almost similar, especially the convection over the southern peninsular Indian region and Arabian Sea is observed. So this may be due to the relation between MJO4 and heavy rainfall events during this time, in the recent time is increased. And MJO4 may be the reason for occurrence of heavy rainfall over the Indian region in recent time. And we have proposed a mechanism that the positive SST anomalies over the Indian Ocean and the maritime continent, and negative SST anomalies over the West Pacific, which this create easterly anomalies to the maritime continent, and which help the formation of MJO4 and duration of MJO4 may help formation and duration of MJO4 there. So MJO4 activation goes strong easterlies from the equatorial Indian Ocean and strong westerlies from the West Indian Ocean to eastern equatorial Indian Ocean, and easterly to southern peninsular Indian region. And this strong easterly and westerly cause cyclonic circulation over the southern peninsular Indian region. So associated convection and convective activity cause heavy rainfall events over the region. So our result is that the relation between El Nino and the northeast monsoon is decreasing in recent time. But the warming in the Indian Ocean and MJO fourth phase is
Okay, Srividya, conclude now. Thank you. Any questions for Srividya? If it is not in that case, thank you, Srividya, for the wonderful talk. Thank you. No, Chair.
Thank you, sir.
With this, the session ended because we are not having another speaker. So, thank you.
Thank you, Dr. Sahai and Dr. Jayakumar for chairing this session. I request Dr. Sahai to present the mementos to the speakers. I request Dr. Fangling Yang to come forward. Now I request Dr. Tapo to come forward. Dr. Paul Davies. Next, I request Dr. Indani Roy. Now I request Dr. Rajagopal sir to present the mementos to Dr. Sahai and Dr. Jayakumar. Thank you, sir. As we are running little late, instead of taking break, we will start our next session. In our next session, I invite Dr. Surya Chandra Rao to chair and Dr. J. Sanjay as co-chair.
Good afternoon, everyone. My name is Surya Chandra Rao, and my co-chair is Dr. Sanjay. We both are from IITM. In this session, we have about 4 talks, and all are interesting talks, 3 from actually operational centers, how the extreme rainfall events are being predicted and what are the challenges being faced by them. And 1 talk is from INPI, Brazil on Parameters of Cloud Organization. So our first speaker is Dr. Patnaik from IMD. He will be talking about the challenges in making extreme rainfall forecasts at IMD.
Yeah. So I am from India department. This is the operational department. So I will be talking about the operational challenges in predicting heavy rainfall events. So let me just quickly. So this is the way I am just trying to proceed it. Operational mandate, since it is a service department, so we have a lot of mandate to give operational forecasting. Then specific to heavy rainfall event, the focus is here. So some backgrounds, why it is important and what are the some statistics of this one. And NOAA modeling and DSS, decision support system that we have generated a recent time for particularly to cater the need of the all users. Then the skill of the heavy rainfall forecast, this is the most challenging part actually where we stand now. And some specific cases that are quickly I will go through some of the specific cases where we will see how it is some cases successful and what are the challenges and potential area where we can further improve this one. So this is the operational mandate. So this 6 pillars we have, starting from observations, then observations, monitoring, continuous, then modeling, numeric modeling part of this thing. Then we are going for the forecaster using the numerical products and value addition, then forecasting. And particularly our focus is the severe weather warning. So all type of severe weather, cyclone, heat wave, cold wave, heavy rainfall, all these things. And various sectoral applications. So this is the 6 pillars of the India department. And mainly that no severe weather hazards should go undetected and unpredicted. So that is the motto. So how we can do so that it, because the loss of life and property involved, so that we can minimize. This is the accurate warning is for the severe weather. What is the lead time you should get so the disaster manager can take the appropriate action. So yes, it is a comprehensive. We have a monitoring and forecasting system and round-the-clock watch, radar, satellite observations. Then forecasting also in the starting seamless forecasting system, starting from nowcasting up to 6 hours, particularly for severe weather, thunderstorm, lightning. Then short to medium range forecast, 7 days. Then we have also extended range forecast up to 4 weeks, updated every week. Then monthly to seasonal forecasting. So we have monitoring, observations monitoring, then forecasting, seamless forecasting system. Now I will be focusing on the heavy rainfall only. So let us say India is a land where if you see the 80% of the rainfall, we mostly get during the monsoon season. And yes, this is the seasonal and mean rainfall. But mean rainfall is not changing with time. Means annual rainfall or seasonal rainfall are not having a significant trend. But yes, if we see the area where the heavy rainfall and extremely heavy rainfall, we generally get how many days in the monsoon season. So this is the area and this is the belt. So if you see central India, west coast and something northern part and eastern and west coast, these are the area mostly climatologically we get the heavy rainfall associated with all the synoptical systems. This is the last year, just to say, I mean, where last year, June, July, August, September, heavy rainfall event, that is the 12 centimeter rainfall to 20 centimeter rainfall in 24 hours. So just see, this is not fixed actually. Some year we get different location. This is the June location where we got July, August, most of the August in northern part, actually you just see the Indo-Gangetic plain. Then September also with a lot of rainfall over the northwest India. And this is the extremely heavy rainfall, mean more than 20 centimeter rainfall during the December. So this is just a recent last year. This is the actual phenomenon. But why it is important? Because we are able to minimize the loss of life associated with tropical cyclone because of our improvement in observation, forecasting, and then role of the disaster manager. But still, there are a lot of casualty happening due to the heavy rainfall during the season. So if you see some statistic, you see, means actually how much area, agriculture, population, and annual loss of life. So this is the significant loss there. Focus is now how to minimize the impact of heavy rainfall event so that we can reduce the loss of life and property. And climate change is another factor that is adding to this problem, because the climate change, global warming, temperature rise. So every temperature rise, there is a morning or talk about the 7% rise in the water holding capacity. So once the water holding capacity of the atmosphere is, so we are getting the downpour. So that's why extreme rainfall frequency is increasing. So the climate change implication, that's why it is also a problem for the disaster manager. And just this is the operational data from the 2013 to 23 to corroborate the climate change, observational change also. If you see in observation, there is a significant increasing trend of the heavy rainfall, extremely heavy rainfall that is recorded during the monsoon season over the Indian. So I was showing the one figure for 2023. So this is the graph, how the increasing trend of the heavy rainfall event. And coming to the prediction part, actually prediction, it is science problem. So scientifically, global warming, as you saw, so this is rising temperature, water holding capacity increasing, then moisture content, and also it is associated with increasing convective activity, convective instability. More so, this is also once the convective activity increasing, water holding capacity increasing, so we are getting more and more downpour. That means number of rainy days are less, but heavy events are more. So that's why this is a more challenging, but model problem is that the error doubling time reduces. So that means model error is when you are going for the heavy rainfall prediction more than 15 centimeter, that means the error is you are reaching the error very fast. So that is the problem challenging for the modeling community, particularly for the prediction of this type of event. But when we offer operational agency, yes, our mandate is to give the operational forecasting to reduce the loss of life for various sectors, general public as well as all sectors. If we means nowadays you can name any sector, they need the weather forecast, and particularly for the severe weather forecasting. So how we do this one? This is a strategy. Yes, first of all, yes, you have to have the observations that will give the model initial conditions. So one, the model initial condition, etc. Coming to observations coming, then model initial condition is prepared, then model will be integrated and numerical forecast will be generated. That is the once the forecast generated, then customized forecast. Forecaster will analyze also because of problem the direct model outputs are not always applicable. So forecaster will analyze, so that will be modulated. The forecast model will be modulated, and the end forecaster will prepare the end forecast. End forecast means customized forecast, actionable forecast. What the disaster manager want. They don't want just map or something. They need where I have to deploy my resources, where I have to migrate my thing, like that. So actionable forecast is needed. So that is called end forecast. So end forecast we prepare, then it will go to the decision maker, disaster manager. So they will do the action. So that way only the effective disaster management is a comprehensive program, like starting from early warning to the actual operation in the field. So when you come to the fast flood forecast, heavy rainfall forecasting, three parts there. One is riverine floods, so that are quantitative precipitation forecast. So we have a distributed 15 flood met office is there in IMD. Under that 156 sub-river basins. So each river basin, they need QPF. So that QPF will come from the numerical modeling, no doubt about it. But that way FMO are separated, they give the forecast, and that quantitative precipitation forecast will go to the CWC, Central Water Commission. There they will run the QPF run up rainfall model to give the actual forecast of the river forecasting. So that's why this is a joint program with CWC, with the IMD, and our input is the model forecast input. So this way riverine flood, it is addressed in this way. Then come to the fast flood. Fast flood is just with 6 hour lead time or something. So that way, this is a WMO program, South Asian fast flood guidance system. So here, what we do all the model guidance, and then even the water set. 30,000 water sets are also there, so that we generated this forecast, and particularly for short term 6 hours, 12 hours. So this forecast is updated, which are the area, and the alert are generated in operationally, and it is submitted to this neighboring country and also India. So this is the flash flood. Third part is the urban flooding. Urban flooding is another area where heavy rainfall, even the urban area, with also is very problematic, particularly like Mumbai. So we have implemented this in Chennai and Mumbai, I flow, sea flow, and along with other observations and other products. So inundation thing, they also give the forecast. So this is the 3 type of river rain forecast, flood forecast, and flash forecast. So all these forecasts you need the forecast, our model product. Next, coming to the forecast, when we call about when we need the disaster manager to take appropriate action. So they need impact information, not the only early warning, also not sufficient. only impact associated with the whatever disaster weather you are talking about, what are the impacts, adverse impacts is going to happen. So that's why impact estimation is the most important part. Whether that means 60 km/h wind will cause damage, how much damage to which structure it will be damaged. Whether 30 centimeter rainfall in a day, whether it will cause damage to some area, it may not cause damage, that much damage over Mumbai. But 30 centimeter happen in Delhi, it will be a very disaster, severe disaster. So impact estimation. So integration of the weather information and translation into exact, then extraction of relevant information from here, then impact estimation. When you are impact estimation, then you can incorporate your all the socioeconomic indicators or what all the geophysical parameters of that places, integrate that thing, then you will be able to give the impact. So impact forecast, then only it will help to the mitigation strategy. So this way impact forecast, now we have come to from the what weather will be to what weather can do. So that means that is the impact forecast. So that we have started in IMD impact forecast associated with all type of severe. So this is the for heavy rainfall impact forecast. If you see how we are giving, though we are giving model running, but we need a forecast at district level. Let us say district level with color code warning. Color code is the most important for the disaster managers. They will think only if it is red color. But how confident you are to give a red warning in such a smaller location? So this is a challenging area. But our district level, at med center level, at regional level, we give this district level warning in the color code form. So yes, heavy rainfall watch, 3-4 days we start whether the model is indicating. So 3-4 days we will give, but we will not give the red warning 3-4 days. Now there is a strategy we have adopted. We will not give the red warning even if it is confident, more than 2 days. Okay, more than 2 days. So third day, if we are expecting that third day also there is a means red warning, but we will keep it initially for the orange. But next day we will be changing to red. So this because now this impact forecast is now very useful, and people in school or college are also that government is taking decision based on the red color. Today, this IMD has issued red warning, so school, college should be due to heat wave or due to heavy rainfall or due to cyclone, like that. So impact forecast that we have adopted now, this is a 4-stage warning, and impact based on, then when we are integrating all the data of the relevant area, means socioeconomic data, then that is very valuable. So integration of GIS based, our now forecasting system, decision support system is a GIS based map with integration of all these relevant inputs, and that is combined with our meteorological input to give the impact weather forecast. So what tools we have now? What tools we are using for particularly heavy rainfall forecast? Because there is last in 10 years, 10, 12 years, there is significant improvement in the accuracy of the severe weather forecast. Severe weather, I mean severe weather, all heat wave, cyclone, this is the significant improvement, 40 to 50% improvement taken place. That is of course combined effect of observational improvement, modeling improvement, integration, DSS, decision support system, communication, everything. But here, when we said early warning, because one component of disaster management is the early warning. So early warning means early warning with accuracy. So what are the different tools for early warning? Numerical modeling is the only tool where we can give a early warning. So now when you come to numerical modeling, so we have a seamless modeling system also to address the weather forecasting from nowcasting, very short range nowcasting to up to the seasonal forecast also. So in the nowcasting level, the regional models are there, the high resolution rapid refresh with radar data assimilation, updated to means 2 kilometer resolution, every 2 hours updated, then EWRF, lightning data assimilation, and so then hurricane WRF for hurricane sign. So all these regional model with radar data assimilation and lighting data assimilation, it is updated 2 kilometer, 3 kilometer, very high resolution for at least for 12 hours forecast. So this is for thunderstorm and lightning. Then coming to the medium range, heavy rainfall or this type of weather system, we have global forecasting system, global Ensemble forecasting system, along with other system from the MOS institution like Ensemble developed, their based models are there. And this is the extended range forecast coupled model system once in a week. at least to know 2-3 weeks whether you are expecting the active monsoon spell or not. That will give idea about that yes, monsoon is going to be active. So isolated or extremely heavy rainfall can be expected in the short to medium range. Then in addition to our model, MOS models, we also generate the multi-model ensemble because for observed uncertainty there, model uncertainty there. So that's how we can combine different models in a different way to give the multi-model forecast. Then come to decision support system. Once this type of product is prepared, then it will be a GIS-based decision support system. So once that is readily available, then only forecaster at regional or Met sub-region level, our Met office, means state Met office, they will utilize that one to communicate the concerned state government. Yeah, so this I will just quickly go different regional model. First, let me say regional model. This is the high example of numerical other product for regional model. This is the high resolution rapid refresh model. So it will give me about next 12 hours, 6 hours, which are the area where you can get high reflectivity, high rainfall. Similarly, this is a lightning data assimilation EWRF model. Also give idea about the potential area of the lightning thunderstorm occurrence. And it is then this is the hurricane WRF model when cyclone is there, track and intensity with the probable area of landfall. And so this is the HRR example, this is lightning example, and this is the HWRF. So this is all three regional model, particularly for the short nowcasting to short range. Then global models, this is the example. Just if you see how this active this during 1 week, means 11 to 17 August 2022. This is the belt images associated with the system, movement of the system, very heavy rainfall and very flooding over the entire region. Okay, this is monsoon trough region. Yes, model are able to capture in the last, if we say large scale features, model is able to capture the depression movement and also the rainfall. But when we come to the actual problem that how much rainfall it can give, that is different. But when if you say large scale rainfall associated with the synoptical system, that is well predicting, model is well predicting the global model. Then the longer period time scale, when we are talking about extended range or 2 to 3 weeks also, there are various users, they need forecast for 3 weeks, 4 weeks also to planning or various other applications. So then even the river management, also dam management also, they need forecast for next 15 days, accurate forecast for next 15 days. So we have a couple modeling system. Actually, it is a joint effort of MOS, IITM, Ensemble, IMD. So operationally running every weekday. So this last monsoon, if you see, just this is a week type of June, very active July, weak August, very active September. So this type of, this active and break transitions, how effective it is model is predicting. So if you see the skill of this, our forecasting system and extended range, yes, very good skill actually. If you see the last year, you can see this is a weak June, good July, weak August, and good September. So that means up to all India scale. This is of course all India scale. When you come to actual application of in the disaster management, this is not helpful. But now this scale was not, we were not achieving that much predictive skill also for 5 years or 10 years before. So now this is very skillful. Even third week also very significant. So that means active phase is there, a break phase is there, weak monsoon phase, high temperature, heat wave, cold wave, that phase next 2-3 weeks. That indication is very well captured in the model. But when our focus is to go to how smaller spatial scale we can go. So there are various ways. So that information we have to translate into smaller spatial scale so that only the users community can utilize that one. So we go for the Met subdivision, why 36 Met subdivision, whether it is above normal or below normal. Accordingly, when we say 36 subdivisions, above normal or below normal, how skillful it? Yes, you can say week 1 is very highly skillful. Week 2, this is the correct category. That means when the category is matching, normal to normal, above normal to normal, or below normal to below normal. So that means week 2, even week 3 also. So that means at least in category wise, we are getting a good rainfall, good forecast skill. That is not all subdivisions. Some subdivisions are not having that much skill also. But overall, if you see 2 to 3 weeks, it is very useful in the sense it can be utilized by the user. So that we translating that information for the agro advisory. farmer advisory, even for a disaster manager or who are operating the reservoir operation also. So this active phase, yes, this is week 1 and week 2. So this prediction part, it is indicating this is the just like break situation over here, active here, and this is weak monsoon over here. So that is well predicting. Then break transition, this transition also break, we are going for a weaker toward the weaker monsoon. That also it is well predicted. So this active base cycle of monsoon is also well predicted in the longer time. Now coming to the whatever I was showing, the average rainfall, whether it is district rainfall or metropolitan rainfall or homogeneous rainfall or all India rainfall, this is rainfall average over that region. But now the heavy rainfall. So our focus is now on the heavy rainfall. So heavy rainfall. So what is the strategy? We are using all global models, whatever in at our dispenser is available. So MOS model, MOS running 6 models, so that inputs are available. And as I showed one graph from GFS, it is able to generally capture the large scale feature. Whenever there is a well-defined synoptic scale system, the associated rainfalls are well credited. Whether of course the magnitude is not predicting that much, but for heavy rainfall forecast, we have adopted another strategy also. This is multi-model strategy, means all models are taken, and whenever any models are 12 kilometer, mostly 7 models are there, including ECMWF model also, so that we are getting the real-time data. And whenever that any particular location, means your polygon, it can be district, it can be river basin, it can be met subdivision. So which are how many grids are falling on that thing, accordingly we calculate the probability. Probability of probability of means area-wise probability, scattered, isolated, because this is the language terminology we are using. Isolated, scattered, fairly widespread means when the how many area, 75%, 50, 25 or less than 25. And intensity also means how many grids are there, average rainfall and what is the maximum rainfall. So these two informations are prepared based on the probability. And 36 subregions every day operationally by 9:30 these products are available. So this is the spatial distribution: dry, isolated, scattered, fairly widespread. So which are the subregions? Met subregions are this whether it is fairly widespread. The intensity wise, there is a maximum rainfall and average rainfall. So that maximum rainfall also any grid point under that area by a particular model, because all models we are using here, MME and all different individual models also. So this information in the real time is available by 9:30 to the forecaster to have some idea about whether this is useful for the met subdivision level warning. So this is the first round product. We give the met subdivision level warning based on this one, along with some of the value addition. If there is some system movement is there, so they also sometimes model is not able to predict. Not all models are able to predict. Then we can give some value addition and give. So this is a met subdivision level forecast. Then come to the district level forecast. We also give district level forecast. District level forecast means met subdivision. Again, we translate into district level. Our polygon is district level. So this is the heavy rainfall. This is the very heavy rainfall probability. And this is the extremely heavy rainfall probability for the same event. So this way, we prepare this product so that you will come to know which are the pinpoint location where we can expect the extremely heavy rainfall or heavy rainfall. So warning, this is useful for the district level warning, which is prepared by each met subdivision. So I showed the met subdivision level forecast, then it is the district level forecast. And skill wise, suppose district wise skill, what is the skill of the district level forecast? Every year we are bringing out, all these reports are available, but MME is found to be the better than individual model, CC and RMSC. So this way, multimodal ensemble is widely used now for our day-to-day forecasting. But here also, if all skills go also, if you analyze, but after certain threshold, means rainfall threshold are increasing, different skill score are decreasing. This is a universal problem. So that is there. This is one of the problem why when we go for the higher 20 minutes, 5 minutes, no? Okay. So okay. So this way. So this is our impact matrix. This is the GIS-based decision support system. So that means this is the probability of no heavy rainfall, very heavy, and extremely heavy. Then accordingly probability, so we identify and we give this thing. So this is very useful for the location district-wise forecast and real-time material. Then over the last 15 years, if you see, there is significant increase, improvement in the POD, probability of detection. This is only the detection, not the threshold. Probability of detection of heavy or extremely heavy rainfall. So that means now it is 80%. Day 1, day 5 is now, this day 1 is 2002. So that means significant improvement of, and impact also. Because of impact forecast we are giving, so the loss it is reducing, and the rainfall, though but so our impact means it is minimized. So impact based forecast is also very useful now. Quickly, I will go some of the example where you will see the difficult cases. Here, this is the very good cases. This is observed rainfall. This is day 1, day 2, day 3 forecast based on our MME. So this is very well predicted. Now this is the 2023 August event. So this was a depression was moving. So this is the observed. This is day 1, day 5 forecast. So up to day 3, it is showing red color. After that, it is weak. And based on this one, we are giving this type of warning, district level warning. So this is very useful, which are the part of West MP or Rajasthan will get the event. Similarly, this is the failed case. This is the case here where observed is showing, but forecast is not showing that much up to 5 days. And most recent challenges, this we have brought out a report. There was a 2023, but 2013 case Uttarakhand was very well predicted. But there are interaction with westerly and easterly system. 8 to 13 July. Model was not able to capture this much, and longer lead time was not there. But if you see here, so this is the event, just see. This is the event 7 to 13 July, very active, but lead time was not sufficient. Only one week, week 1 forecast only was able to capture, week 2 forecast was not able to capture. Similarly, MAT subdivision level also, fairly, all these subdivision over the northern India, we were giving this warning. So this was quite useful, because if you see red color means very high, actively high rainfall. But here, then this is the event. Yes, 1 day only lead time we got. After that, it went down. So there are some difficulty cases, but recently there is cyclone. One cyclone was there just 1 week back, and after that recurved structure, and here we got extremely heavy. Our focus was on the system track, but actually rainfall also we gave warning because of our DSS system. So it gave 60 centimeter rainfall. 60 centimeter record 29th May. So our warning, if you see here, this was the red warning. And then day 2 was the orange warning. So this we could able to do. And this is the 1 day rainfall, 94 centimeter in Chennai. So this is the observed rainfall. Forecast guidance, if you see, yes, 2 weeks in advance, you are getting active phase. But none of the model could able to capture this type of event, 946 mm rainfall in even single day in one advance. So this type of events are very challenging. And hailstorm, this March, 7 March, Northwest India, large scale hailstorm was there. And this is the WD associated with that thing. It was, model was able to capture these large scale features, if you see. But when you talked about even WD was also well captured in the 2-3 weeks in advance. So this is fine. But when we come to the magnitude wise, always it is underestimating. But the last scale, how the disaster manager can utilize, so means that we have to see. But when expected rainfall, that's why I asked the ICMWF whether there can be a maximum probable rainfall. What is the amount of rainfall associated with that particular event? So that is challenging. And so mesoscale systems, and these are the challenging area. We are still not able to capture this event, particularly for the not associated with large scale event. So this is my last slide. So what is the area? I mean, probable area of application of probable area of improvement, significant improvement of multi-hazard early warning system and disaster risk reduction. So that is very clear cut. In last 10-15 years, with the efforts of MOES, Government of India, and all institutions, so this has increased and leading to a drastic reduction in loss of life, especially due to cyclone and heat wave. But we are not able to still minimize the loss due to the heavy rainfall. Since the focus is there, but otherwise it is a significant improvement is there. Scope of weather hazard monitoring and forecasting to meet early warning for UN and WMO. Early warning for all. This is the WMO initiative. By 2027, every household should have the early warning. So now we have to work, improve value chain observations, modeling improvement, forecasting improvement, severe weather, then severe weather warning, sectoral application, including research and development. These are the area all has focus should be there. And dual engine concept, AIML application in conjunction with the NWP modeling to improve the point rainfall. Point rainfall, how it can improve. These are the area where AIML can give some solution. Whatever already achievements have been done to by so that the forecast accuracy of severe weather now we can say the heavy rainfall forecasting should increase by 10 to 15% by 2023. But severe weather hazards, Gram Panchayat level, we are going for the smaller and smaller spatial scale. We have come up to block level. Now we have to go to Gram Panchayat level. And by 25, Har Ghar means early warning for all. So these are the long-lasting mandate or plan for the IMD or operational any operational agency to fulfill in the near future. Thank you.
Thank you, Patnaik, for highlighting the challenges. And you want, yeah, couple of questions.
Drink some water.
Okay, I will looking
no,
for.
this is not question.
Okay, yeah.
Question is, you said, right? You said 10 centimeter rainfall in Mumbai, whatever will be the impact, it will not be same if the same 10 centimeter rainfall happens over some northwest India, so desert, region, right?
Yeah.
Yeah. So that should be the basis of your impact-based forecast.
Yes.
Correct. Very good. Now, if this is true, then how can you make your the definition of heavy rain, very heavy rain, extremely heavy rain fixed 6.5 centimeter for whole India, 11.5 centimeter for whole India, and say 20 centimeter and above for whole India? It doesn't make any sense.
Yeah, I'll come.
Yeah.
The first part, what you said, that is right, but that is nothing to do with the rainfall threshold. Rainfall classification or threshold is just for the your idea of become monsoon heavy, extremely heavy. But second part, what you are telling, impact over that pace or that's why we are going for the impact-based forecasting. That is the reason we are going for the impact-based forecasting. Impact-based forecasting means the same scale, weather means that severe weather of same intensity will not have the same impact in different places. So that's why that all these things are integrated. In Mumbai, a dense populated, okay, if you did somewhere else, it will not have that much impact. So all the impact data.
He got the point.
He got the point. Impact data.
So, yeah.
Hello, sir.
Yeah.
Thank you so much. With due respect, I pay my rich tribute to all IMD for excellent work in the forecasting. So, though means there is intense rainfall within a short duration leads to urban flooding. Okay, as well as due to heavy rainfall, there is a landslide. So, in Pune district, there is a marine village. In Raigad district, there is a Irsarwadi, and due to heavy rainfall, it is washed away. So where we lag behind actually, though we do have excellent forecasting and all, where we lag behind? Why we cannot reach up to the level of that problem before the natural disaster hazard? Thank you.
Yeah. So that's why a good question. Multi-hazard. Why I mentioned somewhere it multi-hazard early warning system. That means hazard is multi-hazard. Why it is multi-hazard? Because we are doing every day operationally forecasting. No, this tropical cyclone, you just recently the Remal cyclone, focus was on West Bengal, Odisha, Bangladesh, where it will cause what is the intensity. Intensity are not that much, 100 to 110 kilometers per hour. It is not a very strong, severe cyclone storm. Okay, so this was a very moderate cyclone. So focus was that. But our forecasting was good. Means when we are telling that this will cross in this wind speed, disaster associated with strong wind or it was less because wind speed was less. But after recurvature, it gave rainfall 60 centimeter over northeastern states. Okay, northeastern states. So second disaster associated with cyclone is after wind and storm surge. Third disaster was rainfall. So rainfall after the third disaster rainfall, again it was fourth disaster was the landslide. Okay, so that's why when we talk about the multi-hazard early warning, so we have to see all the what are the impact. That's why when I could not show this thing, even associated with this system, we had given warning to the northeastern state such and such rainfall expected, and landslide, this thing is possible. But when you have, so when the disaster manager, they have to take all this into account, means where the landslide will happen, whether the worker are working under the ground. So
Okay.
that was happened. So
But
that's why.
I think we can discuss this
Yes, sir.
offline.
Yeah.
Sorry, I have to stop you.
Okay,
because
but
time is
I
already-
explained partly.
Yeah. Thank you, Patnaik.
Online questions.
एक ऑनलाइन क्वेश्चन बोल रहे
Okay, what is that question? Who is the
idea where I need improvement?
Just go up. Piyush Gupta.
Himalayan region. The light rainfall agree well with IMD forecast.
Okay, I
region.
think you can give it, type it there.
Can you
And,
give me
yeah.
idea where I need it?
You can see it from there.
Yeah, so yeah, this is general discussion, not specific to me.
Yeah.
Yes, so whether model improvement is required, yes, physical parameters are required, no doubt. Without, because long-term strategy, model improvement will be there. Then product utilization, product improvements, AI is, that is secondary. So that will go on parallel. But yes, you cannot leave the focus on improving the physical process parameterizations and numerical modeling. Thank you.
Okay. No, thank you, Dr. Patnaik. Now we'll welcome Dr. Silo Freitas from INPE Brazil. INPE. Welcome, sir. So he will be talking on a parameterization for cloud organization and propagation by evaporation-driven cloud pool edges. So you have half an hour. We'll give you a plaque at 5 minutes before half an hour.
Okay, 25 plus 5.
Yeah.
Okay, thank you. So do I have a pointer? Can move the slides as well. Mhm. Okay, thanks again for invitation to be here. It's a nice time, nice talks. So the idea is, what I'm trying to talk to you today is about exactly what we are showing here is this kind of convective system that moves, and most of the low resolution model cannot capture very well this movement, this propagation, right? So what I'm going to talk today is, I will give you some examples of the phenomena I want to improve its representation. But in the context of low resolution, that means no convection allowing, no resolving global or regional circulation models, right? So I will say why I'm doing, why it is important to do. So then I show some cloud resolving models to simulations to help to design the parameterization. So then I'll talk a little bit about what we are proposing in terms of parameterization to represent this process, applications, and summary in ways to move forward. So first of all, sorry about that. I'm from Brazil, so we have a lot of focus over the Amazon. So this picture shows some examples of large-scale squall lines over the Amazon. So you can see the gust fronts, several, the same day, same time over the Amazon. You can see very large mesoscale squall lines propagation. One nice thing also, frequently in the ghost front areas, you have a concentration of lighting, is what you can see in this remote sensing data. Also, this is not only confined over the Amazon, but also the central part of Brazil, where I was born in this place here. This is savanna-like vegetation. So you can see also very large cold pools that triggers convection far away, right? This is an ordinary day over the Amazon. You can see the same day, in same scene, you can see bow echoes, straight lines happening over the Amazon. So Adrian Thompson in 2001, he has a very good paper. He described this cold pools and the effect of the cold pools on triggering convection, right? So in his conceptual model, so in the beginning of the convection, you have some evaporation building subcloud layers that create some positive anomaly of the moisture. Then in the mature phase, you have the downdraft that push this positive anomaly far away. And then you create this kind of signal in the border of the cold pools. We have a signal of the positive anomaly of the moisture. Of course, inside of the cold pool, it's drier and colder. But we have this in front of, in the gas front, in the edge of the cold pool, we have this positive anomaly of moisture that is translated in positive anomaly of moist static energy, right? And also this front moves very quickly. They have a lot of momentum linear that can collide with the environmental wind and ramp the air masses over the environment, creating a region that is prone to develop new convection. So this is just a picture that can give you some overview. It's a nice picture from Britannica that's showing you this intrusion of the dry air in the middle levels in the thunderstorm. Then you have evaporation, you have the negative buoyancy that go propagate down. And when this air mass reaches the surface, they spread laterally and forming this gust front, right? Pardon, my cartoon is not very nice, but I think it's good to show the main idea, right? You have evaporation, downdraft, you have the gust front propagates and create new clouds, right? This is not very good, but it was the best I could do. So, but so far, this is called the dynamical forcing. More recently, we are call attention for something else that also can be important to triggering convection, right? So you have this, for example, we have the cold pool here, the gust front, you have the propagation, linear momentum, but also if you think about that, what happening in the cold pool border, so you have anomaly of the moisture, right? And this anomaly of moisture that reflects on positive anomaly of moisture energy, it's creating a new kind of forcing to trigger convection that is normally called thermodynamic forcing, right? So what I'm doing this because including representation of this process, this might be useful by introducing spatial temporal correlation between convective events. So say, you can create some kind of memory in low resolution models. It might help the diurnal cycle of precipitation, might help the cloud organization in terms of clustering, lifetime, propagation, and also even for atmospheric composition. So this, they can improve subgrid scale emission estimation of the sea salt, dust, aerosols, and so on. So how to parameterize this process? So 1A is, let's do a very high resolution simulation to understand the physical process, and then try to get the essence of the phenomenon to parameterize in the low resolution model, right? So to do that, we using our Brazilian model. It's a BRAMS that is based on the RAMS Colorado State model. So we are running on 250 by 250 meters. That covers about 500 by 500 kilometers square. And vertical resolution 50 to 500 meters with the model top 20 kilometers. So BRAMS is non-hydrostatic, is not fully compressible, but it's enough for simulate explicitly cloud motion. So we have implemented a better time degradation and advection operators. So you're using isotropic turbulence, three-dimensional turbulence. We have a monotonic advection for scarless. And cloud microphysics, you are using the Thompson scheme, which is a hybrid single double moment scheme. Radiation and RHMG and surface scheme is a fully system leafy tree, right? This is picture showing the day of the model simulation and also to give you idea of the extension of the domain, right? So what I'm showing here is some snapshots, instantaneous fields moving, showing the simulation from 13 to 20 UTC, the morning until late afternoon. So what I'm showing here is the precipitation field simulation, remember at 250 meters, right? This is the near surface temperature. This is the water vapor mixing rate and near surface as well. And then the correspondent, the moist static energy over the surface, right? So you can see the clouds, straight lines being formed, some organization you can see. And the idea is explore these results to understand how to parameterize the process. So let's take a zoom to look at more details. For example, look at this box here. So you can see a skull line here moving from east to west. So this is the temperature. So you can see the cold pools surrounded by some warm areas in the front. So you can see here the moisture, the water vapor mixing rate. So you can see what people call moist rings around the dry areas. And here you can see the corresponding moist energy associated with these moist rings, right? So if you look at the vertical velocity on the left and then the moist static energy on the right, so you can see positive vertical velocity is more red, yellow. When you cover the over the MSE, you can see, of course, is expected the upward motion happen over mostly of these areas with positive moist static energy, right? So from this experiment, you can try to discriminate areas that represent the moist rings. I mean, they also just outside of the gust front and areas inside of the gust front. So you can discriminate. And then you can calculate what's the anomaly of the moist static energy in comparison with the area mean, right? And one thing that we got was this kind of PDFs. You have the blue PDF, that is the probability density distribution of the moist static energy anomalies inside of the cold pool. And the red one, that is the anomaly just outside the cold pool. So you can see we have some, the anomalies are positive outside and negative inside, right? So this, when you look at the mean standard deviation, outside you have it on average 2 kilojoules per kilogram, and inside minus 2.1. So this is not original, it's not new. This is several other people already got similar results in terms of the PDF distribution of the anomaly, right? So the idea, if I can in some way simulate this anomaly and can use the dynamic core of the model to transport these anomalies, in some way I can try to propagate some signal that can help trigger convection downstream, right? So the parameterization that we propose so we define a new scalar. It's a positive definite scalar, three-dimensional scalar that we call buoyancy excess. That is the difference negative of the MSE in the downdraft, the cloud work function in the downdraft minus cloud work function. Sorry, the MSE inside the downdraft minus the MSE environment, right? So this quantity is, by definition, positive definite, right? It's a scalar that can be prognostic. So have the AD and ATU, the downdraft environment moist static energy. So one thing that it is a very powerful quantity, because if you have it, you can, for example, estimate the gust front horizontal velocity that depends on the beta X and some environmental properties. We can calculate also, estimate the maximal vertical velocity at the leading edge of the cold pool that we can use by this expression, right? And then you can some way calculate the propagation of the cold pool if you use some kind of the mean cloud layer environmental wind that is transported downward, and then this mean velocity is pushing the cold pool together with the difference of the temperature between inside of the cold pool, outside that by this velocity. We can have a propagation velocity that you can use to propagate your signal. So we use the advection scheme the same of the dynamic core to propagate the signal, right? So this beta X has a prognostic equation that is have the advection term, the diffusion term. You have the source term that is the delta D. Is the trainment mass flux from the downdraft. And of course, the cold pool dissipates because you have mixing with environment, you have surface flux that acts to destroy the cold pool. So this mixing and surface flux is too complex to simulate in this context, right? So the best way to go, in my understanding, is define some decayment term, define a lifetime of the cold pool. So you have some sink term where you have that is proportional of the beta X over some lifetime. And this lifetime is in the range 1 to 3 hours. So it will be a tunable parameter. We currently use it 2 hours, right? So this is a typical output of this variable over the Amazon. So I was very surprised with the output because I realized later that I'm not actually simulating individual cold pools, but I'm simulating the mesoscale effect, I think, right? So you can see here, for example, the front of the gust front. So you can see here in the front, in the front, you have this beta X anomaly is higher value and positive values behind. So this is something that I was surprised that was representing something that I want, because this is already in the scale I need, because this is the scale of GCM, right? So, well, this is the parameterization. Now, how you couple this with the traditional convection parameterization, right? So we use the Grell-Freitas convection scheme, and one of the clauses that you have for calculate the mass flux at cloud base is proportional what you call cloud work function that's related to Cape over the time scale of the overturn of the convection, right? So to include the fate of the cold pool, we have here the cloud work function definition. That is the updraft moist static energy minus the environmental saturation moist static energy is calculated from cloud base to cloud top. So you need the boundary condition to calculate this expression. You need the cloud boundary condition for the updraft moist static energy. So normally the boundary condition using some value of the environmental below the cloud base. So what you do is, if you have a cold pool, you have some extra energy for this cloud, for this air parcel. So you just add the beta X with the environmental moist static energy, right? And also I do the same with the initial moisture from the air parcel. So you have the beta X by the latent heat. Another thing is if I have a cold pool, you have the clouds comes up forced by the environment. So this has a initial vertical velocity. I should use this initial vertical velocity as a boundary condition to calculate the subgrid scale vertical velocity. And then I can calculate the time scale of the turnover like this. That means if I have a larger or stronger vertical velocity in the cloud, my turnover will be shorter. So then I can increase the mass flux. I can get more stronger convection, right? And another effect also is in terms of trigger function. So I can try to calculate energy cinetic in the leading edge of the cold pool. And I can allow convection only if this cinetic energy is over the inhibition convection energy that Professor Manuel told us, right? So this is an example in the model. So we have here 1 hour precipitation rate simulation. It's just a snapshot. This is 8-kilometer resolution. This is the ghost front speed. You can see values about 5.5, 10, 12 meters per second. And this is the maximum vertical velocity at the edge of the cold pool. That would be about 2 to 10, up to 10 meters per second. And this is the beta X, right? So this is an animation showing how this happened in the model. For example, I have here the precipitation rate, cold pool minus control. That means you can see that you have intensification and organization of the system. One nice work, one nice result that I got is how this parameterization impacts the organization propagation. So I have here a simulation. This is northeast part of Brazil. So have a region that in the coast you can is placed to bear call lines that propagates towards the Amazon basin in this direction. So this is from 20 UTC. This is 22, 24. So you can see that the propagation of the squall line is not very well defined. So model broke, the squall line is broke a few hours after, right? But if with this parameterization, you can see the squall line is very well defined, can survive longer. And also this is the position of the squall line in the control experiment. So you can see also the squall line move faster than if you just leave the model do itself, right? So we try to evaluate this more deeply. So you ran for Go Amazon. So now I'm showing results with 8 by 8 kilometers resolution. Again, using BRAM's model. Now the microphysics we are using WSM5 and surface scheme Julius. So we are using reanalysis, ERA 5, as a boundary initial condition, right? And you are doing 10 days forecast, each day, two days lead time. And we are just analyzing the second day, right? So this is the model domain. And we are going to show only the one field campaign that was IUP 2.4 that during the dry to wet transition. So this is the precipitation average, 10 days average, right? This is similar if you took 1 month or not. So this is 10-day average using our GPM emerge that we are going to use as our reference, right? So have here 4.5 millimeters per day, the precipitation average over this area from 1 to 10, October 2014. This is the same period with ERA 5, 5.2, very close to GPM emerge give. But remember that GPM emerge is remote sensing retrieval. They also have some uncertainty, right? I'm not saying which one is the best. Then we have the simulations without the code pool. So the model has similar results as ERA 5. And then you have the results with 5.5. So I'm not asking Nobel Prize here, but we can see that if you compare this precipitation distribution with the GPM emerge, you can see that this has a little bit more organization, right? To have more patches, dry and moist in comparison with the simulation without code pools. So in terms of propagation, we have here the lat long average. So have propagation from in the northeast to northwest. So this is GPM emerge, so you can see the propagation of the systems. And now if you don't use the code pools, you can see some propagation, but it's much more, not more. So if you use the code pool, you have more sharp, more well-defined propagation, as you can see here. So in terms of the intensity of the storms, so we have in black, again, the GPM, PDF, rain rate. In green is with the control experiment, and in blue is the experiment with the code pool. So we expect you get more intense rainfall events with the code. Well, I did not fix these studies over the Amazon. I start looking for different parts of the world with BRAM's model. So I have simulations for Conus, Africa, Amazon, Rio de la Plata bases of mesoscale complex systems. But the resolution of the models is about 10 kilometers horizontal resolution, 48 hours simulation, starting from ERA 5. So this is one example. This is a big event over the United States. 2 to 3 October 2014, was a 1,200-mile long line crossing the continental United States. In the left, we have GPM image. This is the control. This is the cold pool. If you look at in more details, you will see that this is, in some cases, it's slightly better in terms of in comparison with the control. But in some cases, for example, in case of the mesoscale complex system over Western Africa, you can see that in some situation model, the control experiment did not capture well the system. He captured later on. But the cold pool case, he just in the beginning pick up the system better, right? So just to give you a snapshot for a certain time of the simulation, 2-hour precipitation accumulation. So this is the case of the Amazon.
Dr. Tallo, 5 minutes.
5 minutes, okay, let me finish. GPM emerging, this is the control. So we have the cold pool. So we have some gain of organization as when you compare GPM emerge. This is for Africa. This is for the Conos area. And this is for Rio de la Plata Basin in Paraguay. So you can see the cold pool improves the representation of what GPM gave us, right? So just quickly runs now in global scale using the MPAS model. So I'm not going details. It's using now MPAS, using also, now we are using GFS as initial condition. So what I did here was across resolution, 60, 30, and 15 kilometers. I'm trying to represent some squall line over the Amazon. So this is the control experiment, right? So you can see the position is similar, but you don't see so much organization when you include the parameterization. So have much more well-defined and sharpened contrast between moist and dry areas. Also, something that we can think that I cannot compare directly position of the precipitation, as you well know, but some things say that the statistic of this simulation is different of this one in terms of organization, in terms of intensity, right? The last one is a simulation for the same global simulation. This is a tropical cyclone over Australia. So you can see, for example, when you go to 6, 3, 30 or 15 kilometers, you can see in comparison with, for example, you have some filaments that the model can capture. With the cold pool parameterization, you don't see these filaments on the control run, right? And this is just an example of comparison. We have GS map here for 1-day accumulation. This is the true image. GPM emerging, this is control, and the cold pool. So you can see there is some improvement, right? So I'm going to skip this. I'm going to skip the diurnal cycle. Well, so for our summary, we have a proposal parameterization for interpolates between cold pools, wind shear. I did not mention, but the downdraft parameterization is sensitive to wind shear. So depending on wind shear, you intensify the downdraft and then intensify the cold pool and so on. So I hope you agree that improves organization, longevity, propagation severity of simulation of MCS over the Amazon in different areas. There are rooms to advance. For example, if I have a cloud organization, it's expected that the entrainment rate should be less because you have more moist area. The environment is moister, right? So also you can try to connect shallow congestions the deep through the cold pools. Also, the cold pools can enhance the surface flux, and also can use the Rotuno clamping Weisman theory to determine the slope angle of the leading edge of the cold pool that gives you the maximum vertical velocity that affect the turnover time scale, right? So thank you. Sorry for using more time than.
No, you are on time. Thank you very much. It was a very interesting talk on the cold pool effect on cloud organization. So we'll take some 1 or 2 questions.
Hi, so thanks for great presentation. And the question I have is at what resolution you do not need to parameterize the cold pool dynamics. Your CRM zone is 250 meters.
250 meters was the simulation for understand the physical process.
Right. So if you have NWP model, when do you not need to parameterize the code pool?
Say again, please.
It's what is the model resolution, say for the NWP model. It's what resolution you don't need to parameterize
the code pool.
Yes.
Well, it's hard to say, right? But I think maybe 1-2 kilometers, you start getting better description of the resolved. The old dynamics and cloud microfields can't be enough to create this code pools, the intensity that we expect, and then to propagate signals and trigger convection downstream.
Can I also take the question? Your equation shows you only have horizontal advection, but no vertical advection.
Sorry?
Your equation for your beta advection only has a horizontal advection. There's no vertical.
That's right. That's right. We actually have only horizontal falling terrain, horizontal advection. We don't have any. The signal is transported only following the terrain horizontally. You don't have any vertical velocity.
But this will, so like if it's straight, it has like rounding surface going up and down. Well, I could talk more details with you.
I think you can have the discussion. So any more questions? Yeah.
I have a short question. In your model setup, I realize your first model level is either 70 or 90 meters. And then when I think of the typical global model or regional model with relatively higher horizontal resolution, the typical first model level is much lower. We talk about 10, 20 meters. Any particular reasons for you to pick up such a higher first model level?
Yeah, for example, for MPAS, we run on 20 meters, the first tick of the layer. But for BRAMS is still using the old-fashioned sigma Z coordinate. So as you have very steep topography, unfortunately, it's very easy to unstable if you use a very thin thicker layer. So for example, 90 was what we got that make the run stable because we have the Andes mountain that requires very large delta Z. But the experiments that I did with MPAS was 20 meters, the first layer.
Okay, thank you. So if there are any more burning questions, you can take it up later because we are short of time. Thank you, Dr. Silo Surita. So the next.
Is there online? Ashit, are you there? Yeah.
Yeah, I'm here.
Okay, you can share your PPT.
Question
is there? Okay.
Yeah, the sync term is the same because it depends only the beta X over the lifetime code pool. But I think you can make the lifetime depending on the surface. For example, over the ocean should be different. But the source term is the same because it depends only the convection because it depends on the downdraft scheme.
Oh, thank you. So Ashit, you can start your.
Thank you. Am I audible?
Yes, very well.
Yeah, thank you. I thank for the opportunity to be part of the STIPMEX conference remotely. Unfortunately, I couldn't come. The topic of my today's talk is extreme daily rainfall forecasting and verification challenges. Just I wish to take all the audience back through some of the memorable and infamous events. I'm going to name my next slide. I hope this is visible. This is the famous or infamous Mumbai deluge that occurred in 2005. And we know this is now very famous, and we have had several similar incidents, and we identify them like similarly we had one in 2015 and again in 2023 over the city of Chennai in India. And these are result of sporadic events out of the blue, isolated in nature in terms of space and time, and like they leave behind very severe impacts. The challenge to NWP models is that generally they have a good skill in predicting large scale synoptic features and the rainfall associated with these disturbances and all. However, the isolated nature of intense precipitation activity, intense spells, because of the embedded convective activity and things like that, which are still being understood now, they are still like model fails to capture precisely in terms of intensity, timing and location and things like that. That's what makes accurate prediction of intense events a big challenge for the NWP model. I have organized my presentation like what is seen on the screen. I briefly touch upon what is an extreme event, how WMO guideline provides scope for defining and identifying the extreme events, and briefly touch upon where do we stand now. In recent years, I have picked up model-based forecasts and tried to verify them, and with picking up the extreme rainfall events in recent years using SEEPs and sedimetric, just to see as an example whether these metrics are adequate and whether how they can help the forecaster, how the forecaster confidence in ability of the models to predict this, whether it helps, are they adequate, and that some of the things I'll discuss. And then additionally, I'm moving on to see what kind of products that can be generated to give extreme rainfall forecasts. I've tried to put some based on Ensemble, percentiles, and some type of neighborhood post-processing, PQPF, and things like that. We also have a new idea coming up with extreme value analysis clubbed with the Ensemble-based forecasting systems, and touch upon some of the challenges and role of AI/ML and give a quick summary. I'll go to the next slide. Yeah, what is an extreme? So we already know this, like typically it can be identified in terms of magnitudes or the rareness of event, how rare it, depending on the frequency or the severity of impact or things like that. The graphic on the right clearly indicates in a very nominal scale, we can clearly identify for rainfall and the bottom panel and the temperature in the bottom panel, how the extremes, like towards the end of the tail of the distribution, is where the changes are occurring, and that is what broadly we can understand as extreme. And we can also have go back to some of the early studies with Tom Carl in 95 and other studies have defined, like there could be any number of methods that could be used to establish what an extreme one-day event represents. For rainfall or temperature, it could be a 3-hourly rainfall, it could be an hourly rainfall. So depending on the time of accumulation, specifically for rainfall, or the period of the time of interest, window of interest, also your extreme definition keeps changing. I'll go to the next slide. So just to step further into ahead, like typically we can clearly see that they are very severe. They leave behind a lot of strong socioeconomic impact for property, life, and all. They are very rare, unexpected, underreported. So it's like poorly observed. That is also difficult in terms of understanding and also to manage the impacts and provide the relief and things like that. So that's where the high resolution observations as well as forecasts are very, very important. That's beyond. And in addition to that, we also have probably high resolution observations and forecasts are not adequate. Probably we need some more advanced tools. That's what I want to discuss in this presentation. And also we know that with changing climate like these, extremes are also changing. That is also very well documented in many studies, which are also listed in the IPCC. So the WMO guideline, I have put up the guideline documentation here, and just to indicate here, it's like for precipitation, like it's considered it in terms of rarity, it's like 98th, 95th, and 99th percentile. These are recommended as for any time of time window, whether it's a 3-hourly rainfall or 24-hourly rainfall, 48-hourly rainfall. This could be a very overarching kind of a definition, not necessarily based on the threshold, but more to do with the local climatology and things like that. This perhaps fits in very well and encompasses all the aspects of extreme in terms of nature as well as amount. This is the kind of definition that is recommended by WMO. And in my present study, I have tried to take the same approach with slight deviations. I am using the NCMRWF forecast. So what I'm showing here is the NCMRWF unified model forecast. It has different components. It's a seamless prediction system with global, regional, coupled, ensemble, highly localized convective scale modeling activity, everything. So my today's study will be only confined to little bit of ensemble prediction system results, which is in the third row, and mostly in the first row, the global forecasting deterministic system, which is a 12-kilometer forecasting system. So the medium range forecasts are available up to day 1 to day 10. Similarly, at same resolution of 12 kilometers, we have the ensemble based forecasts up to date 10. I'll quickly move with some of the interesting cases just to highlight the kind of approach I have taken. So I'm just taking the verification metrics SEEPS and SEDI. I'll quickly describe very briefly. SEEPS is based on the work done by Mark Rodwell of ECMWF, and the SEDI metric is proposed by Ferro et al. In 2011. And these have been like traditionally not really focused on extremes, but they have been tested for their applicability and usability for verification of the extreme kind of events. So typically, if we summarize the properties like SEEPS and SEDI metrics, both provide sort of complementary measures of performance. And SEDI uses the climatological distribution, so that allows to identify and define the extreme nature of the events based on the local climatology. And both metrics assess the locally important aspects of the forecast. And they can be aggregated, like further advantages that they can be aggregated across different climatological regions to get the metric. And the statistical property allows it to resistant against hedging. These are some of the useful properties for a very fair score. So SEEPS is perhaps well known to some of the audiences, but for the purpose of continuity, I have just described here. SEEPS measures the error in probability space as opposed to measurement space, and it adopts to the climate of the region. So in particular application, the data could be the station-based observation and forecast, or the grid-based observation and forecast. So the right top graphic clearly summarizes how the data is going to be categorized. So we can have the rainfall probabilities on the y-axis, and we can divide like a very little amount of rain, no rain kind of classification can be had, or a dry, any rainfall activity event can be considered as dry for amounts lower than 0.2 millimeters. And subsequently, the entire data set is generally divided into 3 categories: P1, P2, and P3. So where P3, probability of heavy rain, is half the probability of light rain, right? So that's based on the frequencies. The classification is carried out so that overall overall probability is 1. So SEEPS, this can be further written down into a 3x3 contingency table, and a scoring metric can be found as indicated by summation here. So we can see on the right bottom corner how for Northern Hemisphere, SEEPS metric is seen. It's an integrated measure for all the classes of rainfall, not just heavy rains. However, this could be further applied over our Indian region, and we have tried to see how our forecasts have been changing in the last few years. Like 2016 onwards, we have carried out this, and based on a large number of cases, we have found out that like heavy rainfall and very heavy rainfall, extremely heavy rainfall, we have SEEPS metric here. And this is, this gives some information. This could be very useful for the modelers and this thing. But however, forecasters, it could be not adequate. Like it really doesn't give a satisfaction in terms of individual events, in terms of understanding which are the events that are nicely predicted, which are the events that are skillful, and which are the events which are not. So that allows us to see. I go to the next type of using sedimetric. I have tried to isolate some of the cases here and see. This is the graphic here shows the rainfall, observed rainfall over Mumbai since 1950s, and we can clearly see the 2005 event standing tall amongst all. And this is a kind of the event which I showed in the beginning, like the Mumbai deluge. And apart from that, on the right side, we can see the classification that is standard, like traditionally followed in India. Like you have this is the 90th percentile, 95th percentile, and the 99th percentile. 99th percentile corresponds to our extremely heavy rainfall category that is defined in India. And we can clearly see, like, apart from one of outlier kind of an event in 2005, we have almost every other year, every once or two years, we do have many such events which are exceeding the 99th percentile of the climatology. So this is a challenge, but they are occurring not very regular, but once in a while they occur, and that there is a lot of randomness involved, and it makes it all the forecasting very difficult. So I tried to decide to pick up again our model forecast from 2013 to 2020 and tried to see, like in recent years, again, there was an indication that there is a higher frequency of occurrence of these extreme events. So I picked up some of these cases, 2013 to 2020, and then tried to see focus over Mumbai. The right panel shows the Mumbai geographical region, and the spatial area of interest is identified in my yellow rectangular box. And we can clearly see there is a huge spatial gradient, like all the time you don't have heavy rains at one preferred region. They're slightly varying in different regions. And the bottom panels have a tendency to indicate like there is a tendency to the northeast of Mumbai region where you have peaks occurring. This is from the observations. So similarly, I tried to dig out all the forecasts, and this is just the day one forecast and the observed rainfall, and see the model forecasts also very frequently show large amounts, very heavy rainfall amounts exceeding like 300 millimeters in a day kind of thing, that are very similar to what we see in the observations. So here I am trying to employ sedimetric to see, to try to capture the rare events and all things like that. Hits and false alarm rates decrease towards zero. It's in general what happens. Yeah.
We have 5 more minutes.
Yeah, I am almost done. Yeah. So I'll quickly go on to the other cases. Yeah, the basic problem with verification methodology is highlighted here. Like some of the traditional metrics have difficulty as they taper towards very small values at the lower amounts. And yeah, just to highlight that, sedimetrics allows us to quantify the changes and allows us to quantify improvements towards higher rainfall thresholds where the events are very rare. So this is a kind of improvement. It also has very a large number of merits for which it could be recommended for the verification. But again, it is still not a very the forecaster friendly for its practical use and things like that. Generally, we have had experience in India discussing with the forecasters that these metrics all sound very esoteric and friendly to modelers and not much this thing. So more practical approach, we wanted to develop some of the products, and I have listed here. Just I picked up a recent case of rainfall over Chennai region. So probabilistic forecasts, and especially for heavy rainfall events, do show signatures of heavy rainfall in day 1 and day 3 forecast. With this, we tried to translate in by making use of climatological percentiles to further focus in terms. So bottom panels here show how the rainfall, forecast rainfall exceeding the 90th percentile, climatological 90th percentile. So that gives, that actually removes the model biases and the things like that. So that gives an idea of isolated nature of the event can be depicted for to help the forecasters. Similarly, further, we have also developed a neighborhood type neighborhood PQPF kind of a tool. This will actually give quantify even the spatial biases if there are within a region, within a district kind of a thing, and it will allow us to gain some lead time, even 5 days and 6 days ahead of lead time, or we are able to get the probabilities for higher rainfall amounts. So all said and done, the new approach that we have taken is employing the extreme value analysis and building in terms of forecasting. So the graphic here top shows for the case of Kerala, like the 100-year return period rainfall would look like something like this, and the bottom panels show what happened to the 2019 event. They were exceeding the 100-year return period or not. So the bottom panels clearly identify which are the regions where the rainfall was exceeding the 100-year and 200-year return period levels. So this we are trying to build into the model forecast. So whether my forecast model, the bottom panels here show the forecast rainfall against the return levels that are identified. So this also has a very, very significant use in terms of identifying the occurrence of extreme in terms of something which is not seen in the data, because we have already seen like there are various tools that are coming up. I'll just skip through some of these challenges. I have discussed observation challenges, there are forecasting challenges, and there are verification challenges, some of which I already discussed. But there are a lot of information available from AIM, and can AIML help us predict in extreme, in short and medium range? But we have to keep in mind that AIML require large amount of historical data, and they primarily depend on finding the patterns and training on the patterns. And here we have the events that are outside the patterns, like they're one in a kind of, they're completely outside the system. The training on historical data can't really predict unseen kind of events, unseen and unprecedented kind of events. So that makes it like unprecedented. There is actually no signature in the predictor fields also. So can AIML also prepare us for the extreme event? There are some examples coming from GraphCast and things like that, but still there are challenges in terms of precision, in terms of timing and location. That challenges are still there. So just that's the summary I have put here. Probably the bottom 4 lines I wish to draw your attention, like it could be useful. AIML kind of tools could be useful, but not effective in predicting unseen data. But probably we should have a mechanism to develop them based on unseen data in terms of extreme value analysis and return period analysis, what I mentioned, and also in terms of climate change simulations. Climate change simulations have all kinds of unseen data. Probably AIML tools could be developed based on climate change simulations. Yeah, these are some of the ideas I wanted to share. Thank you. Thank you for your attention.
Thank you, Ashit. Any quick questions to Ashit?
Ashit, so a good talk. You said that this 99 percentile corresponds to 20 centimeter across India. I think that is not correct.
No, that's
Maybe
for Mumbai.
Yeah, that's for Mumbai.
That's for Mumbai. Yeah.
That's one of the problem. If we fix the threshold, then it doesn't.
No.
Percentile. If you fix percentile, it will.
Yeah,
not
no.
add to
The idea of going to percentile is not to fix the threshold value.
Are there any online questions?
Okay. Oh, okay. Thank you. Thank you, Arshid. So now I'm very happy to welcome Dr. Partho Mukhopadhyay for his talk, and who spent enough time in organizing this event jointly with Dr. Suvarna Patnavis. So we will hear from him. So Partha, now you have total 20 minutes. 5 minutes before I'll be giving.
Okay, I'm setting my stopwatch. Okay. Yeah, so thank you. And just to share, I don't know whether I have able to put everything
in the midst of so much of chaotic situation last few days. Okay, so this is my title, but it will. What has happened is you have heard Dr. Patnaik. Now you have heard Raghu. So you must have understood what's going on in India. So Patnaik basically asked. I mean, he showed a list of tools. So you did not ask, but there could have been some questions from audience that who develops this tool? From where do you get these tools? Okay. And he told that we are always there, something like Lalen Richie's famous song, whatever you do, whatever, wherever you are, I am always there waiting for you. So IMD is like that. You should always find Patnaik in any disaster situations, not us, but we are behind them for developing the tools. That is the basic our purpose. Okay. So in IITM, we develop tools from seasonal, from medium range to weekly, S2S, to seasonal, to decadal, to climate. Okay. And the tool what we use is GFS and CFS. So GFS is the model that was adopted as a part of Monsoon mission. Surya is sitting there. And this is AGCM. It's not coupled so far. But we have CFS, and which is coupled. And then we have art system model, where we have a lot of other things which we participated in CMIP 6 and so on. Rain has come, what Estival is predicted. Okay, good. And so these are my colleagues and students who contributed in the large, the results that I will show. Okay, so this is a very, very brief outline. I will give a backdrop of this the extreme rainfall. And then you must have heard this Kerala event, which everybody was referring. And then I will briefly touch upon what approaches we are developing to handle this type of extremes using GFS and other models. And our new development is the global 6 kilometer models. Now, these are the words we are hearing right from team's talk on the first day. We heard about kilometer scale model. We heard about stochastic approaches. We heard many times the ensemble prediction system. We also heard vertical resolution and also hybrid NWP and AI. We have heard many other things as well. At least these I could remember, and these are relevant to our activity. So now these papers also many people have referred by Goswami et al. 2006, Rajivan et al. 2008, and Roxy et al. 2017. The paper basically says, broadly this paper, message of the paper is same. They say that this 5 to 10 centimeter per day is not increasing, whereas more than 10 centimeter per day is increasing. More than 15 centimeter per day is significantly increasing. And that signature, if you see here, it is kind of this time series is put into in spatial. And you can see here that the Gangetic plains are not having so much of extremes, whereas the western part, central India, is getting a significant, the paper argues that it is 3 times, okay? So the focus is here, okay? And also the Northeast in some parts, okay? So keep this in background. Now I come to this Kerala deluge, August 2018. Why I'm telling you, it has become a benchmark problem to me, to all students, researchers. They should really look into this. We have published one paper in weather forecasting in 2021. We have proposed a hypothesis there. We suggested that, the combinations of large-scale westward propagating Rossby waves and moisture conversion must have triggered these extraordinarily strong events, okay? But there can be many other aspects as well. So now I'm going to show you something very, very, very strange. So this was the plot from IMD, okay, which shows is that each districts, okay, each districts of Kerala, these are the districts, how much deficit, how much excess percentage for just this 6th August to 19th August, okay? And what it shows in some station 400%. Can anybody imagine? Okay. And okay, so this is 18, the story of 2018. You go to 2019, it's an action replay. So he says 1 in 100 years. It happened consecutive 2 years, okay? And now this is the most, I mean, strange and surprising, table, I should say. So what it shows for all the districts, this is the climatological standard deviation for these days, okay, 6th to 19th August, okay? What actually has happened, you look at this actual standard deviation, 41 and 50, okay, 74. Can you imagine? Can there be any model in this whole globe which can produce a 74 sigma? Is it feasible? Do we have the science to do this? Answer is no, okay? But this has happened, okay? So Patnaik not even should not dream that this can be predicted, 74 sigma. So the title of our paper was 30 sigma. Okay, now you see the 2019, the same. Some districts, 72 sigma, 54, 14. I mean, it's crazy, 78. Okay? Now, so this is something abnormal happened, consecutive 2 years, not 1 in 100 years. Now you look at this, okay? This is from IMD again. So there was a depression crossing, okay? It was over Bay of Bengal. You can see this is the brightness temperature. Brightness temperature is very low. There are a lot of lightning going on. What is happening here? Nothing. There's nothing. Brightness temperature is substantially high, right? And hardly any lightning. So it will make you more perplexed. So what's going on? In one hand, is 74 sigma rain, okay? And there is no brightness temperature that much low, and there is no lightning happening. So what is this on Earth going on? And you have to predict it, okay? So anyway, now this is what, so forget it. So this is the three state-of-the-art modeling system across in the whole world. GFS, ECMWF, and NCOM, okay? What you see basically, so this black line is the observations, okay? The red line is the climatology, what you have already shown in the table. And these other colors is the forecast for different day, okay? The green is day 1, day 2, day 3, day 4, and day 5. What you see, we are going into the detail, that broadly, only the green color has somewhat come to, close to black color. That's all, okay? No other days forecast is close to the observations. You come to, this is the slide I bought from my friend Roberto Buiza earlier in ECMWF, now in some university in Italy. So what he was showing that this forecast surprisingly was not being predicted in any of the extended range forecast. Okay, this is ECMWF. They could not forecast it. Go to this. This is NCEP CFS. You can see no signature. This is NCMWF, our own 60 kilometer. So the point is, if it is really a, it's a large scale system, this model should have captured it. So what is that? I mean, we said Rossby wave, and this model, of course, is very poor in producing CCWs. So whatever, I mean, this is the fact. So, okay, now let's go to Ensemble, okay? I have to do fast. So this is the current system, what we are using. And you see, this is just to build, to express you that this is called reliability diagram. How reliable is my Ensemble forecast? If you take this is a very heavy rainfall, 11.5 centimeter per day, okay? And you see this blue is for this IITM GFS, green is for NCEP, and red is for ECMWF. And you see when this model goes out of this cone, it loses its reliability, okay? And what we find here for 11.5 centimeter, it is losing its reliability by around 30-40% of probability, okay? So it is not able to say with 60 or 70% probability that a rainfall of 11.5 centimeter per day will happen. This is the situations of Ensemble. But up to 6.5 centimeter per day, okay, they are doing good. Even up to 80%, the IITM GFS, these two are a little less. So the point is, the GFS that we are using, that Patnaik is using, is good. That's the best. We cannot produce something better than this. We are all at par, okay? And don't even dream of 72 sigma, okay? So now, okay, this is for day 5, okay? Day 5 things are not good for 11 point, that is day 1, okay? But day 5, still some, confidence is there up to 6.5 centimeter, okay? Now, this is from our paper again, somewhat similar to what Peter Webster did. And if you see, so what we did is forget 72 sigma. Just take 1 sigma, 2 sigma, and 3 sigma. Model goes flat, okay? If you try to evaluate your model for an event of 4 standard deviation, you will not get any signal. What we are getting here, just in 3 sigma, these models are producing, this is the blue is the observations. You see, the probability for 2 days is something around 70%. It's not going up to 5 days. Okay, for 1 sigma and 1 sigma, the probability is very high, 2 sigma falls down, 3 sigma goes down. So model story gets over by 3 standard deviations. And we are handling whatever Raghu showed just now, all the events, okay, with respect to its climatology, they are all beyond 10 sigma. Okay, we don't have the tool. Dynamical model, and not even AIML, forget. AIML will not get the data to get it driven for this purpose. Okay, fine. So this I am skipping. Okay, they were talking about percentile. Percentile is good. You see the same Kerala event, percentile, it is showing. It's showing. But question is 95th percentile, forecaster will tell extreme, but that does not guarantee that it will give you an event of that magnitude. That's the problem. That's the problem, okay? Percentile is good. Forecaster will be happy. I'm also happy. Yes, there is a, extreme. But what type of extreme? Is it? So that's the challenge. I don't know the answer, okay? Okay, this is the EFI, okay? So my team sitting there, so we developed, first we ran the ensemble of GFS and so on and so forth. And this is the last year, big event over northern India. I could forecast up to day 5. IMD is happy. You can warn people, something very serious going to happen. But again, no magnitude, no standard deviations, we can't. Okay, so this is my colleague, Dr. Deshpande, sitting there. And you see, the beauty of ensemble forecast is, if you depend on deterministic, this cyclone, super cyclone Amphan, we would have concluded it is going to hit Odisha. But the ensemble teaches us, no, it is not. The cyclone will go towards Bengal and Bangladesh. So this is the confidence that the ensemble. So ensemble is the future for all the students. Ensemble forecast is the future, not the deterministic. Okay. Yeah. So new approaches quickly. Okay. So you see, somebody, Siok was telling, increasing the number of vertical levels improves. Okay. You see the same Kerala event, we are struggling. You see, this is the 64 level. And by the way, I think this, Vijay was telling, or somebody, the CFS, we kept on increasing the horizontal resolution, but not the vertical. Okay, this is very strange. So we changed it to L128. Maybe we are going, top of the troposphere or stratosphere. Something is happening. We did not evaluate. But what we have found is that when we do 128, it really improves. Okay, you see, this is the observation and this is the forecast. Okay, so, and there is a paper coming in climate dynamics, which many other things. Okay, yeah.
3 minutes.
Yes, my stopwatch also says that. So, okay, now very quickly, there are many things that we have done. This is one development in GFS where we have changed the microphysics. Fangling was telling about WDM6. We have added WSM6. And what WSM6? And okay, when you add more microphysics, you have to change your radiations accordingly so that your radiation parameter senses all these hydrometeors, which was not there in CFS by default. Okay, so we borrowed SAM, okay, System of Atmospheric Model by Marat. And by doing all these things, okay, I'll just skip it. We get very nice, cloud ice water and cloud liquid water compared with SMWF and also M3 and so on. And as a result of that, models relations with the rainfall and cloud liquid water and ice improves. You see the rain during monsoon, it moves northward. The ice also, the cloud liquid water moves northward, and the cloud ice also moves with some lag. So this we were not able to do. Now we are able to do that. The Taylor diagram shows this model is on top. This is by Surya and BAMS. So many good things. This is stochastic, which our Professor Tim was mentioning. So here what we do is that we use the transition probabilities derived from radar data. This is a new approach, okay? By doing this, I'm not going into detail. There are many, you can read this paper, okay? There are four or five papers published. By doing this, what we got something very, very interesting. You see, this is the CFS V2, okay? I mean, actual, the default. And you don't find any mixed Rossby gravity wave, which actually creates extremes, okay? But when we use this stochastic model, you see all these convectively coupled waves, they are represented very well, okay? So this is one of the benefit, okay? And now, coming to last few slides. So this is the development. The dynamical core, please read this ECMWF newsletter 146, 2015. And you see, this is the currently GFS, what we are using is semi-Lagrangian, okay? All over the globe, it is 12 kilometer. But when we try to use TCO, then what it provides, it gives me a very high resolution over tropics and not so high resolution over extratropics. That gives me some leverage for my computations, okay? Now, what we did is we are here, okay? Using this TCO 1534, we are here. Our target is to come here, okay? So that's what I think team also suggested, okay? So fine. So now this is our development. I'll finish in 1 minute. So we first started with the aquaplanet. Then you do Held-Suarez. There is a BAMS paper. Please read it, okay? When you try to build model, you should first run only the dynamical core, no physics, and see whether the model is stable or not. Held-Suarez, you should check it. So you do Held-Suarez, then you add land, then you add topography, then you add vegetations, okay? And one year goes in this, or maybe more, okay? Finally, you get this, and you get some rainfall, okay? So this is a PDF of rainfall. You see, in day 5, this is GFS rate, and this is TCO. The highest rainfall, 20.45 centimeter, we find this fellow is still trying to capture the black line, okay, where the GFS is not. Okay, so chairman is on standing. Now I will stop. This is no. I'll stop it. So just to give a glimpse that we are getting good results for tropical cyclone as well. You can check the position errors, track errors, intensity errors, okay, particularly in the longer lead, which is needed by IMD. And this is that famous, just now Raghu was telling that last year's Tamil Nadu rain. So GFS is raining here somehow. Okay, TCO somehow is capturing. Okay, so this fellow, because of 6 kilometers, it is trying to capture the orography and all this heterogeneity. So it is capturing here, and this is actual. Okay, so I'll cross all this. No, I have no time. So this is just AIML I mentioned. So there is a system called superparameterization. Some of you may be knowing. If you don't know, you read this paper, Journal of Climate. In superparameterization is a Rolls-Royce car which runs 1 kilometer in 10 liter oil. So nobody used that, okay? So we could not use superparameters. We built it, published it, and kept it, okay? Now, once AIML has come, what we are finding is that we are taking from superparameterizations this tendency, okay? And we are forcing these tendencies. So we are building our layers, okay? And then we are getting a data-driven temperature and moisture tendencies that every grid globally, okay? And you discard your convection, throw it away. Use that tendencies, that's what your GCM needs, right? So, and then just run it, okay? That's what estimally shows. It will be an ant, okay? And so this is work under progress. And this is the last for Zubin. So in the stochastic, we did, cloud transition probabilities from radar. And what we are currently doing is we are using this Go Amazon radar. We have already used our Indian radar. We have also used Dynamo radars and also Darwin. Only Amazon is remaining. So our plan is to use all the available tropical radar, which may be more available when GPEX, SCFX type of experiment will happen, use those and make this model stochastic representative, not just for India or West Pacific, but for whole globe. And then, try to simulate. I stop. Yeah, thank you.
Thank you, Dr. Partha. Yeah, for a very interesting new ideas for
Thanks.
Tackling the extreme event. So if you have any, so already we have crossed the tea time.
Yes,
But
I have taken 1 minute extra.
If you have
Sorry.
any questions here, or you can take it up, discuss with Dr. Partha during the tea time.
Yes, I think that's better.
So,
Or if there is any burning
yes,
question.
Anybody? Yeah.
Yes, please.
So by now we have already found out that there are places where these events happen at like a larger frequency, especially say in Uttarakhand or in Bombay. Do we have some dedicated local models or systems which just run for these places? So I know that this is monsoon time and there can be an evident cloudburst in Uttarakhand. So I have a dedicated model which runs for just that area, just so that it's faster to get the results and all.
I really don't know. Okay, I actually don't work with any dedicated model for any specific region. I even don't know whether such a dedicated model without any data dedicated for that region can even be developed.
No, so the boundary condition on that region would be given by, say, the global models.
That doesn't work. That will never work. I can give my all boundary condition, initial condition from TCO GFS, and you try to simulate. Raghu said Bombay, I said Chennai. These are the two events, 1 meter rain in 24 hours. Okay. Sometime you will get, sometimes it is absolutely random. So there is no dedication. Unless otherwise you have the dedicated data of that region, you can't expect. It's not a black magic. Model is a tool. Charney has told it's an initial value problem. Unless otherwise I improve my initial condition, I should not even expect that this model will give me something. We have nothing to improve. How many rain gauges data were there in Chennai? Only 2. How many rain gauges are there over Pune? Only 2, 3. So it doesn't make any sense. We should not expect, we should not even dream that we can catch. I don't know, these models are doing something amazing, maybe God's grace. We are getting these things. I, as a NWP person, I don't even expect that this model will capture. What model is capturing? Every morning I get surprised. How does it do that without any data?
Okay, then
Yeah.
I think you can continue during the
Let's
time.
stop
So,
here.
so thank you very much,
Thank
Dr.
you.
Partha, and thanks to the all speakers also. Thank you very much.
Thank you, Dr. Rao and Dr. Sanjay, to chair the session. I request Dr. Rao to come up on the stage to present the mementos to the speakers. Dr. Patnaik, if he's here. Yeah. Okay. Dr. Saulo Freitas. Dr. Mukhopadhyay. I request Dr. Sahai to come on the stage to felicitate the co-chair and chair. Dr. Sanjay, please come up on the stage. Thank you. Thank you, sir. Just a few announcements that we have. Poster judges of PMEX theme, kindly complete the evaluation by today's poster session and return your recommendations to the organizers. We'll have the poster session on the PMEX theme in the basement of this auditorium. Tea has been arranged there as well as near the reception desk. The cultural program will begin at 7 p.m. So kindly be seated by 6:45. And the program will be followed by a dinner adjacent to this auditorium. Thank you.